Made Easy by Silvanus P. Thompson. What one fool can do, another can. Ancient Simian proverb. Preface to the second edition. The surprising success of this work has led the author to add a considerable number of worked examples and exercises. Advantage has also been taken to enlarge certain parts where experience has shown that further explanations would be useful. The author acknowledges with gratitude many valuable suggestions and letters received from teachers, students, and critics. October 1914. Prologue. Considering how many fools can calculate, it is surprising that it should be thought either a difficult or a tedious task for any other fool to learn how to master the same tricks. Some calculus tricks are quite easy. Some are enormously difficult. The fools who write the textbooks of advanced mathematics, and they are mostly clever fools, seldom take the trouble to show you how easy the easy calculations are. On the contrary, they seem to desire to impress you with their tremendous cleverness by going about it in the most difficult way. Being myself a remarkably stupid fellow, I have had to unteach myself the difficulties, and now beg to present to my fellow fools the parts that are not hard. Master these thoroughly, and the rest will follow. What one fool can do, another can. End of Preface and Prologue. To deliver you from the preliminary terrors. The preliminary terror, which chokes off most fifth-form boys from even attempting to learn how to calculate, can be abolished once for all by simply stating what is the meaning, in common-sense terms, of the two principal symbols that are used in calculating. These dreadful symbols are 1. D, which merely means a little bit of. Thus, dx means a little bit of x, or du means a little bit of u. Ordinary mathematicians think it more polite to say an element of instead of a little bit of, just as you please, but you will find that all these little bits, or elements, may be considered to be indefinitely small. 2. The integral symbol, which is merely a long s and may be called, if you like, the sum of. Thus, the integral of dx means the sum of all the little bits of x, or the integral of dt means the sum of all the little bits of t. Ordinary mathematicians call this symbol the integral of. Now, any fool can see that if x is considered to be made up of a lot of little bits, each of which is called dx, if you add them all up together, you get the sum of all the dx's, which is the same thing as the whole of x. The word integral simply means the whole. If you think of the duration of time for 1 hour, you may, if you like, think of it as cut up into 3,600 little bits called seconds. The whole of the 3,600 little bits added up together make 1 hour. When you see an expression that begins with this terrifying symbol, you will henceforth know that it is put there merely to give you instructions that you are now to perform the operation, if you can, of totaling up all the little bits that are indicated by the symbols that follow. That's all. End of Section 1.
Calculus Made Easy by Silvanus P. Thompson. On different degrees of smallness. We shall find that in our process of calculation we have to deal with small quantities of various degrees of smallness. We shall have also to learn under what circumstances we may consider small quantities to be so minute that we may omit them from consideration. Everything depends upon relative minuteness. Before we fix any rules, let us think of some familiar cases. There are 60 minutes in the hour, 24 hours in the day, 7 days in the week, and there are therefore 1,440 minutes in the day and 10,080 minutes in the week. Obviously, 1 minute is a very small quantity of time compared with a whole week. Indeed, Our forefathers considered it small as compared with an hour, and called it 1 minute, meaning a minute fraction, namely 1/60th of an hour. When they came to require still smaller subdivisions of time, they divided each minute into 60 still smaller parts, which in Queen Elizabeth's days they called second minutes, i.e., small quantities of the second order of minuteness. And nowadays we call these small quantities of the second order of smallness seconds, but few people know why they are so called. Now, if 1 minute is so small as compared with a whole day, how much smaller by comparison is 1 second? Again, think of a farthing as compared with a sovereign. It is barely worth more than 1/1000th part. A farthing, more or less, is of precious little importance compared with a sovereign. It may certainly be regarded as a small quantity. But compare a farthing with 1,000 pounds. Relatively to this greater sum, the farthing is of no more importance than 1/1000th of a farthing would be to a sovereign. Even a golden sovereign is relatively a negligible quantity in the wealth of a millionaire. Now, if we fix upon any numerical fraction as constituting the proportion for which any purpose we call relatively small, we can easily state other fractions of a higher degree of smallness. Thus, if, for the purpose of time, 1/60 be called a small fraction, then 1/60 of 1/60, being a small fraction of a small fraction, may be regarded as a small quantity of the second order of smallness. Footnote: the mathematicians talk about the second order of magnitude, i.e., greatness, when they really mean second order of smallness. This is very confusing to beginners. Or if for any purpose we were to take 1%, i.e., 1/100, as a small fraction, then 1% of 1%, i.e., 1/10,000, would be a small fraction of the second order of smallness, and 1/1,000,000 would be a small fraction of the third order of smallness, being 1% of 1% of 1%. Lastly, suppose that for some very precise purpose we should regard 1/1,000,000 as small. Thus, if a first-rate chronometer is not to lose or gain more than half a minute in a year, it must keep time with an accuracy of 1 part in 1,051,200. Now, if for such a purpose we regard 1/1,000,000, or 1/1,000th, as a small quantity, then 1/1,000,000 of 1/1,000,000, that is 1/1,000,000,000, or 1/1000th, will be a small quantity of the second order of smallness, and may be utterly disregarded by comparison. Then we see that the smaller a small quantity itself is, the more negligible does the corresponding small quantity of the second order become. Hence we know that in all cases we are justified in neglecting the small quantities of the second or third or higher orders, if only we take the small quantity of the first order small enough in itself. But it must be remembered that small quantities, if they occur in our expressions as factors multiplied by some other factor, may become important if the other factor is itself large. Even a farthing becomes important if only it is multiplied by a few hundred. Now, in the calculus we write dx for a little bit of x. These things, such as dx and du and dy, are called differentials. The differential of x, or of u, or of y, as the case may be. You read them as dx or du or dy. If dx be a small bit of x, and relatively small of itself, it does not follow that such quantities as x times dx, or x squared dx, or a to the x power dx are negligible. but dx times dx would be negligible, being a small quantity of the second order. A very simple example will serve as illustration. Let us think of x as a quantity that can grow by a small amount so as to become x plus dx, where dx is the small increment added by growth. The square of this is x squared plus 2x times dx plus parentheses dx close parentheses squared. The second term is not negligible because it is a first-order quantity, while the third term is of the second order of smallness, being a bit of x squared. Thus, if we took dx to mean numerically, say, 1/60 of x, then the second term would be 2/60 of x squared, whereas the third term would be 1/3600 of x squared. This last term is clearly less important than the second. But if we go further and take dx to mean only 1/1000 of x, then the second term will be 2/1000 of x squared, while the third term will be only 1/1,000,000 of x squared. Geometrically, this may be depicted as follows. Draw a square, the side of which we will take to represent x. Now suppose the square to grow by having a bit dx added to its size each way. The enlarged square is made up of the original square, x squared. The two rectangles at the top and on the right, each of which is of area x times dx, or together 2x times dx, and the little square at the top right-hand corner, which is parentheses dx close parentheses squared. In figure 2 we have taken dx as quite a big fraction of x, about 1/5. But suppose we had taken it only 1/100, about the thickness of an inked line drawn with a fine pen. Then the little corner square will have an area of only 1/10,000 of x squared, and be practically invisible. Clearly, parentheses dx close parentheses squared is negligible, if only we consider the increment dx to be itself small enough. Let us consider a simile. Suppose a millionaire were to say to his secretary, "Next week I will give you a small fraction of any money that comes in to me." Suppose that the secretary were to say to his boy, "I will give you a small fraction of what I get." Suppose the fraction in each case to be 1/100 part. Now, if Mr. Millionaire received during the next week £1,000, the secretary would receive £10, and the boy 2 shillings. £10 would be a small quantity compared with £1,000, but 2 shillings is a small quantity indeed, of a very secondary order. But what would be the disproportion if the fraction, instead of being 1/100, had been settled at 1/1000 part? Then, while Mr. Millionaire got his £1,000, Mr. Secretary would get only £1, and the boy less than 1 farthing. The witty Dean Swift once wrote, "So naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller fleas to bite 'em, and so proceed ad infinitum." On Poetry, a Rhapsody, page 20, printed 1733, usually misquoted. An ox might worry about a flea of ordinary size, a small creature of the first order of smallness, but he would probably not trouble himself about a flea's flea, being of the second order of smallness. It would be negligible. Even a gross of fleas would not be of much account to the ox. End of section 2.
Calculus Made Easy by Silvanus P. Thompson. on relative growings. All through the calculus we are dealing with quantities that are growing, and with rates of growth. We classify all quantities into two classes, constants and variables. Those which we regard as a fixed value, and call constants, we generally denote algebraically by letters from the beginning of the alphabet, such as A, B, or C, while those which we consider as capable of growing, or, as mathematicians say, of varying, we denote by letters from the end of the alphabet, such as X, Y, Z, U, V, W, or sometimes T. Moreover, we are usually dealing with more than one variable at once, and thinking of the way in which one variable depends on the other. For instance, we think of the way in which the height reached by a projectile depends on the time of attaining that height. Or we are asked to consider a rectangle of given area, and to inquire how any increase in the length of it will compel a corresponding decrease in the breadth of it. Or we think of the way in which any variation in the slope of a ladder will cause the height that it reaches to vary. Suppose we have got two such variables that depend one on the other. An alteration in one will bring about an alteration in the other because of this dependence. Let us call one of the variables x and the other that depends on it y. Suppose we make x to vary. That is to say, we either alter it or imagine it to be altered, by adding to it a bit which we call dx. We are thus causing x to become x plus dx. Then, because x has been altered, y will have altered also, and will have become y plus dy. Here the bit dy may be in some cases positive, in others negative, and it won't, except by a miracle, be the same size as dx. Take two examples. 1. Let x and y be respectively the base and the height of a right-angled triangle, Fig. 4, of which the slope of the other side is fixed at 30 degrees. If we suppose this triangle to expand, and yet keep its angles the same as at first, then, when the base grows so as to become x plus dx, the height becomes y plus dy. Here, increasing x results in an increase of y. The little triangle, the height of which is dy, and the base of which is dx, is similar to the original triangle, and it is obvious that the value of the ratio dy over dx is the same as that of the ratio y over x. As the angle is 30 degrees, it will be seen that here dy over dx equals 1 over 1.73. 2. Let x represent, in Figure 5, the horizontal distance from a wall of the bottom end of a ladder, AB, of fixed length, and let y be the height it reaches up the wall. Now y clearly depends on x. It is easy to see that if we pull the bottom end A a bit further from the wall, the top end B will come down a little lower. Let us state this in scientific language. If we increase x to x plus dx, then y will become y minus dy. That is, when x receives a positive increment, the increment which results to y is negative. Yes, but how much? Suppose the ladder was so long that when the bottom end A was 19 inches from the wall, the top end B reached just 15 feet from the ground. Now, if you were to pull the bottom end out 1 inch more, how much would the top end come down? Put it all into inches. X equals 19 inches, y equals 180 inches. Now the increment of x, which we call dx, is 1 inch, or x plus dx equals 20 inches. How much will y be diminished? The new height will be y minus dy. If we work out the height by Euclid 1:47, then we shall be able to find how much dy will be. The length of the ladder is the square root of the sum 180 squared plus 19 squared equals 181 inches. Clearly then, the new height, which is y minus dy, will be such that the difference y minus dy squared equals 181 squared minus 20 squared equals 32,761 minus 400 equals 32,361. Y minus dy equals the square root of 32,361 equals 179.89 inches. Now y is 180, so that dy is 180 minus 179.89 equals 0.11 inch. So we see that making dx an increase of 1 inch has resulted in making dy a decrease of 0.11 inch. And the ratio of dy to dx may be stated thus: dy over dx is equal to negative 0.11 over 1. It is also easy to see that, except in one particular position, dy will be of a different size from dx. Now right through the differential calculus we are hunting for a curious thing, a mere ratio, namely the proportion which dy bears to dx when both of them are indefinitely small. It should be noted here that we can only find this ratio dy over dx when y and x are related to each other in some way, so that whenever x varies, y does vary also. For instance, in the first example just taken, if the base x of the triangle be made longer, the height y of the triangle becomes greater also. And in the second example, if the distance x of the foot of the ladder from the wall be made to increase, the height y reached by the ladder decreases in a corresponding manner, slowly at first, but more and more rapidly as x becomes greater. In these cases, the relation between x and y is perfectly definite. It can be expressed mathematically, being y over x equals tangent 30 degrees, and x squared plus y squared equals L squared, where L is the length of the ladder respectively, and dy over dx has the meaning we found in each case. If, while x is, as before, the distance of the foot of the ladder from the wall, y is, instead of the height reached, the horizontal length of the wall, or the number of bricks in it, or the number of years since it was built, any change in x would naturally cause no change whatever in y. In this case, dy over dx has no meaning whatever, and it is not possible to find an expression for it. Whenever we use differentials dx, dy, dz, etc., the existence of some kind of relation between x, y, z, etc. is implied, and this relation is called a function in x, y, z, etc. The two expressions given above, for instance, namely y over x equals tangent 30 degrees, and x squared plus y squared equals L squared, are functions of x and y. Such expressions contain implicitly, that is, contain without distinctly showing it, the means of expressing either x in terms of y or y in terms of x. And for this reason they are called implicit functions in x and y. They can be respectively put into the forms y equals x times tangent 30 degrees, or x equals y over tangent 30 degrees, and y equals square root of the difference L squared minus x squared, or x equals square root of the difference L squared minus y squared. These last expressions state explicitly, that is distinctly, the value of x in terms of y, or of y in terms of x, and they are for this reason called explicit functions of x or y. For example, x squared plus 3 equals 2y minus 7 is an implicit function in x and y. It may be written y equals the quantity x squared plus 10 over 2, explicit function of x, or x equals square root of the difference to y minus 10, explicit function of y. We see that an explicit function in x, y, z, etc. is simply something the value of which changes when x, y, z, etc. are changing, either one at the time or several together. Because of this, the value of the explicit function is called the dependent variable, as it depends on the value of the other variable quantities in the function. These other variables are called the independent variables, because their value is not determined from the value assumed by the function. For example, if u equals x squared times sine theta, x and theta are the independent variables, and u is the dependent variable. Sometimes the exact relation between several quantities x, y, z either is not known, or it is not convenient to state it. It is only known or convenient to state that there is some sort of relation between these variables, so that one cannot alter either x or y or z singly without affecting the other quantities. The existence of a function in x, y, z is then indicated by the notation capital F of x, y, z, implicit function, or by x equals capital F of y and z, y equals capital F of x and z, or z equals capital F of x and y, explicit function. Sometimes the letter lowercase f or phi is used instead of uppercase F, so that y equals uppercase f of x, y equals lowercase f of x, and y equals phi of x all mean the same thing, namely, that the value of y depends on the value of x in some way which is not stated. We call the ratio dy over dx the differential coefficient of y with respect to x. It is a solemn scientific name for this very simple thing. But we are not going to be frightened by solemn names, when the things themselves are so easy. Instead of being frightened, we will simply pronounce a brief curse on the stupidity of giving long, crack-jaw names, and, having relieved our minds, we'll go on to the simple thing itself, namely the ratio dy over dx. In ordinary algebra, which you learned at school, you were always hunting after some unknown quantity which you called x or y. Or sometimes there were two unknown quantities to be hunted for simultaneously. You have now to learn to go hunting in a new way, the fox being now neither x nor y. Instead of this, you have to hunt for this curious cub called dy over dx. The process of finding the value of dy over dx is called differentiating. But remember, what is wanted is the value of this ratio when both dy and dx are themselves indefinitely small. The true value of the differential coefficient is that to which it approximates in the limiting case when each of them is considered as infinitesimally minute. Let us now learn how to go in quest of dy over dx. Note to Chapter 3. How to read differentials. It will never do to fall into the schoolboy error of thinking that dx means d times x, for d is not a factor. It means an element of, or a bit of, whatever follows. One reads dx thus, dx. In case the reader has no one to guide him in such matters, it may here be simply said that one reads differential coefficients in the following way. The differential coefficient dy over dx is read dy by dx or dy over dx. So also du over dt is read du by dt. Second differential coefficients will be met with later on. They are like this: d superscript 2y over d x superscript 2, which is read d2y over dx squared. And it means that the operation of differentiating y with respect to x has been or has to be performed twice over. Another way of indicating that a function has been differentiated is by putting an accent to the symbol of the function. Thus, if y equals capital F of x, which means that y is some unspecified function of x, see page 13, we may write capital F prime of x instead of d capital F of x over dx. Similarly, capital F double prime of x will mean that the original function capital F of x has been differentiated twice over with respect to x. End of section 3. Calculus Made Easy by Silvanus P. Thompson. Simplest cases. Now, let us see how, on first principles, we can differentiate some simple algebraical expression. Case 1. Let us begin with the simple expression y equals x squared. Now remember that the fundamental notion about the calculus is the idea of growing. Mathematicians call it varying. Now, as y and x squared are equal to one another, it is clear that if x grows, x squared will also grow. And if x squared grows, then y will also grow. What we have got to find out is the proportion between the growing of y and the growing of x. In other words, our task is to find out the ratio between dy and dx, or, in brief, to find the value of dy over dx. Let x then grow a little bit bigger and become x plus dx. Similarly, y will grow a bit bigger and will become y plus dy. Then, clearly, it will still be true that the enlarged y will be equal to the square of the enlarged x. Writing this down, we have y plus dy equals the quantity x plus dx squared. Doing the squaring, we get y plus dy equals x squared plus 2x times dx plus dx squared. What does dx squared mean? Remember that dx meant a little bit, of x. Then dx squared will mean a little bit of x. That is, as explained above, page 4, it is a small quantity of the second order of smallness. It may therefore be discarded as quite inconsiderable in comparison with the other terms. Leaving it out, we then have y plus dy equals x squared plus 2x times dx. Now y equals x squared, so let us subtract this from the equation, and we have left dy equals 2x times dx. Dividing across by dx, we find dy over dx equals 2x. Now this is what we set out to find. Note: This ratio dy over dx is the result of differentiating y with respect to x. Differentiating means finding the differential coefficient. Suppose we had some other function of x, as for example, u equals 7x squared plus 3. Then, if we were told to differentiate this with respect to x, we should have to find du over dx, or, what is the same thing, d, the quantity 7x squared plus 3, over dx. On the other hand, we may have a case in which time was the independent variable, see page 14, such as this. Y equals b plus the fraction 1/2 a t squared. Then, if we were told to differentiate it, that means we must find its differential coefficient with respect to t. So that then our business would be to try to find dy over dt, that is, to find d, the quantity, b plus the fraction 1/2 a t squared over dt. End of note. The ratio of the growing of y to the growing of x is, in the case before us, found to be 2x. Numerical example. Suppose x equals 100, and therefore y equals 10,000. Then let x grow till it becomes 101. That is, let dx equal 1. Then the enlarged y will be 101 times 101 equals 10,201. But if we agree that we may ignore small quantities of the second order, 1 may be rejected as compared with 10,000. So we may round off the enlarged y to 10,200. Y has grown from 10,000 to 10,200. The bit added on is dy, which is therefore 200. dy over dx equals 200 over 1 equals 200. According to the algebra working of the previous paragraph, we find dy over dx equals 2x. And so it is, for x equals 100 and 2x equals 200. But, you will say, we neglected a whole unit. Well, try again, making dx a still smaller bit. Try dx equals the fraction 1/10. Then x plus dx equals 100.1. And the quantity x plus dx squared equals 100.1 times 100.1 equals 10,020.01. Now the last figure 1 is only 1/millionth part of the 10,000, and is utterly negligible, so we may take 10,020 without the little decimal at the end. And this makes dy equals 20, and dy over dx equals 20 over 0.1 equals 200, which is still the same as 2x. Case 2. Try differentiating y equals x cubed in the same way. We let y grow to y plus dy, while x grows to x plus dx. Then we have y plus dy equals the quantity x plus dx cubed. Doing the cubing, we obtain y plus dy equals x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed. Now we know that we may neglect small quantities of the second and third orders, since when dy and dx are both made indefinitely small, dx squared and dx cubed will become indefinitely smaller by comparison. So regarding them as negligible, we have left y plus dy equals x cubed plus 3x squared times dx. But y equals x cubed, and subtracting this, we have dy equals 3x squared times dx, and dy over dx equals 3x squared. Case 3. Try differentiating y equals x raised to the fourth power. Starting as before by letting both y and x grow a bit, we have y plus dy equals the quantity x plus dx raised to the fourth power. Working out the raising to the fourth power, we get y plus dy equals x raised to the fourth power plus 4x cubed times dx plus 6x squared times dx squared plus 4x times dx cubed plus dx raised to the fourth power. Then striking out the terms containing all the higher powers of dx as being negligible by comparison, we have y plus dy equals x raised to the fourth power plus 4x cubed times dx. Subtracting the original y equals x to the fourth power, we have left dy equals 4x cubed times dx and dy over dx equals 4x cubed. Now all these cases are quite easy. Let us collect the results to see if we can infer any general rule. Put them in two columns, the values of y in one and the corresponding values found for dy over dx in the other. Thus, when y is x squared, dy over dx is 2x. When y is x cubed, dy over dx is 3x squared. When y is x raised to the fourth power, dy over dx is 4x cubed. Just look at these results. The operation of differentiating appears to have had the effect of diminishing the power of x by 1. For example, in the last case, reducing x raised to the fourth power to x cubed, and at the same time multiplying by a number, the same number, in fact, which originally appeared as the power. Now, when you have once seen this, you might easily conjecture how the others will run. You would expect that differentiating x raised to the fifth power would give 5x raised to the fourth power, or differentiating x raised to the sixth power would give 6x raised to the fifth power. If you hesitate, try one of these and see whether the conjecture comes right. Try y equals x raised to the fifth power. Then, y plus dy equals the quantity x plus dx raised to the fifth power equals x raised to the fifth power plus 5x raised to the fourth power times dx plus 10x cubed times dx squared plus 10x squared times dx cubed plus 5x times dx raised to the fourth power plus dx raised to the fifth power. Neglecting all the terms containing small quantities of the higher orders, we have left y plus dy equals x raised to the fifth power plus 5x raised to the fourth power times dx. And subtracting y equals x raised to the fifth power leaves us dy equals 5x raised to the fourth power times dx, whence dy over dx equals 5x raised to the fourth power exactly as we supposed. Following out logically our observation, we should conclude that if we want to deal with any higher power, call it n, we could tackle it in the same way. Let y equal x raised to the n power. Then we should expect to find that dy over dx equals n x raised to the n minus 1 power. For example, let n equal 8. Then y equals x raised to the 8th power. And differentiating it would give dy over dx equals 8x raised to the 7th power. And indeed, the rule that differentiating x raised to the n power gives, as the result, n x raised to the n minus 1 power is true for all cases where n is a whole number and positive. Expanding the quantity x plus dx raised to the n power by the binomial theorem will at once show this. But the question whether it is true for cases where n has negative or fractional values requires further consideration. Case of a negative power. Let y equal x to the minus 2. Then proceed as before. Y plus dy equals the quantity x plus dx to the minus 2 equals x to the minus 2 times the quantity 1 plus dx over x to the minus 2. Expanding this by the binomial theorem, see page 137, we get equals x to the minus 2 times the quantity 1 minus 2 dx over x plus 2 times the quantity 2 plus 1 over 1 times 2. That fraction times the quantity dx over x squared minus etc. equals x to the minus 2 minus 2x to the minus 3 times dx plus 3x to the minus 4 times dx squared minus 4x to the minus 5 times dx cubed plus etc. So, neglecting the small quantities of higher orders of smallness, we have y plus dy equals x to the minus 2 minus 2x to the minus 3 times dx. Subtracting the original y equals x to the minus 2, we find dy equals negative 2x to the minus 3 times dx. dy over dx equals negative 2x to the minus 3. And this is still in accordance with the rule inferred above. Case of a fractional power. Let y equal x to the 1/2. Then, as before, y plus dy equals the quantity x plus dx to the 1/2 equals x to the 1/2 times the quantity 1 plus dx over x to the 1/2 equals the square root of x plus 1/2 times dx over the square root of x minus 1/8 times dx squared over x times the square root of x plus terms with higher powers of dx. Subtracting the original y equals x to the 1/2 and neglecting higher powers, we have left dy equals 1/2 times dx over the square root of x equals 1/2 x to the minus 1/2 times dx, and dy over dx equals 1/2 x to the minus 1/2. Agreeing with the general rule. Summary. Let us see how far we have got. We have arrived at the following rule. To differentiate x raised to the n power, multiply by the power and reduce the power by 1, so giving us n x raised to the n minus 1 power as the result. End of section 4.
Calculus Made Easy by Silvanus P. Thompson, Section 5. Exercises 1. Differentiate the following. 1. y equals x to the power of 13. Answer: dy by dx equals 13x to the power of 12. 2. Y equals x to the power of negative 3 halves. Answer: dy by dx equals negative 3 halves x to the power of negative 5 halves. 3. Y equals x to the power of 2a. Answer: dy by dx equals 2ax to the power of 2a minus 1. 4. U equals t to the power of 2.4. Answer: du by dt equals 2.4 t to the power of 1.4. 5. Z equals the cube root of u. Answer: dz by du equals 1/3 u to the power of negative 2/3. 6. Y equals the cube root of x to the negative 5. Answer: dy by dx equals negative 5/3 x to the power of negative 8/3. 7. U equals the fifth root of 1 over x to the 8th. Answer: du by dx equals negative 8/5 x to the power of negative 13/5. 8. Y equals 2x to the power of a. Answer: dy by dx equals 2a x to the power of a minus 1. 9. Y equals the qth root of x to the third. Answer: dy by dx equals 3 over q times x to the power of 3 minus q over q. 10. Y equals the nth root of 1 over x to the m. Answer: dy by dx equals negative m over n x to the power of negative m plus n over n. You have now learned how to differentiate powers of x. How easy it is! End of section 5.
Next stage. What to do with constants. In our equations, we have regarded x as growing, and as a result of x being made to grow, y also changed its value and grew. We usually think of x as a quantity that we can vary, and, regarding the variation of x as a sort of cause, we consider the resulting variation of y as an effect. In other words, we regard the value of y as depending on that of x. Both x and y are variables, but x is the one that we operate upon, and y is the dependent variable. In all the preceding chapter, we have been trying to find out rules for the proportion which the dependent variation in y bears to the variation independently made in x. Our next step is to find out what effect on the process of differentiating is caused by the presence of constants, that is, of numbers which don't change when x or y change their values. Added constants. Let us begin with some simple case of an added constant. Thus, let y equal x cubed plus 5. Just as before, let us suppose x to grow to x plus dx and y to grow to y plus dy. Then y plus dy equals the sum of x plus dx cubed plus 5 equals x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed plus 5. Neglecting the small quantities of higher orders, this becomes y plus dy equals x cubed plus 3x squared times dx plus 5. Subtract the original y equals x cubed plus 5, and we have left dy equal 3x squared dx. dy over dx equals 3x squared. So the 5 has quite disappeared. It added nothing to the growth of x and does not enter into the differential coefficient. If we had put 7 or 700 or any other number instead of 5, it would have disappeared. So if we take the letter A or B or C to represent any constant, it will simply disappear when we differentiate. If the additional constant had been of negative value, such as -5 or -b, it would equally have disappeared. Multiplied constants. Take as a simple experiment this case. Let y equal 7x squared. Then on proceeding as before, we get y plus dy equals 7 times the quantity of x plus dx squared equals 7, left bracket, x squared plus 2x times dx plus the quantity dx squared, right bracket, equals 7x squared plus 14x times dx plus 7 times the quantity dx squared. Then, subtracting the original y equals 7x squared and neglecting the last term, we have dy equals 14x times dx. dy over dx equals 14x. Let us illustrate this example by working out the graphs of the equation y equals 7x squared and dy over dx equals 14x. By assigning to x a set of successive values 0, 1, 2, 3, etc., and finding the corresponding values of y and of dy over dx. These values we tabulate as follows. When x is 0, y is 0, dy over dx is 0. When x is 1, y is 7, dy over dx is 14. When x is 2, y is 28, dy over dx is 28. When x is 3, y is 63, dy over dx 42. When x is 4, y is 112, dy over dx is 56. When x is 5, y is 175, dy over dx is 70. When x is -1, y is 7, dy over dx is -14. When x is -2, y is 28, dy over dx is -28. When x is -3, y is 63, dy over dx is -42. Now, plot these values to some convenient scale, and we obtain the two curves of Figure 6 and 6a. Figure 6, graph of y equals 7x squared. X-axis is scaled -3, -2, -1, 0, 1, 2, 3, 4, 5. Y-axis scaled 0, 50, 100, 150, 200, with a curve through 0, 0, 1, 7, 2, 28, 3, 63, 4, and 112, 5, and 175, -1 and 7, -2 and 28, -3, 63. Figure 6a, Graph of dy over dx equals 14x. X-axis scaled at -3, -2, -1, 0, 1, 2, 3, 4, 5. dy over dx axis scaled -50, 0, 50, 100, 150, with a curve through points 0, 0, 1, 14, 2, 28, 3, 42, 4, 56, 5, 70, -1, -14, -2, -28, -3, -42. Carefully compare the two figures and verify by inspection that the height of the ordinate of the derived curve, figure 6a, is proportional to the slope of the original curve, figure 6, at the corresponding value of x. Note: see page 76 about slopes of curves. To the left of the origin, where the original curve slopes negatively, that is downward from left to right, the corresponding ordinates of the derived curves are negative. Now, if we look back at page 18, we shall see that simply differentiating x squared gives us 2x, so that the differential coefficient of 7x squared is just 7 times as big as that of x squared. If we had taken 8x squared, the differential coefficient would have come out 8 times as great as that of x squared. If we put y equals ax squared, we shall get dy over dx equals a times 2x. If we had begun with y equals ax to the nth power, we should have had dy over dx equals a times nx to the n minus 1 power, so that any mere multiplication by a constant reappears as a mere multiplication when the thing is differentiated, and what is true about multiplication is equally true about division. For if, in the example above, we had taken as the constant 1/7 instead of 7, we should have had the same 1/7 come out in the result after differentiation. Some further examples. The following further examples, fully worked out, will enable you to master completely the process of differentiation as applied to ordinary algebraic expressions, and enable you to work out by yourself the examples given at the end of this chapter. Number 1. Differentiate. Y equals x to the 5th power over 7 minus 3 over 5. 3 over 5 is an added constant and vanishes. See page 25. We may then write at once dy over dx equals 1/7 times 5 times x to the 5 minus 1 power, or dy over dx equals 5/7 times x to the 4th power. Number 2. Differentiate y equals a square root of x minus 1/2 square root of a. The term 1/2 square root of a vanishes, being an added constant, and as a square root of x in the index form is written ax to the 1/2 power, we have dy over dx equals a times 1/2 times x to the 1/2 minus 1 power equals a over 2 times x to the negative 1/2 power, or dy over dx equals a over 2 times the square root of x. 3. If ay plus bx equals by minus ax plus the sum of x plus y times the square root of a squared minus b squared, find the differential coefficient of y with respect to x. As a rule, an expression of this kind will need a little more knowledge than we have acquired so far. It is, however, always worthwhile to try whether the expression can be put in a simpler form. First, we must try to bring it into the form y equals some expression involving x only. The expression may be written: the quantity a minus b times y plus the quantity a plus b times x equals the quantity x plus y times the square root of a squared minus b squared. Squaring, we get the quantity a minus b squared times y squared plus the quantity a plus b squared times x squared plus 2 times the quantity a plus b times the quantity a minus b times xy equals the quantity x squared plus y squared plus 2xy times the quantity a squared minus b squared, which simplifies to quantity a minus b squared y squared plus quantity a plus b squared x squared equals x squared times the quantity of a squared minus b squared plus y squared times the quantity of a squared minus b squared, or open bracket quantity a minus b squared minus quantity a squared minus b squared close bracket y squared equals open bracket quantity a squared minus b squared minus quantity a plus b squared close bracket x squared. That is 2b times the quantity of b minus a times y squared equals negative 2b times the quantity of b plus a times x squared. Hence, y equals the square root of a plus b over a minus b times x, and dy over dx equals the square root of a plus b over a minus b. Number 4. The volume of a cylinder of radius r and height h is given by the formula uppercase V equals pi r squared h. Find the rate of variation of volume with the radius when r equals 5.5 inches and h equals 20 inches. If r equal h, find the dimensions of the cylinder so that a change of 1 inch in radius causes a change of 400 cubic inches in the volume. The rate of variation uppercase V with regard to r is d uppercase V over dr equals 2 pi rh. If r equal 5.5 inches and h equal 20 inch, this becomes 690.8. It means that a change of radius of 1 inch will cause a change of volume of 690.8 cubic inch. This can be easily verified, for the volumes with r equal 5 and r equal 6 are 1,570 cubic inch and 2,260.8 cubic inch, respectively, and 2,260.8 minus 1,570 equals 690.8. Also, if r equal h, dV over dr equals 2 pi r squared equals 400, and r equals h equals the square root of 400 divided by 2 pi equals 7.98 inches. Number 5. The reading theta of Faraday's radiation parameter is related to the centigrade temperature T of the observed body by the relation theta over theta sub 1 equals the quantity T over T sub 1 to the 4th power, where theta sub 1 is the reading corresponding to a known temperature, T sub 1, of the observed body. Compare the sensitiveness of the parameter at temperatures 800 degrees centigrade, 1000 degrees centigrade, 1200 degrees centigrade, given that it read 25 when the temperature was 1000 degrees centigrade. The sensitiveness is the rate of variation of the reading with the temperature, that is, d theta over dt. The formula may be written theta equals theta sub 1 over t sub 1 to the fourth power times t to the fourth power equals 25t to the fourth power over 1000 to the fourth power. And we have d theta over dt equals 100t cubed over 1000 to the fourth power equals t cubed over 10 billion. When t equals 800, 1000, and 1200, we get d theta over dt equals 0.0512, 0.1, and 0.1728, respectively. The sensitiveness is approximately doubled from 800 degrees to 1000 degrees and becomes 3/4 as great again up to 1200 degrees. End of section 6.
Calculus Made Easy by Silvanus P. Thompson, Section 7. Exercises 2. Differentiate the following. Number 1. Y equals ax cubed plus 6. Answer. dy over dx equals 3ax squared. Number 2. Y equals 13x to the 3/2 power minus c. Answer. dy over dx equals 13 times 3/2 x to the 1/2 power. Number 3. Y equals 12x to the 1/2 power plus c to the 1/2 power. Answer. dy over dx equals 6x to the negative 1/2 power. Number 4. Y equals c to the 1/2 power times x to the 1/2 power. Answer. dy over dx equals 1/2 c to the 1/2 power times x to the negative 1/2 power. Number 5. U equals az to the nth power minus 1 over c. Answer. du over dz equals an over c times z to the n minus 1 power. Number 6. Y equals 1.18 t squared plus 22.4. Answer. dy over dt equals 2.36 t. Make up some other examples for yourself and try your hand at differentiating them. Number 7. If L sub t and L sub 0 be the lengths of a rod of iron at the temperatures of T degree centigrade and 0 degree centigrade, respectively, then L sub t equals L sub 0, left parentheses, 1 plus 0.000012 t, right parentheses. Find the change of length of the rod per degree centigrade. Answer. dl sub t over dt equals 0.0000 0.0012 times L sub 0. Number 8. It has been found that if C be the candle power of an incandescent electric lamp, and capital V be the voltage, C equals A capital V to the B power, where A and B are constants. Find the rate of change of the candle power with the voltage and calculate the change of candle power per volt at 80, 100, and 120 volts in the case of a lamp for which A equals 0.5 times 10 to the negative 10 power, and B equals 6. Answer: D uppercase C over D uppercase V equals AB uppercase V to the B minus 1 power, 0.98, 3.00, and 7.47 candle power per volt, respectively. Number 9. The frequency N of vibration of a string of diameter D, length L, and specific gravity sigma, stretched with the force T, is given by N equals 1 over D L times the square root of G T over pi sigma. Find the rate of change of the frequency when D, L, sigma, and T are varied singly. Answer: dN over d equals negative 1 over L D squared times the square root of G T over pi sigma. dN over d L equals negative 1 over D L squared times square root of G T over pi sigma. dN over d sigma equals negative 1 over 2 D L times the square root of G T over pi sigma cubed. dN over d T equals 1 over 2 D L times the square root of G over pi sigma T. Number 10. The greatest external pressure, P, which a tube can support without collapsing, is given by P equals, left parentheses, 2 E over 1 minus sigma squared, end parentheses, times T cubed over D cubed, where E and sigma are constants. T is the thickness of the tube, and D is its diameter. This formula assumes that 4T is small compared to D. Compare the rate at which P varies for a small change of thickness and for a small change of diameter taking place separately. Answer: rate of change of P when T varies over rate of change of P when D varies equals negative D over T. Number 11. Find, from first principles, the rate at which the following vary with respect to a change in radius. A. The circumference of a circle of radius r. B. The area of a circle of radius r. C. The lateral area of cone of slant dimension L. D. The volume of a cone of radius r and height h. E. The area of a sphere of radius r. F. The volume of a sphere of radius r. Answers: A. 2 pi. B. 2 pi r. C. Pi l. D. 2/3 pi r h. E. 8 pi r. F. 4 pi r squared. Number 12. The length L of an iron rod at the temperature T being given by L equals L sub T left bracket 1 plus 0.000012 left parentheses T minus T right parentheses right bracket, where L sub T is the length at the temperature T. Find the rate of variation of the diameter D of an iron tire suitable for being shrunk on a wheel when the temperature T varies. Answer: D over D T equals 0.000012 L sub T over pi. End of section 7. Differences, products, and quotients. We have learned how to differentiate simple algebraical functions such as x squared plus c or ax to the fourth power, and we have now to consider how to tackle the sum of two or more functions. For instance, let y equal the quantity x squared plus c plus the quantity ax to the fourth power plus b. What will its dy over dx be? How are we to go to work on this new job? The answer to this question is quite simple. Just differentiate them, one after the other, thus: dy over dx equal 2x plus 4ax cubed. If you have any doubt whether this is right, try a more general case, working it by first principles, and this is the way. Let y equal u plus v, where u is any function of x and v any other function of x. Then, letting x increase to x plus dx, y will increase to y plus dy, and u will increase to u plus du, and v to v plus dv. And we shall have y plus dy equals u plus du plus v plus dv. Subtracting the original y equal u plus v, we get dy equal du plus dv. And dividing through by dx, we get dy over dx equal du over dx plus dv over dx. This justifies the procedure. You differentiate each function separately and add the results. So if now we take the example of the preceding paragraph and put in the values of the two functions, we shall have, using the notation shown, page 16, dy over dx equal d times the quantity x squared plus c all over dx plus d times the quantity ax to the fourth power plus b all over dx equal 2x plus 4ax cubed, exactly as before. If there were three functions of x, which we may call u, v, and w, so that y equal u plus v plus w, Then dy over dx equal du over dx plus dv over dx plus dw over dx. As for subtraction, it follows at once, for if the function v had itself had a negative sign, its differential coefficient would also be negative, so that by differentiating y equal u minus v, we should get dy over dx equal du over dx minus dv over dx. But when we come to do with products, the thing is not quite so simple. Suppose we were asked to differentiate the expression y equal the quantity x squared plus c times the quantity ax to the fourth power plus b. What are we to do? The result will certainly not be 2x times 4ax cubed, for it is easy to see that neither c times ax to the fourth power nor x squared times b would have been taken into that product. Now, there are two ways in which we may go to work. First way, do the multiplying first, and, having worked it out, then differentiate. Accordingly, we multiply together x squared plus c and ax to the fourth power plus b. This gives ax to the sixth power plus acx to the fourth power plus bx squared plus bc. Now differentiate, and we get dy over dx equal 6ax to the fifth power plus 4acx cubed plus 2bx. Second way. Go back to first principles and consider the equation y equal u times v, where u is one function of x and v is another function of x. Then, if x grows to be x plus dx and y to y plus dy, and u becomes u plus du, and v becomes v plus dv, we shall have y plus dy equal the quantity u plus du times the quantity v plus dv, equal u times v plus u times dv plus v times du plus du times dv. Now, du times dv is a small quantity of the second order of smallness, and therefore in the limit may be discarded, leaving y plus dy equal u times v plus u times dv plus v times du. Then, subtracting the original y equal u times v, we have left dy equal u times dv plus v times du. And, dividing through by dx, we get the result dy over dx equal u times dv over dx plus v times du over dx. This shows that our instructions will be as follows. To differentiate the product of two functions, multiply each function by the differential coefficient of the other, and add together the two products so obtained. You should note that this process amounts to the following. Treat u as a constant while you differentiate v. Then treat v as a constant while you differentiate u. And the whole differential coefficient, dy over dx, will be the sum of these two treatments. Now, having found this rule, apply it to the concrete example which was considered above. We want to differentiate the product quantity x squared plus c times quantity ax to the fourth power plus b. Call quantity x squared plus c equal u and quantity ax to the fourth power plus b equal v. Then, by the general rule just established, we may write dy over dx equal quantity x squared plus c times d times the quantity ax to the fourth power plus b all over dx plus quantity ax to the fourth power plus b times d times the quantity x squared plus c all over dx equal quantity x squared plus c times 4ax cubed plus quantity ax to the fourth power plus b times 2x equal 4ax to the fifth power plus 4acx cubed plus 2ax to the fifth power plus 2bx. dy over dx equal 6ax to the fifth power plus 4acx cubed plus 2bx, exactly as before. Lastly, we have to differentiate quotients. Think of this example. Y equal bx to the fifth power plus c over x squared plus a. In such a case, it is no use to try to work out the division beforehand, because x squared plus a will not divide into bx to the fifth power plus c. Neither have they any common factor, so there is nothing for it but to go back to first principles and find a rule. So we will put y equal u over v, where u and v are two different functions of the independent variable x. Then, when x becomes x plus dx, y will become y plus dy, and u will become u plus du, and v will become v plus dv. So then, y plus dy equal u plus du over v plus dv. Now, perform the algebraic division thus. V plus dv divided into u plus du equals u over v plus du over v minus u times dv over v squared, by multiplying u over v by v plus dv and subtract the product u plus u times dv over v equals du minus u times dv over v. Subtract the product of v plus dv times du over v equals du plus du times dv over v equals negative u times dv over v minus du times dv over v. Subtract the product of v plus dv times u times dv over v squared equals negative u times dv over v minus u times dv over v squared equals negative du times dv over v plus u times dv over v squared. As both these remainders are small quantities of the second order, they may be neglected, and the division may stop here, since any further remainder would be of still smaller magnitudes. So we have got y plus dy equal u over v plus du over v minus u times dv over v squared, which may be written equals u over v plus v times du minus u times dv all over v squared. Now subtract the original y equals u over v, and we have left dy equal v times du minus u times dv all over v squared, whence dy over dx equal v times du over dx minus u times dv over dx all over v squared. This gives us our instructions as to how to differentiate a quotient of two functions. Multiply the divisor function by the differential coefficient of the dividend function, then multiply the dividend function by the differential coefficient of the divisor function, and subtract. Lastly, divide by the square of the divisor function. Going back to our example, y equal bx to the fifth power plus c over x squared plus a. Write bx to the fifth power plus c equal u, and x squared plus a equal v. Then dy over dx equal quantity x squared plus a times d times the quantity bx to the fifth power plus c all over dx minus the quantity bx to the fifth power plus c times d times the quantity x squared plus a all over dx all over the quantity squared x squared plus a equals the quantity x squared plus a times 5bx to the fourth power minus the quantity bx to the fifth power plus c times 2x all over the quantity squared x squared plus a. dy over dx equal 3bx to the sixth power plus 5abx to the fourth power minus 2cx all over the quantity squared x squared plus a. Answer. The working out of quotients is often tedious, but there's nothing difficult about it. Some further examples fully worked out are given hereafter. 1. Differentiate y equal a over b squared times x cubed minus a squared over b times x plus a squared over b squared. Being a constant, a squared over b squared vanishes and we have dy over dx equal a over b squared times 3 times x to the 3 minus 1 power minus a squared over b times 1 times x to the 1 minus 1 power. But x to the 1 minus 1 power equal x to the 0 power equal 1. So we get dy over dx equal 3a over b squared times x squared minus a squared over b. 2. Differentiate y equal 2a times the square root of bx cubed minus 3b times the cube root of a all over x minus 2 times the square root ab. Putting x in the index form, we get y equal 2a times the square root of b times x to the 3/2 power minus 3b times the cube root of a times x to the minus 1 power minus 2 times the square root of ab. Now, dy over dx equal 2a times the square root of b times 3/2 times x to the 3/2 minus 1 power minus 3b times the cube root of a times -1 times x to the -1 minus 1 power. Or dy over dx equal 3a times the square root of bx plus 3b times the cube root of a all over x squared. 3. Differentiate z equal 1.8 times the cube root of 1 over theta squared minus 4.4 over the fifth root of theta minus 27 degrees. This may be written z equal 1.8 times theta to the -2/3 power minus 4.4 theta to the -1/5 power minus 27 degrees. The 27 degrees vanishes and we have dz over d theta equal 1.8 times -2/3 times theta to the -2/3 minus 1 power minus 4.4 times -1/5 times theta to the -1/5 minus 1 power. Or dz over d theta equal -1.2 theta to the -5/3 power plus 0.88 theta to the -6/5 power. Or dz over d theta equal 0.88 over the fifth root of theta to the 6th power minus 1.2 over the cubed root of theta to the 5th power. 4. Differentiate v equal the quantity cubed 3t squared minus 1.2t plus 1. A direct way of doing this will be explained later. See page 66. But we can nevertheless manage it now without any difficulty. Developing the cube, we get v equal 27t to the 6th power minus 32.4t to the 5th power plus 39.96t to the 4th power minus 23.328t cubed minus 13.32t squared minus 3.6t plus 1. Hence, dv over dt equal 162t to the 5th power minus 162t to the 4th power plus 159.84t cubed minus 69.984t squared plus 26.64t minus 3.6. 5. Differentiate y equal quantity 2x minus 3 times the quantity squared x plus 1. dy over dx equal the quantity 2x minus 3 times d times the quantity of quantity x plus 1 times x plus 1 all over dx plus the quantity squared x plus 1 times d times the quantity 2x minus 3 all over dx equal the quantity 2x minus 3 times, open bracket, quantity x plus 1 times d times the quantity x plus 1 all over dx plus the quantity x plus 1 times d times the quantity x plus 1 all over dx, close bracket, plus the quantity squared x plus 1 times d times the quantity 2x minus 3 all over dx equal 2 times the quantity x plus 1 times the quantity 2x minus 3 plus quantity x plus 1 equals 2 times the quantity x plus 1 times the quantity 3x minus 2. Or, more simply, multiply out and then differentiate. 6. Differentiate y equal 0.5 x cubed times the quantity x minus 3. dy over dx equal 0.5 times the quantity x cubed times d times the quantity x minus 3 all over dx plus the quantity x minus 3 times d times x cubed all over dx equal 0.5 times the quantity x cubed plus quantity x minus 3 times 3x squared equal 2x cubed minus 4.5x squared. Same remarks as for preceding example. 7. Differentiate w equal the quantity theta plus 1 over theta times the quantity square root of theta plus 1 over the square root of theta. This may be written w equal the quantity theta plus theta to the negative 1 power times the quantity theta to the 1/2 power plus theta to the negative 1/2 power. dw over d theta equal quantity theta plus theta to the negative 1 power times d times the quantity theta to the 1/2 power plus theta to the negative 1/2 power all over d theta plus quantity theta to the 1/2 power plus theta to the negative 1/2 power times d times quantity theta plus theta to the negative 1 power all over d theta equal quantity theta plus theta to the negative 1 power times quantity 1/2 theta to the negative 1/2 power minus 1/2 theta to the negative 3/2 power plus the quantity theta to the 1/2 power plus theta to the negative 1/2 power times 1 minus theta to the negative 2 power equal 1/2 times the quantity theta to the 1/2 power plus theta to the negative 3/2 power minus theta to the negative 1/2 power minus theta to the negative 5/2 power, plus the quantity theta to the 1/2 power plus theta to the negative 1/2 power minus theta to the negative 3/2 power minus theta to the negative 5/2 power equal 3/2 times the quantity square root of theta minus 1 over the square root of theta to the 5th power plus 1/2 times the quantity 1 over the square root of theta minus 1 over the square root of theta cubed. This, again, could be obtained more simply by multiplying the two factors first and differentiating afterwards. This is not, however, always possible. See, for instance, page 170, example 8, in which the rule for differentiating a product must be used. 8. Differentiate y equal a over 1 plus a times the square root of x plus a squared x. dy over dx equal the quantity 1 plus ax to the 1/2 power plus a squared times x times 0 minus a times d times the quantity 1 plus ax to the 1/2 power plus a squared x all over dx all over quantity squared 1 plus a times the square root of x plus a squared x equal negative a times the quantity 1/2 ax to the negative 1/2 plus a squared all over the quantity squared 1 plus ax to the 1/2 power plus a squared x. 9. Differentiate y equal x squared over x squared plus 1. dy over dx equal the quantity x squared plus 1 times 2x minus x squared times 2x all over the quantity squared x squared plus 1 equal 2x over the quantity squared x squared plus 1. 10. Differentiate y equal a plus the square root of x all over a minus the square root of x. In the index form, y equal a plus x to the 1/2 power all over a minus x to the 1/2 power dy over dx equal the quantity a minus x to the 1/2 power times the quantity 1/2 x to the negative 1/2 power minus the quantity a plus x to the 1/2 power times the quantity negative 1/2 x to the negative 1/2 power all over the quantity squared a minus x to the 1/2 power equal a minus x to the 1/2 power plus a plus x to the 1/2 power all over 2 times the quantity squared a minus x to the 1/2 power times x to the 1/2 power. Hence, dy over dx equal a over the quantity squared a minus the square root of x times the square root of x. 11. Differentiate. Theta equals 1 minus a times the cubed root of t squared all over 1 plus a times the square root of t cubed. Now, theta equals 1 minus at to the 2/3 power all over 1 plus at to the 3/2 power. d theta over dt equal the quantity 1 plus at to the 3/2 power times the quantity negative 2/3 at to the negative 1/3 power minus the quantity 1 minus at to the 2/3 power times 3/2 at to the 1/2 power all over the quantity squared 1 plus at to the 3/2 power equal 5a squared times the 6th root of t to the 7th power minus 4a over the cubed root of t minus 9a times the square root of t all over 6 times the quantity squared 1 plus a times the square root of t cubed. 12. A reservoir of square cross-section has sides sloping at an angle of 45 degrees with the vertical. The side of the bottom is 200 feet. Find an expression for the quantity pouring in or out when the depth of water varies by 1 foot. Hence find, in gallons, the quantity withdrawn hourly when the depth is reduced from 14 to 10 feet in 24 hours. The volume of a frustum of pyramid of height H and of bases A and a is V equals H over 3 times the quantity A plus a plus the square root of A times a. It is easily seen that the slope being 45 degrees, if the depth be h, the length of the side of the square surface of the water is 200 plus 2 h feet, so that the volume of water is h over 3 times the quantity 200 squared plus the quantity squared 200 plus 2 h plus 200 times the quantity 200 plus 2 times h equals 40,000 h plus 400 h squared plus 4h cubed over 3. D V over D h equal 40,000 plus 800h plus 4h squared equal cubic feet per foot of depth variation. The mean level from 14 to 10 feet is 12 feet. When h equals 12, d times V over d over h equals 50,176 cubic feet. Gallons per hour corresponding to a change of depth of 4 feet in 24 hours equals 4 times 50,176 times 6.25 all over 24 equal 52,267 gallons. 13. The absolute pressure in atmospheres P of saturated steam at the temperature T degrees centigrade is given by Dulong as being P equals the quantity to the fifth power 40 plus T over 140, as long as T is above 80 degrees. Find the rate of variation of the pressure with the temperature at 100 degrees centigrade. Expand the numerator by the binomial theorem, see page 137. P equals 1 over 140 to the fifth power times the quantity 40 to the fifth power plus 5 times 40 to the fourth power T plus 10 times 40 cubed times T squared plus 10 times 40 squared T cubed plus 5 times 40 T to the fourth power plus T to the fifth power. Hence, D P over dt equals 1 over 537,824 times 10 to the fifth power times the quantity 5 times 40 to the fourth power plus 20 times 40 cubed T plus 30 times 40 squared T squared plus 20 times 40 T cubed plus 5 T to the fourth power. When T equals 100, this becomes 0.036 atmosphere per degree centigrade change of temperature. End of section 8.
Calculus Made Easy by Silvanus P. Thompson, Section 9. Exercises 3. Exercise 1. Differentiate. Question A. U equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... Answer. 1 plus x squared over 2 plus x cubed over 6 plus x4 over 24 plus dot dot dot. Question B. Y equals ax squared plus bx plus c. Answer: 2ax plus b. Question C. Y equals x plus a quantity squared. Answer: 2x plus 2a. Question D. Y equals x plus a quantity cubed. Answer: 3x squared plus 6ax plus 3a squared. Question 2. If w equals at plus 1/2 bt squared, find dw by dt. Answer: dw by dt equals a minus bt. Question 3. Find the differential coefficient of y equals the quantity x plus the square root of minus 1 multiplied by the quantity x minus the square root of minus 1. Answer: dy by dx equals 2x. Question 4. Differentiate. Y equals open bracket 197x minus 34x squared close bracket multiplied by open bracket 7 plus 22x minus 83x cubed close bracket. Answer: 14,110 x to the fourth minus 65,404 x cubed minus 2,244 x squared plus 8,192x plus 1,379. Question 5. If x equals open bracket y plus 3 close bracket multiplied by open bracket y plus 5 close bracket, find dx by dy. Answer: dx by dy equals 2y plus 8. Question 6. Differentiate. Y equals 1.3709x multiplied by open bracket 112.6 plus 45.202x squared close bracket. Answer: 185.9022654x squared plus 154.36334. Question 7. Find the differential coefficients of y equals the quantity 2x plus 3 divided by the quantity 3x plus 2. Answer: -5 divided by open bracket 3x plus 2 close bracket all squared. Question 8. Find the differential coefficients of y equals the quantity 1 plus x plus 2x squared plus 3x cubed divided by the quantity 1 plus x plus 2x squared. Answer: the quantity 6x to the fourth plus 6x cubed plus 9x squared all divided by open bracket 1 plus x plus 2x squared close bracket all squared. Question 9. Find the differential coefficients of y equals the quantity ax plus b divided by the quantity cx plus d. Answer: the quantity ad minus bc divided by open bracket cx plus d close bracket all squared. Question 10. Y equals the quantity x to the power n plus a divided by the quantity x to the power of minus n plus b. Answer: anx to the power of negative n minus 1 plus bnx to the power of n minus 1 plus 2nx to the power of minus 1 all divided by open bracket x to the power of minus n plus b close bracket, all squared. Question 11. The temperature T of the filament of an incandescent electric lamp is connected to the current passing through the lamp by the relation C equals A plus BT plus CT squared. Find an expression giving the variation of the current corresponding to a variation of temperature. Answer: B plus 2CT. Question 12. The following formulae have been proposed to express the relation between the electric resistance R of a wire at the temperature T degrees Celsius and the resistance R naught of the same wire at 0 degrees centigrade, A, B, C being constants. R equals R naught times open bracket 1 plus AT plus BT squared close bracket. R equals R naught times open bracket 1 plus AT plus B times the square root of T close bracket. R equals R naught times open bracket 1 plus AT plus BT squared close bracket raised to the power minus 1. Find the rate of variation of the resistance with regard to temperature as given by each of these formulae. Answer: R naught times open bracket A plus 2BT close bracket. R naught times open bracket A plus B divided by 2 root T close bracket. Negative R naught times open bracket A plus 2BT close bracket divided by open bracket 1 plus AT plus BT squared close bracket squared. Or R squared times open bracket A plus 2BT close bracket divided by R naught. Question 13. The electromotive force E of a certain type of standard cell has been found to vary with the temperature T according to the relation E equals 1.4340 times open bracket 1 minus 0.000814 times open bracket T minus 15 close bracket plus 0.000007 times open bracket T minus 15 close bracket squared closed bracket volts. Find the change of electromotive force per degree at 15 degrees, 20 degrees, and 25 degrees. Answer: 1.4340 multiplied by open bracket 0.000014 T minus 0.001024 close bracket. Negative 0.00117, negative 0.00107, and finally negative 0.00097. Question 14. The electromotive force necessary to maintain an electric arc of length L with a current of intensity I has been found by Mrs. Ayrton to be E equals A plus BL plus the quantity C plus KL all divided by I, where A, K, B, and C are constants. Find an expression for the variation of the electromotive force A with regard to the length of the arc and B with regard to the strength of the current. Answers: dE by dL equals B plus K over I, and dE by dI equals negative C minus KL all divided by I squared. End of section 9. pjk.scripts.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson, Section 10. Chapter 7. Successive Differentiation. Let us try the effect of repeating several times over the operation of differentiating a function. Begin with a concrete case. Let y equal x to the power 5. First differentiation, 5x to the power 4. Second differentiation, 5 times 4 times x to the power 3. That's equal to 20x cubed. Third differentiation, 5 times 4 times 3 times x squared, which is equal to 60x squared. Fourth differentiation, 5 times 4 times 3 times 2 times x, which is 120x. Fifth differentiation, 5 times 4 times 3 times 2 times 1 equals 120. Sixth differentiation, 0. There is a certain notation with which we already are acquainted, used by some writers that is very convenient. This is to employ the general symbol f of x for any function of x. Here the symbol f followed by a pair of brackets is read as function of without saying what particular function is meant. So the statement y equals f of x merely tells us that y is a function of x. It may be x squared or ax to the n or cosine of x or any other complicated function of x. The corresponding symbol for the differential coefficient is f primed of x, which is simpler to write than dy by dx. This is called the derived function of x. Suppose we differentiate over again. We shall get the second derived function or second differential coefficient, which is denoted by f double prime of x, and so on. Now let's generalize. Let y equal f of x equal x to the power n. First differentiation, f primed of x equals n times x to the power n minus 1. Second differentiation, f double primed of x equals n times n minus 1 times x to the power n minus 2. Third differentiation, f triple prime of x equals n times n minus 1 times n minus 2 times x to the power n minus 3. Fourth differentiation, f quadruple prime of x equals n times n minus 1 times n minus 2 times n minus 3 times x to the power n minus 4, etc., etc. But this is not the only way of indicating successive differentiations. For if the original function be y equals f of x, once differentiating gives dy by dx equals f primed of x. Twice differentiating gives d by dy by dx equals f double primed of x. And this is more conveniently written as d squared y by dx quantity squared, or more usually as d squared y by dx squared. Similarly, we may write as the result of thrice differentiating d cubed y by dx cubed, or f triple primed of x. Examples. Now let us try y equals f of x equals 7x to the power 4 plus 3.5x to the power 3 minus 1 half x squared plus x minus 2. dy by dx, that's f primed of x, which is 28x cubed plus 10.5 x squared minus x plus 1. d squared y by dx squared equals f double primed of x equals 84x squared plus 21x minus 1. d cubed y by dx cubed equals the third derivative of x, which is equal to 168x plus 21. d to the fourth power y plus dx to the power 4 is the fourth derivative of x, which is equal to 168. And finally, d to the fifth y by dx to the fifth is the fifth derivative, which is 0. In a similar manner, if y equals phi of x equals 3x times the quantity x squared minus 4, then phi prime of x equals dy by dx equals 3 times the quantity x times 2x plus the quantity x squared minus 4 times 1, which equals 3 times the quantity 3x squared minus 4. Phi double primed of x is equal to d squared y by dx squared, which is equal to 3 times 6x, which is equal to 18x. Phi triple prime of x, which is equal to d cubed y by dx cubed, is equal to 18. And the fourth derivative, phi quadruple prime of x, is equal to d to the fourth y by dx fourth, which is 0. End of section 10.
Calculus Made Easy by Silvanus P. Thompson. Section 11. Exercises 4. Find dy over dx and d squared y all over dx squared for the following expressions. 1. Y equal 17x plus 12x squared. Answer. 17 plus 24x, and 24. 2. Y equal x squared plus a over x plus a. Answer: x squared plus 2ax minus a all over the quantity squared x plus a, and 2a times the quantity a plus 1 all over the quantity cubed x plus a. 3. Y equal 1 plus x over 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3 plus x to the 4th power over 1 times 2 times 3 times 4. Answer: 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3, and 1 plus x squared over 1 times 2. 4. Find the second and third derived functions in the exercises 3, number 1 to number 7, and in the examples given, number 1 to number 7. Answers: Exercises 3. 1. A. D squared y over dx squared equals d cubed y over dx cubed equals 1 plus x plus 1/2 x squared plus 1/6 x cubed plus ellipsis. B. 2a and 0. C. 2 and 0. D. 6x plus 6a and 6. 2. Negative b and 0. 3. 2 and 0. 4. 56,440 x cubed minus 196,212 x squared minus 4,488x plus 8,192. 169,320 x squared minus 392,424 x minus 4,488. 5. 2, 0. 6. 371.80453x 371.80453. 7. 30 over the quantity cubed 3x plus 2 negative 270 over the quantity to the 4th power 3x plus 2. Examples, page 40. 1. 6a over b squared x 6a over b squared. 2. 3a square root of b over 2 square root of x minus 6b cubed root of a all over x cubed. 18b times the cubed root of a over x to the 4th power minus 3a times the square root of b all over 4 times the square root of x cubed. 3. 2 over the cubed root of theta to the 8th power minus 1.056 over the 5th root of theta to the 11th power, 2.3232 over the 5th root of theta to the 16th power minus 16 over 3 times the cube root of theta to the 11th power. 4. 810t to the 4th power minus 648t cubed plus 479.52t squared minus 139.968t plus 26.64. 3,240t cubed minus 1,944t squared plus 959.04t minus 139.968. 5. 12x plus 2, 12. 6. 6x squared minus 9x, 12x minus 9. 7. 3/4 times the quantity 1 over the square root of theta plus 1 over the square root of theta to the 5th power plus 1/4 times the quantity 15 over the square root of theta to the 7th power minus 1 over the square root of theta to the 3rd power. 3/8 times the quantity 1 over the square root of theta to the 5th power minus 1 over the square root of theta to the 3rd power minus 15 over 8 times the quantity 7 over the square root of theta to the 9th power plus 1 over the square root of theta to the 7th power. End of section 11.
Some of the most important problems of the calculus are those where time is the independent variable, and we have to think about the values of some other quantity that varies when the time varies. Some things grow larger as time goes on. Some other things grow smaller. The distance that a train has got from its starting place goes on ever increasing as time goes on. Trees grow taller as the years go by. Which is growing at the greater rate? A plant 12 inches high, which in 1 month becomes 14 inches high, or a tree 12 feet high, which in a year becomes 14 feet high. In this chapter, we are going to make much use of the word rate. Nothing to do with pour rate or water rate, except that even here the word suggests a proportion, a ratio, so many pence in the pound. Nothing to do even with birth rate or death rate, though these words suggest so many births or deaths per thousand of the population. When a motor car whizzes by us, we say, "What a terrific rate!" When a spendthrift is flinging about his money, we remark that that young man is living at a prodigious rate. What do we mean by rate? In both these cases, we are making a mental comparison of something that is happening and the length of time that it takes to happen. If the motor car flies past us, going 10 yards per second, a simple bit of mental arithmetic will show us that this is the equivalent, while it lasts, to a rate of 600 yards per minute, or over 20 miles per hour. Now, in what sense is it true that a speed of 10 yards per second is the same as 600 yards per minute? 10 yards is not the same as 600 yards, nor is 1 second the same thing as 1 minute. What we mean by saying that the rate is the same is this: that the proportion borne between distance passed over and time taken to pass over it is the same in both cases. Take another example. A man may have only a few pounds in his possession, and yet be able to spend money at the rate of millions a year, provided he goes on spending money at that rate for a few minutes only. Suppose you hand a shilling over the counter to pay for some goods, and suppose the operation lasts exactly 1 second. Then, during that brief operation, you are parting with your money at the rate of 1 shilling per second, which is the same rate as 3 pounds per minute, or 180 pounds per hour, or 4,320 pounds per day, or 1,576,800 pounds per year. If you have 10 pounds in your pocket, you can go on spending money at the rate of 1 million a year for just 5 1/4 minutes. It is said that Sandy had not been in London above 5 minutes when bang went saxpence. If he were to spend money at that rate all day long, say for 12 hours, he would be spending 6 shillings an hour, or £3 12 shillings per day, or £21 12 shillings a week, not counting the Sabbath. Now try to put some of these ideas into differential notation. Let y in this case stand for money, and let t stand for time. If you are spending money, and the amount you spend in a short time dt be called dy, the rate of spending it will be dy over dt, or rather should be written with a minus sign as negative dy over dt, because dy is a decrement, not an increment. But money is not a good example for the calculus, because it generally comes and goes by jumps, not by a continuous flow. You may earn £200 a year, but it does not keep running in all day long in a thin stream. It comes in only weekly, or monthly, or quarterly in lumps, and your expenditure also goes out in sudden payments. A more apt illustration of the idea of a rate is furnished by the speed of a moving body. From London, Euston Station, to Liverpool is 200 miles. If a train leaves London at 7 o'clock and reaches Liverpool at 11 o'clock, you know that, since it has traveled 200 miles in 4 hours, its average rate must have been 50 miles per hour, because 200 divided by 4 equals 50 divided by 1. Here you are really making a mental comparison between the distance passed over and the time taken to pass over it. You are dividing one by the other. If y is the whole distance and t the whole time, clearly the average rate is y over t. Now the speed was not actually constant all the way. At starting and during the slowing up at the end of the journey, the speed was less. Probably at some part, when running downhill, the speed was over 60 miles an hour. If during any particular element of time, dt, the corresponding element of distance passed over was dy, then at that part of the journey the speed was dy over dt. The rate at which one quantity, in the present instance distance, is changing in relation to the other quantity, in this case time, is properly expressed, then, by stating the differential coefficient of one with respect to the other. A velocity, scientifically expressed, is the rate at which a very small distance in any given direction is being passed over, and may therefore be written v equals dy over dt. But if the velocity v is not uniform, then it must be either increasing or else decreasing. The rate at which a velocity is increasing is called the acceleration. If a moving body is, at any particular instant, gaining an additional velocity dv in an element of time dt, then the acceleration a, at that instant, may be written a equals dv over dt. But dv is itself d times dy over dt. Hence, we may put a equals d times dy over dt all over dt. And this is usually written a equals d squared y over dt squared, or the acceleration is the second differential coefficient of the distance with respect to time. Acceleration is expressed as a change of velocity in unit time. For instance, as being so many feet per second per second. The notation used being feet divided by seconds squared. When a railway train has just begun to move, its velocity v is small, but it is rapidly gaining speed. It is being hurried up or accelerated by the effort of the engine, so its d squared y over dt squared is large. When it has got up its top speed, it is no longer being accelerated, so that then d squared y over dt squared has fallen to 0. But when it nears its stopping place, its speed begins to slow down, may indeed slow down very quickly if the brakes are put on, and during this period of deceleration or slackening of pace, the value of dv over dt, that is, of d squared y over dt squared, will be negative. To accelerate a mass m requires the continuous application of force. The force necessary to accelerate a mass is proportional to the mass, and it is also proportional to the acceleration which is being imparted. Hence, we may write for the force F the expression F equals ma, or F equals m times dv over dt, or F equals m times d squared y over dt squared. The product of a mass by the speed at which it is going is called its momentum, and is in symbols mv. If we differentiate momentum with respect to time, we shall get d times mv all over dt for the rate of change of momentum. But since m is a constant quantity, this may be written m times dv over dt, which we see above is the same as F. That is to say, force may be expressed either as mass times acceleration, or as rate of change of momentum. Again, if a force is employed to move something against an equal and opposite counterforce, it does work, and the amount of work done is measured by the product of the force into the distance, in its own direction, through which its point of application moves forward. So if a force F moves forward through a length y, the work done, which we may call W, will be W equals F times y, where we take F as a constant force. If the force varies at different parts of the range y, then we must find an expression for its value from point to point. If F be the force along the small element of length dy, the amount of work done will be F times dy. But as dy is only an element of length, only an element of work will be done. If we write W for work, then an element of work will be dW, and we have dW equals F times dy, which may be written dW equals ma times dy, or dW equals m times d squared y over dt squared times dy, or dW equals m times dv over dt times dy. Further, we may transpose the expression and write dW over dy equals F. This gives us yet a third definition of force, that if it is being used to produce a displacement in any direction, the force in that direction is equal to the rate at which work is being done per unit of length in that direction. In this last sentence, the word rate is clearly not used in its time sense, but in its meaning as ratio or proportion. Sir Isaac Newton, who was, along with Leibniz, an inventor of the methods of the calculus, regarded all quantities that were varying as flowing, and the ratio which we nowadays call the differential coefficient he regarded as the rate of flowing, or the fluxion of the quantity in question. He did not use the notation of the dy and dx and dt. This was due to Leibniz, but had instead a notation of his own. If y was a quantity that varied, or flowed, then his symbol for its rate of variation, or fluxion, was y dot. If x was the variable, then its fluxion was called x dot. The dot over the letter indicated that it had been differentiated, but this notation does not tell us what is the independent variable with respect to which the differentiation has been effected. When we see dy over dt, we know that y is to be differentiated with respect to t. If we see dy over dx, we know that y is to be differentiated with respect to x. But if we see merely y dot, we cannot tell without looking at the context whether this is to mean dy over dx, or dy over dt, or dy over dz, or what is the other variable. So therefore, this fluxional notation is less informing than the differential notation, and has in consequence largely dropped out of use. But its simplicity gives it an advantage, if only we will agree to use it for those cases exclusively where time is the independent variable. In that case, y dot will mean dy over dt, and u dot will mean du over dt, and x double dot will mean d squared x over dt squared. Adopting this fluxional notation, we may write the mechanical equations considered in the paragraphs above as follows. Distance, x. Velocity, v equals x dot. Acceleration, a equals v dot equals x double dot. Force, F equals mv dot equals mx double dot. Work, W equals x times mx double dot. End of section 12. Recording by Jarganiel. Examples. Example 1. A body moves so that the distance x in feet, which it travels from a certain point O, is given by the relation x equals 0.2 t squared plus 10.4, where t is the time in seconds elapsed since a certain instant. Find the velocity and acceleration 5 seconds after the body began to move, and also find the corresponding values when the distance covered is 100 feet. Find also the average velocity during the first 10 seconds of its motion. Suppose distances and motion to the right to be positive. Now, x equals 0.2 t squared plus 10.4. v equals x dot equals dx over dt, which equals 0.4 t. And a equals x double dot equals d squared x over dt squared, which equals 0.4, which equals constant. When t equals 0, x equals 10.4, and v equals 0. The body started from a point 10.4 feet to the right of the point O, and the time was reckoned from the instant the body started. When t equals 5, v equals 0.4 times 5, which equals 2 feet per second. A equals 0.4 feet per second squared. When x equals 100, 100 is equal to 0.2 t squared plus 10.4, or t squared equals 448, and t equals 21.17 seconds. V equals 0.4 times 21.17, which equals 8.468 feet per second. When t equals 10, distance traveled equals 0.2 times 10 squared plus 10.4 minus 10.4, which equals 20 feet. Average velocity equals 20 over 10, which equals 2 feet per second. It is the same velocity as the velocity at the middle of the interval, negative 0.85 feet. That is 0.85 feet to the left of the point O. Now, when t equals 2.5, x equals 0.2 times 2.5 squared plus 3 times 2.5 plus 10.4, which equals 19.15. So in 10 seconds, the distance traveled was 19.15 plus 0.85, which equals 20 feet. and the average velocity equals 20 over 10, which equals 2 feet per second. Example 3. Consider a similar problem when the distance is given by x equals 0.2t squared minus 3t plus 10.4. Then v equals 0.4t minus 3. A equals 0.4, which equals constant. When t equals 0, x equals 10.4, as before, and v equals negative 3, so that the body was moving in the direction opposite to its motion in the previous cases. As the acceleration is positive, however, we see that this velocity will decrease as time goes on, until it becomes 0, when v equals 0, or 0.4t minus 3 equals 0, or t equals 7.5 seconds. After this, the velocity becomes positive, and 5 seconds after the body started, t equals 12.5, and v equals 0.4 times 12.5 minus 3, which equals 2 feet per second. When x equals 100, 100 equals 0.2t squared minus 3t plus 10.4, or t squared minus 15t minus 448, which equals 0, and t equals 29.95, v equals 0.4 times 29.95 minus 3, which equals 8.98 feet per second. When v is 0, x equals 0.2 times 7.5 squared minus 3 times 7.5 plus 10.4, which equals negative 0.85, informing us that the body moves back to 0.85 feet beyond the point O before it stops. 10 seconds later, t equals 17.5 and x equals 0.2 times 17.5 squared minus 3 times 17.5 plus 10.4, which equals 19.15. The distance traveled is equal to 0.85 plus 19.15, which equals 20.0. And the average velocity is again 2 feet per second. Example 4. Consider yet another problem of the same sort with x equals 0.2t cubed minus 3t squared plus 10.4. v equals 0.6t squared minus 6t. A equals 1.2t minus 6. The acceleration is no more constant. When t equals 0, x equals 10.4, v equals 0, a equals negative 6. The body is at rest, but just ready to move with a negative acceleration. That is, to gain a velocity towards the point O. Example 5. If we have x equals 0.2t cubed minus 3t plus 10.4, then v equals 0.6t squared minus 3, and a equals 1.2t. When t equals 0, x equals 10.4, v equals negative 3, a equals 0. The body is moving towards the point O with a velocity of 3 feet per second, and just at that instant the velocity is uniform. We see that the conditions of the motion can always be at once ascertained from the time-distance equation and its first and second derived functions. In the last two cases, the mean velocity during the first 10 seconds and the velocity 5 seconds after the start will no more be the same, because the velocity is not increasing uniformly, the acceleration being no longer constant. Example 6. The angle theta in radians turned through by a wheel is given by theta equals 3 plus 2t minus 0.1 t cubed, where t is the time in seconds from a certain instant. Find the angular velocity, omega, and the angular acceleration, alpha, A, after 1 second, B, after it has performed 1 revolution. At what time is it at rest, and how many revolutions has it performed up to that instant? Writing for the acceleration, omega equals theta dot equals d theta over dt, which equals 2 minus 0.3 t squared. Alpha equals theta double dot equals d squared theta over dt squared, which equals negative 0.6 t. When t equals 0, theta equals 3, omega equals 2 radians per second, alpha equals 0. When t equals 1, omega equals 2 minus 0.3, which equals 1.7 radians per second. Alpha equals negative 0.6 radians per second squared. This is a retardation. The wheel is slowing down. After 1 revolution, theta equals 2 pi, which equals 6.28. 6.28 equals 3 plus 2t minus 0.1 t cubed. By plotting the graph, theta equals 3 plus 2t minus 0.1 t cubed, we can get the value or values of t for which theta equals 6.28. These are 2.11 and 3.03. There is a third negative value. When t equals 2.11, theta equals 6.28. Omega equals 2 minus 1.34, which equals 0.66 radians per second. Alpha equals negative 1.27 radians per second squared. When t equals 3.03, theta equals 6.28, omega equals 2 minus 2.754, which equals negative 0.754 radians per second. Alpha equals negative 1.82 radians per second squared. The velocity is reversed. The wheel is evidently at rest between these two instants. It is at rest when omega equals 0, that is when 0 equals 2 minus 0.3 t cubed, or when t equals 2.58 seconds. It has performed theta divided by 2 pi equals 3 plus 2 times 2.58 minus 0.1 times 2.58 cubed, all over 6.28, which equals 1.025 revolutions. End of section 13. Recording by Jarganiel.
Calculus Made Easy by Silvanus P. Thompson. Section 14. Exercises 5. 1. If y equals a plus bt squared plus ct to the fourth, find dy over dt and d2y over dt squared. Answer: dy over dt equals 2bt plus 4ct cubed. d2y over dt squared equals 2b plus 12ct squared. 2. A body falling freely in space describes in t seconds a space s in feet expressed by the equation s equals 16t squared. Draw a curve showing the relation between s and t. Also determine the velocity of the body at the following times from its being let drop. T equals 2 seconds, t equals 4.6 seconds, t equals 0.01 second. Answer: 64, 147.2, and 0.32 feet per second. 3. If x equals at minus 1/2 gt squared, find x dot and x double dot. Answer: x equals a minus gt. X double dot equals minus g. 4. If a body moves according to the law, s equals 12 minus 4.5t plus 6.2 t squared, find its velocity when t equals 4 seconds, s being in feet. Answer: 45.1 feet per second. 5. Find the acceleration of the body mentioned in the preceding example. Is the acceleration the same for all values of t? Answer: 12.4 feet per second per second. Yes. 6. The angle theta in radians, turned through by a revolving wheel, is connected with the time t in seconds that has elapsed since starting by the law theta equals 2.1 minus 3.2t plus 4.8 t squared. Find the angular velocity in radians per second of that wheel when 1 1/2 seconds have elapsed. Find also its angular acceleration. Answers: angular velocity equals 11.2 radians per second. Angular acceleration equals 9.6 radians per second per second. 7. A slider moves so that, during the first part of its motion, its distance s in inches from its starting point is given by the expression s equals 6.8 t cubed minus 10.8 t, t being in seconds. Find the expression for the velocity and the acceleration at any time, and hence find the velocity and the acceleration after 3 seconds. Answer: v equals 20.4 t squared minus 10.8. A equals 40.8 t, 172.8 inches per second, 122.4 inches per second squared. 8. The motion of a rising balloon is such that its height, h in miles, is given at any instant by the expression h equals 0.5 plus 1/10 times the cube root of t minus 125, t being in seconds. Find an expression for the velocity and the acceleration at any time. Draw curves to show the variation of height, velocity, and acceleration during the first 10 minutes of the ascent. Answers: v equals 1 over 30 times the cube root of open parenthesis t minus 125 close parenthesis squared. A equals minus 1 over 45 times the cube root of open parenthesis t minus 125 close parenthesis to the fifth. 9. A stone is thrown downwards into water, and its depth p in meters at any instant t seconds after reaching the surface of the water is given by the expression p equals 4 over 4 plus t squared, all plus 0.8 t minus 1. Find an expression for the velocity and the acceleration at any time. Find the velocity and acceleration after 10 seconds. Answers: v equals 0.8 minus 8t over open parenthesis 4 plus t squared close parenthesis squared. A equals 24t squared minus 32 all over open parenthesis 4 plus t squared close parenthesis cubed. 0.7926 and 0.00211. 10. A body moves in such a way that the spaces described in the time t from starting is given by s equals t to the nth, where n is a constant. Find the value of n when the velocity is doubled from the 5th to the 10th second. Find it also when the velocity is numerically equal to the acceleration at the end of the 10th second. Answer: n equals 2, n equals 11. End of section 14. By Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 9. Introducing a useful dodge. Sometimes one is stumped by finding that the expression to be differentiated is too complicated to tackle directly. Thus the equation y equals open parenthesis x squared plus a squared close parenthesis to the 3/2 power is awkward to a beginner. Now the dodge to turn the difficulty is this. Write some symbol, such as u, for the expression x squared plus a squared. Then the equation becomes y equals u to the 3/2 power, which you can easily manage, for dy over du equals 3/2 times u to the 1/2 power. Then tackle the expression u equals x squared plus a squared, and differentiate it with respect to x. Du over dx equals 2x. Then all that remains is plain sailing, for dy over dx equals dy over du times du over dx. That is, dy over dx equals 3/2 times u to the 1/2 power, all times 2x, equals 3/2 open parenthesis x squared plus a squared close parenthesis to the 1/2 power, all times 2x, equals 3x open parenthesis x squared plus a squared close parenthesis to the 1/2 power. And so the trick is done. By and by, when you have learned how to deal with sines and cosines and exponentials, you will find this dodge of increasing usefulness. Examples. Let us practice this dodge on a few examples. 1. Differentiate y equals the square root of the quantity a plus x. Let a plus x equal u. Du over dx equals 1. Y equals u to the 1/2 power. Dy over du equals 1/2 times u to the minus 1/2 power, equals 1/2 open parenthesis a plus x close parenthesis to the minus 1/2 power. Dy over dx equals dy over du times du over dx equals 1 over 2 times the square root of a plus x. 2. Differentiate y equals 1 over the square root of a plus x squared. Let a plus x squared equal u. Du over dx equals 2x. Y equals u to the minus 1/2 power. Dy over du equals minus 1/2 times u to the minus 3/2 power. Dy over dx equals dy over du times du over dx equals minus x over the square root of open parenthesis a plus x squared close parenthesis cubed. 3. Differentiate y equals open parenthesis m minus nx to the 2/3 power plus the quantity p over x to the 4/3 power close parenthesis to the power a. Let m minus nx to the 2/3 power plus px to the minus 4/3 power equal u. Du over dx equals minus 2/3 nx to the minus 1/3 power minus 4/3 px to the minus 7/3 power. Y equals u to the a power. Dy over du equals a u to the a minus 1 power. Dy over dx equals dy over du times du over dx equals minus a open parenthesis m minus nx to the 2/3 power plus p over x to the 4/3 power close parenthesis to the a minus 1 power open parenthesis 2/3 nx to the minus 1/3 power plus 4/3 px to the minus 7/3 power close parenthesis. 4. Differentiate y equals 1 over the square root of x cubed minus a squared. Let u equal x cubed minus a squared. Du over dx equals 3x squared. Y equals u to the minus 1/2. dy over du equals minus 1/2, open parenthesis, x cubed minus a squared, close parenthesis, to the minus 3 over 2. dy over dx equals dy over du times du over dx equals minus 3x squared all over 2 times the square root of, open parenthesis, x cubed minus a squared, close parenthesis, cubed. 5. Differentiate y equals the square root of the quantity 1 minus x over 1 plus x. End quantity. Write this as y equals, open parenthesis, 1 minus x, close parenthesis, to the 1/2, all over, open parenthesis, 1 plus x, close parenthesis, to the 1/2. dy over dx equals numerator, open parenthesis, 1 plus x, close parenthesis, to the 1/2, times the quantity, numerator, d, open parenthesis, 1 minus x, close parenthesis, to the 1/2, end numerator, over dx, end quantity, minus, open parenthesis, 1 minus x, close parenthesis, to the 1/2, times the quantity, numerator, d, open parenthesis, 1 plus x, close parenthesis, to the 1/2, end numerator, over dx, end quantity, end numerator, over denominator, 1 plus x, end denominator. We may also write y equals, open parenthesis, 1 minus x, close parenthesis, to the 1/2, open parenthesis, 1 plus x, close parenthesis, to the minus 1/2, and differentiate as a product. Proceeding as in example 1 above, we get numerator d, open parenthesis, 1 minus x, close parenthesis, to the 1/2, and numerator, over denominator dx, and denominator equals minus numerator 1 and numerator over denominator 2 times the square root of the quantity 1 minus x, and denominator, and numerator d, open parenthesis, 1 plus x, close parenthesis, to the 1/2, and numerator over denominator dx, and denominator equals numerator 1 and numerator over denominator 2 times the square root of the quantity 1 plus x. Hence, dy over dx equals minus numerator, open parenthesis, 1 plus x, close parenthesis, to the 1/2, and numerator over denominator 2, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 minus x, and denominator minus numerator, open parenthesis, 1 minus x, close parenthesis, to the 1/2, and numerator over denominator 2, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 plus x, and denominator equals minus numerator 1 and numerator over denominator 2 times the square root of the quantity 1 plus x times the square root of the quantity 1 minus x, and denominator minus numerator the square root of the quantity 1 minus x, and numerator all over denominator 2 times the square root of the quantity, open parenthesis, 1 plus x, close parenthesis, cubed, and denominator. Or dy over dx equals minus numerator 1 and numerator over denominator, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 minus x squared, and denominator. 6. Differentiate y equals the square root of the quantity x cubed over 1 plus x squared, end quantity. We may write this y equals x to the 3 over 2 power open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2. dy over dx equals 3 over 2 x to the 1/2, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, plus x to the 3 over 2 power, times numerator d, open bracket, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, close bracket, and numerator, over dx. Differentiating, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, as shown in example 2 above, we get numerator d, open bracket, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, close bracket, and numerator, over dx, equals minus numerator x and numerator over denominator the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, and denominator. So that dy over dx equals numerator 3 times the square root of x, and numerator over denominator 2 times the square root of the quantity 1 plus x squared, and denominator, minus numerator the square root of x to the 5th, and numerator over denominator the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, and denominator, equals numerator the square root of x, open parenthesis, 3 plus x squared, close parenthesis, and numerator, over denominator 2 times the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, and denominator. 7. Differentiate y equals, open parenthesis, x plus the square root of the quantity x squared plus x plus a, close parenthesis, cubed. Let x plus the square root of the quantity x squared plus x plus a equal u. du over dx equals 1 plus numerator d, open bracket, open parenthesis, x squared plus x plus a, close parenthesis, to the 1/2, close bracket, and numerator, over dx. Y equals u cubed, and dy over du equals 3u squared, equals 3, open parenthesis, x plus the square root of the quantity x squared plus x plus a, close parenthesis, squared. Now let, open parenthesis, x squared plus x plus a, close parenthesis, to the 1/2 equal v, and, open parenthesis, x squared plus x plus a, close parenthesis, equal w. dw over dx equals 2x plus 1. v equals w to the 1/2. dv over dw equals 1/2 w to the minus 1/2. dv over dx equals dv over dw times dw over dx equals 1/2, open parenthesis, x squared plus x plus a, close parenthesis, to the minus 1/2, open parenthesis, 2x plus 1, close parenthesis. Hence, du over dx equals 1 plus numerator 2x plus 1 and numerator over denominator 2 times the square root of the quantity x squared plus x plus a, and denominator. dy over dx equals dy over du times du over dx equals 3, open parenthesis, x plus the square root of the quantity x squared plus x plus a, close parenthesis, squared, open parenthesis, 1 plus numerator 2x plus 1 and numerator over denominator 2 times the square root of the quantity x squared plus x plus a, and denominator, close parenthesis. 8. Differentiate y equals the square root of the quantity numerator a squared plus x squared and numerator over denominator a squared minus x squared, and denominator, and quantity, times the cube root of the quantity, numerator, a squared minus x squared, and numerator, over denominator, a squared plus x squared, and denominator, and quantity, we get y equals numerator, open parenthesis, a squared plus x squared, close parenthesis, to the 1/2, open parenthesis, a squared minus x squared, close parenthesis, to the 1/3, and numerator, over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 1/2, open parenthesis, a squared plus x squared, close parenthesis, to the 1/3, and denominator, equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6 power. dy over dx equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, times numerator d, open bracket, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6 power, close bracket, and numerator, over denominator dx, and denominator, plus numerator d, open bracket, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, close bracket, and numerator, over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 1/6 power, dx, and denominator. Let u equal, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6, and v equal, open parenthesis, a squared minus x squared, close parenthesis. U equals v to the minus 1/6 power, du over dv equals minus 1/6 v to the minus 7/6 power. dv over dx equals minus 2x. du over dx equals du over dv times dv over dx equals 1/3 x, open parenthesis, a squared minus x squared, close parenthesis, to the minus 7/6 power. Let w equal, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, and z equal the quantity a squared plus x squared. W equals z to the 1/6 power, dw over dz equals 1/6 z to the minus 5/6 power. dz over dx equals 2x. dw over dx equals dw over dz times dz over dx equals 1/3 x, open parenthesis, a squared plus x squared, close parenthesis, to the minus 5/6 power. Hence, dy over dx equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, times numerator x, and numerator, over denominator, 3, open parenthesis, a squared minus x squared, close parenthesis, to the 7/6 power, and denominator, plus numerator x, and numerator, over denominator, 3, open parenthesis, a squared minus x squared, close parenthesis, to the 1/6 power, open parenthesis, a squared plus x squared, close parenthesis, to the 5/6 power, and denominator. Or dy over dx equals x over 3, open bracket, the 6th root of the quantity numerator a squared plus x squared, and numerator, over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 7th power, and denominator, and quantity, and 6th root, plus 1 over denominator, the 6th root of, open parenthesis, a squared minus x squared, close parenthesis, open parenthesis, a squared plus x squared, close parenthesis, to the 5th, and 6th root, and denominator, and bracket. 9. Differentiate y to the n with respect to y to the fifth. d of y to the n over d of y to the fifth equals ny to the n minus 1 all over 5y to the 5 minus 1 equals the quantity n over 5, end quantity, times y to the n minus 5. 10. Find the first and second differential coefficients of y equals x over b times the square root of, open parenthesis, a minus x, close parenthesis, x. dy over dx equals x over b times numerator d, open brace, open bracket, open parenthesis, a minus x, close parenthesis, x, close bracket, to the 1/2, close brace, end numerator, over denominator dx, end denominator, plus numerator, the square root of, open parenthesis, a minus x, close parenthesis, x, end numerator, over denominator b, end denominator. Let, open bracket, open parenthesis, a minus x, close parenthesis, x, close bracket, to the 1/2, equal u, and let, open parenthesis, a minus x, close parenthesis, x, equal w. Then u equals w to the 1/2. du over dw equals 1/2 w to the minus 1/2, equals 1 over 2w to the 1/2, equals 1 over denominator 2 times the square root of, open parenthesis, a minus x, close parenthesis, x, end denominator. dw over dx equals a minus 2x. du over dw times dw over dx equals du over dx equals numerator a minus 2x and numerator over denominator 2 times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator. Hence, dy over dx equals numerator x, open parenthesis, a minus 2x, close parenthesis, and numerator, over denominator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator, plus numerator, the square root of, open parenthesis, a minus x, close parenthesis, x, and numerator, over denominator b, and denominator, equals numerator x, open parenthesis, 3a minus 4x, close parenthesis, and numerator, over denominator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator. Now, d2y over dx squared equals numerator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and square root, open parenthesis, 3a minus 8x, close parenthesis, minus the quantity, numerator, open parenthesis, 3ax minus 4x squared, close parenthesis, b, open parenthesis, a minus 2x, close parenthesis, and numerator, over denominator, the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator, and quantity, and numerator, all over denominator 4b squared, open parenthesis, a minus x, close parenthesis, x, and denominator, equals numerator 3a squared minus 12ax plus 8x squared, and numerator, over denominator 4b, open parenthesis, a minus x, close parenthesis, times the square root of, open parenthesis, a minus x, close parenthesis, x, and square root, and denominator. We shall need these last two differential coefficients later on. See exercise 10, number 11. End of section 15. Calculus Made Easy by Silvanus P. Thompson, section 16. Exercises 6. Differentiate the following. 1. Y equals the square root of the quantity x squared plus 1. Answer: x over the square root of the quantity x squared plus 1. 2. Y equals the square root of the quantity x squared plus a squared. Answer: x over the square root of the quantity x squared plus a squared. 3. Y equals 1 over the square root of the quantity a plus x. Answer: minus 1 over 2 times the square root of, open parenthesis, a plus x, close parenthesis, cubed. 4. Y equals a over the square root of the quantity a minus x squared. Answer: ax over the square root of, open parenthesis, a minus x squared, close parenthesis, cubed. 5. Y equals the square root of the quantity x squared minus a squared, all over x squared. Answer: 2a squared minus x squared, all over x cubed times the square root of the quantity x squared minus a squared. 6. Y equals the cube root of the quantity x to the fourth plus a, all over the square root of the quantity x cubed plus a. Answer: numerator 3 over 2 x squared, open bracket, 8 over 9 x, open parenthesis, x cubed plus a, close parenthesis, minus, open parenthesis, x to the fourth plus a, close parenthesis, close bracket, end numerator, all over, denominator, open parenthesis, x to the fourth plus a, close parenthesis, to the 2 over 3 power, open parenthesis, x cubed plus a, close parenthesis, to the 3 over 2 power, end denominator. 7. Y equals the quantity a squared plus x squared, all over, open parenthesis, a plus x, close parenthesis, squared. Answer: 2a times the quantity x minus a, all over, open parenthesis, x plus a, close parenthesis, cubed. 8. Differentiate y to the fifth with respect to y squared. Answer: 5 over 2 y cubed. 9. Differentiate y equals the square root of the quantity 1 minus theta squared, all over 1 minus theta. Answer: 1 over the quantity 1 minus theta times the square root of the quantity 1 minus theta squared. The process can be extended to 3 or more differential coefficients, so that dy over dx equals dy over dz times dz over dv times dv over dx. Examples: 1. If z equals 3x to the fourth, v equals 7 over z squared, y equals the square root of the quantity 1 plus v, find dv over dx. We have dy over dv equals 1 over 2 times the square root of the quantity 1 plus v. dv over dz equals minus 14 over z cubed. dz over dx equals 12x cubed. dy over dx equals minus 168x cubed over, open parenthesis, 2 times the square root of the quantity 1 plus v, close parenthesis, z cubed, equals minus 28 over 3x to the fifth times the square root of the quantity 9x to the eighth plus 7. 2. if t equals 1 over 5 times the square root of theta, x equals t cubed plus the quantity t over 2, v equals 7x squared over the cube root of the quantity x minus 1, find dv over d theta. dv over dx equals 7x, open parenthesis, 5x minus 6, close parenthesis, all over 3 times the cube root of, open parenthesis, x minus 1, close parenthesis, to the fourth. dx over dt equals 3t squared plus 1/2. dt over d theta equals minus 1 over 10 times the square root of theta cubed. Hence, dv over d theta equals minus numerator 7x, open parenthesis, 5x minus 6, close parenthesis, open parenthesis, 3t squared plus 1/2, close parenthesis, end numerator, over denominator 30 times the cube root of, open parenthesis, x minus 1, close parenthesis, to the fourth, end cube root, times the square root of theta cubed, end denominator, an expression in which x must be replaced by its value, and t by its value in terms of theta. 3. If theta equals 3a squared x, all over the square root of x cubed, omega equals the square root of the quantity 1 minus theta squared, all over 1 plus theta, and phi equals the square root of 3 minus the quantity 1 over omega times the square root of 2. Find d phi over dx. We get theta equals 3a squared x to the minus 1/2. Omega equals the square root of the quantity 1 minus theta over 1 plus theta. And phi equals the square root of 3 minus the quantity 1 over the square root of 2 times omega to the minus 1. d theta over dx equals minus 3a squared all over 2 times the square root of x cubed. d omega over d theta equals minus 1 over the quantity 1 plus theta times the square root of 1 minus theta squared. See example 5, page 68. And d phi over d omega equals 1 over the quantity the square root of 2 times omega squared, so that d theta over dx equals 1 over the quantity the square root of 2 times omega squared, all times 1 over the quantity 1 plus theta times the square root of 1 minus theta squared, all times 3a squared over 2 times the square root of x cubed. Replace now first omega, then theta by its value. Exercises 7. You can now successfully try the following. 1. If u equals 1/2 x cubed, v equals 3 times the quantity u plus u squared, and w equals 1 over v squared, find dw over dx. Answer. dw over dx equals numerator 3x squared, open parenthesis, 3 plus 3x cubed, close parenthesis, end numerator, all over denominator 27, open parenthesis, 1/2 x cubed plus 1/4 x to the 6th, close parenthesis, cubed, end denominator. 2. If y equals 3x squared plus the square root of 2, z equals the square root of the quantity 1 plus y, and v equals 1 over the quantity the square root of 3 plus 4z, find dv over dx. Answer. dv over dx equals minus numerator 12x, end numerator, over denominator the square root of 1 plus the square root of 2 plus 3x squared, end square root, open parenthesis, the square root of 3 plus 4 times the square root of the quantity 1 plus the square root of 2 plus 3x squared, close parenthesis, squared. End denominator. 3. If y equals x cubed over the square root of 3, z equals the quantity 1 plus y squared, and u equals 1 over the square root of the quantity 1 plus z, find du over dx. Answer: du over dx equals minus numerator x squared, open parenthesis, the square root of 3 plus x cubed, close parenthesis, end numerator, all over denominator, the square root of, open bracket, 1 plus, open parenthesis, 1 plus the quantity x cubed over the square root of 3, close parenthesis, squared, close bracket, cubed. End denominator. End of section 16.
It is useful to consider what geometrical meaning can be given to the differential coefficient. In the first place, any function of x, such for example as x squared or the square root of x or ax plus b, can be plotted as a curve, and nowadays every schoolboy is familiar with the process of curve plotting. Let p, q, and r in figure 7 be a portion of a curve plotted with respect to the axes of coordinates ox and oy. Consider any point q on this curve, where the abscissa of the point is x and the ordinate is y. Now, observe how y changes when x is varied. If x is made to increase by a small increment, dx, to the right, it will be observed that y also, in this particular curve, increases by a small increment dy, because this particular curve happens to be an ascending curve. Then the ratio of dy to dx is a measure of the degree to which the curve is sloping up between the 2 points q and t. As a matter of fact, it can be seen on the figure that the curve between q and t has many different slopes, so that we cannot very well speak of the slope of the curve between q and t. If, however, q and t are so near each other that the small portion of qt of the curve is practically straight, then it is true to say that the ratio of dy dx is the slope of the curve along qt. The straight line qt produced on the other side touches the curve along the portion qt only, and if this portion is indefinitely small, the straight line will touch this curve at practically 1 point only, and be therefore a tangent to the curve. This tangent to the curve is evidently the same slope as qt, so that dy dx is the slope of the tangent to the curve at the point q for which the value of dy dx is found. We have seen that the short expression, the slope of a curve, has no precise meaning because a curve has so many slopes. In fact, every small portion of a curve has a different slope. The slope of a curve at a point is, however, a perfectly defined thing. It is the slope of a very small portion of the curve situated just at that point, and we have seen that this is the same as the slope of the tangent to the curve at that point. Observe that dx is a short step to the right and dy the corresponding short step upwards. These steps must be considered as short as possible, in fact, indefinitely short, though in diagrams we have to represent them by bits that are not infinitesimally small, otherwise they could not be seen. We shall hereafter make considerable use of the circumstance that dy dx represents the slope of the curve at any point. If a curve is sloping up at 45 degrees at a particular point, as in figure 8, dy and dx will be equal, and the value of dy dx equals 1. If the curve slopes up steeper than 45 degrees, as in figure 9, dy dx will be greater than 1. If the curve slopes up very gently, as in figure 10, dy dx will be a fraction smaller than 1. For a horizontal line or a horizontal place in a curve, dy equals 0, and therefore dy dx equals 0. If a curve slopes downward, as in figure 11, dy will be a step down, and must therefore be reckoned of negative value, hence dy dx will have negative sign also. If the curve happens to be a straight line, like that in figure 12, the value of dy dx will be the same at all points along it. In other words, its slope is constant. If a curve is one that turns more upwards as it goes along to the right, the value of dy dx will become greater and greater with the increasing steepness, as in figure 13. If a curve is one that gets flatter and flatter as it goes along, the values of dy dx will become smaller and smaller as the flatter part is reached, as in figure 14. If a curve first descends and then goes up again, as in figure 15, presenting a concavity upwards, then clearly dy dx will first be negative, with diminishing values as the curve flattens, then will be 0 at the point where the bottom of the trough of the curve is reached, and from this point onward, dy dx will have positive values that go on increasing. In such a case, y is said to pass by a minimum. The minimum value of y is not necessarily the smallest value of y, it is that value of y corresponding to the bottom of the trough. For instance, in figure 28, the value of y corresponding to the bottom of the trough is 1, while y takes elsewhere values which are smaller than this. The characteristic of a minimum is that y must increase on either side of it. Note, for the particular value of x that makes y a minimum, the value of dy dx equals 0. If a curve first ascends and then descends, the value of dy dx will be positive at first, then 0 as the summit is reached, then negative as the curve slopes downwards, as in figure 16. In this case, y is said to pass by a maximum, but the maximum value of y is not necessarily the greatest value of y. In figure 28, the maximum of y is 2 1/3, but this is by no means the greatest value of y can have at some other point of the curve. Note, for the particular value of x that makes y a maximum, the value of dy dx equals 0. If a curve has the peculiar form of figure 17, the values of dy dx will always be positive, but there will be one particular place where the slope is least steep, where the value of dy dx will be a minimum, that is, less than it is at any other part of the curve. If a curve has the form of figure 18, the value of dy dx will be negative in the upper part and positive in the lower part, while at the nose of the curve, where it becomes actually perpendicular, the value of dy dx will be infinitely great. Now that we understand that dy dx measures the steepness of a curve at any point, let us turn to some of the equations we have already learned how to differentiate. 1. As the simplest case, take this, y equals x plus b. It is plotted out in figure 19, using equal scales for x and y. If we put x equals 0, then the corresponding ordinate will be y equals b. That is to say, the curve crosses the y-axis at the height b. From here, it ascends at 45 degrees. For whatever values we give to the x to the right, we have an equal y to ascend. The line has a gradient of 1 and 1. Now differentiate y equals x plus b by the rules we have already learned, and we get dy dx equals 1. The slope of the line is such that for every little step dx to the right, we go an equal little step dy upward, and this slope is constant, always the same slope. 2. Take another case, y equals ax plus b. We know that this curve, like the preceding one, will start from a height b on the y-axis. But before we draw the curve, let us find its slope by differentiating, which gives dy dx equals a. The slope will be constant at an angle, the tangent of which is here called a. Let us assign to a some numerical value, let's say 1/3. Then we must give it such a slope that it ascends 1 in 3, or dx will be 3 times as great as dy, as magnified in figure 21. So, draw the line in figure 20 at this slope. 3. Now for a slightly harder case. Let y equals ax squared plus b. Again, the curve will start on the y-axis at a height b above the origin. Now differentiate. If you have forgotten, turn back to page 25, or rather don't turn back but think out the differentiation. dy dx equals 2ax. This shows that the steepness will not be constant. It increases as x increases. At the starting point P, where x equals 0, the curve of figure 22 has no steepness. That is, it is level. On the left of the origin, where x has negative values, dy dx will also have negative values, or it will descend from left to right, as in the figure. Let us illustrate this by working out a particular instance, taking the equation y equals 1/4 x squared plus 3. And differentiating it, we get dy dx equals 1/2 x. Now, assign a few successive values, say from 0 to 5 to x, and calculate the corresponding values of y by the first equation and of dy dx from the second equation. Tabulating the results, we have, for values of x, 0, 1, 2, 3, 4, 5, we have values of y of 3, 3 1/4, 4, 5 1/4, 7, 9 1/4. For values of x, 0, 1, 2, 3, 4, 5, we have dy dx equals 0, 1/2, 1, 1.5, 2, 2.5. Then plot them out in two curves, figure 23 and 24. In figure 23, plotting the value of y against those of x, and in figure 24, those of dy dx against those of x. For any assigned value of x, the height of the ordinate in the second curve is proportional to the slope of the first curve. If a curve comes to a sudden cusp, as in figure 25, the slope at that point suddenly changes from a slope upward to a slope downward. In that case, dy dx will clearly undergo an abrupt change from a positive to a negative value. The following examples will show further applications of the principles just explained. 4. Find the slope of the tangent of the curve y equals 1/2x plus 3 at the point where x equals -1. Find the angle which this tangent makes with the curve of y equals 2x squared plus 2. The slope of the tangent is the slope of the curve at the point where they touch each other. That is, it is the dy dx of the curve for that point. Here, dy dx equals minus 1/2x squared, and for x equals -1, dy dx equals -1/2, which is the slope of the tangent and of the curve at that point. The tangent, being a straight line, has for the equation y equals ax plus b, and its slope is dy dx equals a. Hence, a equals -1/2. Also, if x equals -1, y equals 1/2 times -1 plus 3, and that equals 2.5. And as the tangent passes by this point, the coordinates of the point must satisfy the equation of the tangent, namely, y equals -1/2x plus b, so that 2.5 equals -1/2 times -1 plus b, and b equals 2. The equation of the tangent is therefore y equals -1/2x plus 2. Now when the two curves meet, the intersection being a point common to both curves, its coordinates must satisfy the equation of each one of the two curves. That is, it must be a solution of the system of simultaneous equations formed by coupling together the equations of the curves. Here, the curves meet one another at points given by the solution of y equals 2x squared plus 2 and y equals -1/2x plus 2, or 2x squared plus 2 equals -1/2x plus 2. That is, x times the quantity of 2x plus 1/2 equals 0. This equation has for its solution x equals 0 and x equals -1/4. The slope of the curve y equals 2x squared plus 2 at any point is dy dx equals 4x. For the point where x equals 0, the slope is 0. The curve is horizontal. For the point where x equals -1/4, dy dx equals -1. Hence the curve at the point slopes downward to the right at such an angle theta with the horizontal that tan theta equals 1. That is, at 45 degrees to the horizontal. The slope of the straight line is -1/2. That is, it slopes downwards to the right and makes with the horizontal an angle phi such that tan phi equals 1/2. That is an angle of 26 degrees 34 minutes. It follows that at the first point the curve cuts the straight line at an angle of 26 degrees 34 minutes, while at the second it cuts at an angle of 45 degrees minus 26 degrees 34 minutes, which equals 18 degrees 26 minutes. 5. A straight line is to be drawn through a point whose coordinates are x equal 2 and y equals minus 1, as tangent to the curve y equals x squared minus 5x plus 6. Find the coordinates of the point of contact. The slope of the tangent must be the same as dy dx of the curve, that is, 2x minus 5. The equation of the straight line is y equals ax plus b, and it is satisfied for the values of x equals 2 and y equals minus 1. Then minus 1 equals a times 2 plus b. Also, its dy dx equals a equals 2x minus 5. The x and the y of the point of contact must also satisfy both the equations of the tangent and the equations of the curve. We have then simultaneous equations: y equals x squared minus 5x plus 6, y equals ax plus b, minus 1 equals 2a plus b, and a equals 2x minus 5. 4 equations in a, b, x, y. Equations 1 and 2 give us x squared minus 5x plus 6 equals ax plus b. Replacing a and b by their values in this, we get x squared minus 5x plus 6 equals the quantity 2x minus 5 times x minus 1 minus 2 times the quantity 2x minus 5, which simplifies to x squared minus 4x plus 3 equals 0, the solutions of which are x equals 3 and x equals 1. Replacing in equation 1, we get y equals 0 and y equals 2, respectively. The 2 points of contact are then x equal 1, y equal 2, and x equal 3, y equals 0. Note, in all exercises dealing with curves, students will find it extremely instructive to verify the deductions obtained by actually plotting the curves. End of section 17.
Calculus Made Easy by Silvanus P. Thompson, Section 18. Exercises 8. 1. Plot the curve y equals 3/4 x squared minus 5 using a scale of millimeters. Measure at points corresponding to different values of x the angle of its slope. Find, by differentiating the equation, the expression for slope, and see, from a table of natural tangents, whether this agrees with the measured angle. 2. Find what will be the slope of the curve y equals 0.12x cubed minus 2 at the particular point that has an abscissa x equal 2. Answer: 1.44. 3. If y equal the quantity x minus a times the quantity x minus b, show that at the particular point of the curve where dy over dx equals 0, x will have the value 1/2 times the quantity a plus b. 4. Find the dy over dx of the equation y equals x cubed plus 3x and calculate the numerical values of dy over dx for the points corresponding to x equals 0, x equal 1/2, x equal 1, x equal 2. Answer: dy over dx equal 3x squared plus 3, and the numerical values are 3, 3 3/4, 6, and 15. 5. In the curve to which the equation is x squared plus y squared equal 4, find the values of x at those points where the slope equal 1. Answer: plus or minus the square root of 2. 6. Find the slope, at any point, of the curve whose equation is x squared over 3 squared plus y squared over 2 squared equal 1, and give the numerical value of the slope at the place where x equals 0, and at that where x equal 1. Answer: dy over dx equal -4/9 times x over y. Slope is 0 where x equals 0, and it is plus or minus 1/3 times the square root of 2, where x equal 1. 7. The equation of a tangent to the curve y equal 5 minus 2x plus 0.5 x cubed, being of the form y equal mx plus n, where m and n are constants, find the value of m and n if the point where the tangent touches the curve has x equal 2 for abscissa. Answer: m equal 4, n equal -3. 8. At what angles do the two curves y equal 3.5 x squared plus 2 and y equal x squared minus 5x plus 9.5 cut one another? Answer: intersections at x equal 1, x equal -3, angles 153 degrees 26 minutes, 2 degrees 28 minutes. 9. Tangents to the curve y equal plus or minus the square root of 25 minus x squared are drawn at points for which x equal 3 and x equal 4. Find the coordinates of the points of intersection of the tangents and their mutual inclination. Answer: intersection at x equal 3.57, y equal 3.50, angle 16 degrees 16 minutes. 10. A straight line, y equal 2x minus b, touches a curve y equal 3x squared plus 2 at one point. What are the coordinates of the point of contact, and what is the value of b? Answer: x equal 1/3, y equal 2 1/3, b equal -5/3. End of section 18.
Made Easy by Silvanus P. Thompson. Chapter 11, Maxima and Minima, Part 1. One of the principal uses of the process of differentiating is to find out under what conditions the value of the thing differentiated becomes a maximum or a minimum. This is often exceedingly important in engineering questions, where it is most desirable to know what conditions will make the cost of working a minimum or will make the efficiency a maximum. Now, to begin with a concrete case, let us take the equation y equals x squared minus 4x plus 7. By assigning a number of successive values to x and finding the corresponding values of y, we can readily see that the equation represents a curve with a minimum. When x equals 0, y equals 7. When x equals 1, y equals 4. When x equals 2, y equals 3. When x equals 3, y equals 4. When x equals 4, y equals 7. When x equals 5, y equals 12. These values are plotted in Figure 26, which shows that y has apparently a minimum value of 3 when x is made equal to 2. But are you sure that the minimum occurs at 2 and not in 2 1/4 or 1 3/4? Note: Figure 26 shows a graph with the curve y equals x squared minus 4x plus 7, plotted with dotted lines indicating the earlier mentioned points. Of course, it would be possible with any algebraic expression to work out a lot of values, and in this way arrive gradually at the particular value that may be a maximum or a minimum. Here is another example. Let y equals 3x minus x squared. calculate a few values thus. When x equals -1, y equals -4. When x equals 0, y equals 0. When x equals 1, y equals 2. When x equals 2, y equals 2. When x equals 3, y equals 0. When x equals 4, y equals -4. When x equals 5, y equals -10. Plot these values as in figure 27. Note: figure 27 shows the curve y equals 3x minus x squared plotted with dotted lines indicating previously mentioned points. The maximum value is somewhere between 1 and 2 on the x-axis. It will be evident that there will be a maximum somewhere between x equals 1 and x equals 2, and the thing looks as if the maximum value of y ought to be about 2 1/4. Try some intermediate values. If x equals 1 1/4, y equals 2.187. If x equals 1 1/2, y equals 2.25. If x equals 1.6, y equals 2.24. How can we be sure that 2.25 is the real maximum, or that it occurs exactly when x equals 1 1/2? Now, it may sound like juggling to be assured that there is a way by which one can arrive straight at a maximum or minimum value without making a lot of preliminary trials or guesses, and that way depends on differentiating. Look back to an earlier page, 78, for the remarks about figures 14 and 15, and you will see that whenever a curve gets either to its maximum or to its minimum height, at that point its dy over dx equals 0. Now this gives us the clue to the dodge that is wanted. When there is put before you an equation, and you want to find that value of x which will make its y a minimum or a maximum, first differentiate it, and having done so, write its dy over dx as equal to 0, and then solve for x. Put this particular value of x into the original equation, and you will then get the required value of y. This process is commonly called equating to 0. To see how simply it works, take the example with which this chapter opens, namely y equals x squared minus 4x plus 7. Differentiating, we get dy over dx equals 2x minus 4. Now equate this to 0, thus 2x minus 4 equals 0. Solving this equation for x, we get 2x equals 4, x equals 2. Now we know that the maximum or minimum will occur exactly when x equals 2. Putting the value x equals 2 into the original equation, we get y equals 2 squared minus 4 times 2 plus 7 equals 4 minus 8 plus 7 equals 3. Now look back at figure 26, and you will see that the minimum occurs when x equals 2, and that this minimum of y equals 3. Try the second example, figure 27, which is y equals 3x minus x squared. Differentiating, dy over dx equals 3 minus 2x, equating to 0. 3 minus 2x equals 0, whence x equals 1 1/2. And putting this value of x into the original equation, we find y equals 4 1/2 minus 1 1/2 times 1 1/2, y equals 2 1/4. This gives us exactly the information as to which the method of trying a lot of values left us uncertain. Now before we go on to any further cases, we have two remarks to make. When you are told to equate dy over dx to 0, you feel at first, that is if you have any wits of your own, a kind of resentment. because you know that dy over dx has all sorts of different values at different parts of the curve, according to whether it is sloping up or down. So when you are suddenly told to write dy over dx equals 0, you resent it, and feel inclined to say that it can't be true. Now you will have to understand the essential difference between an equation and an equation of condition. Ordinarily, you are dealing with equations that are true in themselves, but, on occasions, of which the present are examples, you have to write down equations that are not necessarily true, but are only true if certain conditions are to be fulfilled, and you write them down in order, by solving them, to find the conditions which make them true. Now we want to find the particular value that $x$ has when the curve is neither sloping up nor sloping down, that is, at the particular place where dy over dx equals 0. So, writing dy over dx equals 0 does not mean that it is always equal 0, but you write it down as a condition in order to see how much x will come out if dy over dx is to be 0. The second remark is one which, if you have any wits of your own, you will probably have already made, namely, that this much belauded process of equating to 0 entirely fails to tell you whether the x that you thereby find is going to give you a maximum value of y or a minimum value of y. Quite so. It does not of itself discriminate. It finds for you the right value of x, but leaves you to find out for yourselves whether the corresponding y is a maximum or a minimum. Of course, if you have plotted the curve, you know already which it will be. For instance, take the equation y equals 4x plus 1 over x. Without stopping to think what curve it corresponds to, differentiate it, and equate to 0. dy over dx equals 4 minus x to the power of minus 2 equals 4 minus 1 over x squared equals 0, whence x equals a half, and inserting this value, y equals 4, will be either a maximum or else a minimum, but which? You will hereafter be told away, depending upon a second differentiation. But at present it is enough if you will simply try any other value of x differing a little from the one found, and see whether with this altered value the corresponding value of y is less or greater than that already found. Try another simple problem in maxima and minima. Suppose you were asked to divide Calculus Made Easy by Silvanus P. Thompson. Chapter 11, Maxima and Minima, Part 2. Further examples. A most interesting example is afforded by a curve that has both a maximum and a minimum. Its equation is y equals 1/3 x cubed minus 2x squared plus 3x plus 1. Now, dy over dx equals x squared minus 4x plus 3. Equating to 0, we get the quadratic x squared minus 4x plus 3 equals 0, and solving the quadratic gives us two roots, viz. X equals 3 and x equals 1. Now, when x equals 3, y equals 1, and when x equals 1, y equals 2 1/3. The first of these is a minimum, the second a maximum. The curve itself may be plotted from the values calculated as below from the original equation. When x equals -1, y equals -4 1/3. When x equals 0, y equals 1. When x equals 1, y equals 2 1/3. When x equals 2, y equals 1 2/3. When x equals 3, y equals 1. When x equals 4, y equals 2 1/3. When x equals 5, y equals 7 2/3. When x equals 6, y equals 19. A further exercise in maxima and minima is afforded by the following example. The equation to a circle of radius r, having its centre C at the point whose coordinates are x equals a, y equals b, as depicted in Figure 29 is open brackets y minus b close brackets squared plus open brackets x minus a close brackets squared equals r squared. Note: Figure 29 shows a circle in the xy plane as described, with a line from the centre of the circle to the edge labelled r for the radius. This may be transformed into y equals the square root of r squared minus open brackets x minus a close brackets squared and plus b. Now we know beforehand, by mere inspection of the figure, that when x equals a, y will be either at its maximum value b plus r, or else its minimum value b minus r. But let us not take advantage of this knowledge. Let us set about finding what value of x will make y a maximum or a minimum by the process of differentiating and equating to zero. dy over dx equals 1/2 times 1 over the square root of r squared minus open brackets x minus a close brackets squared times by open brackets 2a minus 2x close brackets, which reduces to dy over dx equals a minus x all over square root of r squared minus open brackets x minus a close brackets squared. Then the condition for y being maximum or minimum is a minus x all over the square root of r squared minus open brackets x minus a close brackets squared equals 0. Since no value whatever of x will make the denominator infinite, the only condition to give 0 is x equals a. Inserting this value in the original equation for the circle, we find y equals square root of r squared plus b. And as the root of r squared is either plus r or minus r, we have two resulting values of y equals b plus r, y equals b minus r. The first of these is the maximum at the top, the second is the minimum at the bottom. If the curve is such that there is no place that is a maximum or a minimum, the process of equating to 0 will yield an impossible result. For instance, let y equals a x cubed plus bx plus c. Then dy over dx equals 3ax squared plus b. Equating this to 0, we get 3ax squared plus b equals 0. X squared equals minus b over 3a, and x equals the square root of minus b over 3a, which is impossible. Therefore y has no maximum nor minimum. A few more worked examples will enable you to thoroughly master this most interesting and useful application of the calculus. 1. What are the sides of the rectangle of maximum area inscribed in a circle of radius r? If one side be called x, the other side equals the square root of diagonal squared minus x squared. And as the diagonal of the rectangle is necessarily a diameter, the other side equals square root of 4r squared minus x squared. Then area of rectangle S equals x times the square root of 4r squared minus x squared. ds over dx equals x times d open brackets square root of 4r squared minus x squared close brackets over dx plus the square root of 4r squared minus x squared times dx over dx. If you have forgotten how to differentiate the square root of 4r squared minus x squared, here is a hint. Write 4r squared minus x squared equals w, and y equals the square root of w, and seek dy over dw and dw over dx. Fight it out, and only if you can't get on refer to page 66. You will get ds over dx equals x times minus x over square root of 4r squared minus x squared, add the square root of 4r squared minus x squared, equals 4r squared minus 2x squared all over the square root of 4r squared minus x squared. For maximum or minimum we must have 4r squared minus 2x squared all over the square root of 4r squared minus x squared equals 0. That is, 4r squared minus 2x squared equals 0, and x equals r times root 2. The other side equals square root of 4r squared minus 2r squared equals r times square root of 2. The two sides are equal. The figure is a square, the side of which is equal to the diagonal of the square constructed on the radius. In this case, of course, it is a maximum with which we are dealing. 2. What is the radius of the opening of a conical vessel, the sloping side of which has a length L when the capacity of the vessel is greatest? If r be the radius and h the corresponding height, h equals the square root of L squared minus r squared. Volume V equals pi r squared times h over 3 equals pi r squared times square root of L squared minus r squared all over 3. Proceeding as in the previous problem, we get dv over dr equals pi r squared times minus r over 3 times the square root of L squared minus r squared plus 2 pi r over 3 times the square root of L squared minus r squared equals 2 pi r open brackets L squared minus r squared close brackets minus pi r cubed all over 3 times the square root of L squared minus r squared equals 0 for maximum or minimum, or 2 pi r open brackets L squared minus r squared close brackets minus pi r cubed equals 0, and r equals L times the square root of 2 over 3 for a maximum, obviously. 3. Find the maxima and minima of the function y equals x over 4 minus x plus 4 minus x all over x. We get dy over dx equals open brackets 4 minus x close brackets minus open brackets minus x close brackets all over open brackets 4 minus x close brackets squared plus minus x minus open brackets 4 minus x close brackets all over x squared equals 0. The maximum or minimum, or 4 over open brackets 4 minus x close brackets squared minus 4 over x squared equals 0, and x equals 2. There is only one value, hence only one maximum or minimum. For x equals 2, y equals 2. For x equals 1.5, y equals 2.27. For x equals 2.5, y equals 2.27. It is therefore a minimum. It is instructive to plot the graph of the function. 4. Find the maxima and minima of the function y equals the square root of 1 plus x add the square root of 1 minus x. It will be found instructive to plot the graph. Differentiating gives at once. See example number 1, page 67. dy over dx equals 1 over 2 times the square root of 1 add x minus 1 over 2 times the square root of 1 minus x equals 0 for maximum or minimum. Hence, square root of 1 plus x equals the square root of 1 minus x, and x equals 0 the only solution. For x equals 0, y equals 2. For x equals plus minus 0.5, y equals 1.932, so it is a maximum. 5. Find the maxima and minima of the function y equals x squared minus 5 all over 2x minus 4. We have dy over dx equals open brackets 2x minus 4 close brackets times 2x minus open brackets x squared minus 5 close brackets times 2 all over open brackets 2x minus 4 close brackets squared equals 0. The maximum or minimum, or 2x squared minus 8x plus 10 all over open brackets 2x minus 4 close brackets squared equals 0, or x squared minus 4x plus 5 equals 0, which has for solutions x equals 5 over 2 plus minus square root of minus 1. These being imaginary, there is no real value of x for which dy over dx equals 0, hence there is neither maximum nor minimum. 6. Find the maxima and minima of the function open brackets y minus x squared close brackets squared equals x to the power 5. This may be written y equals x squared plus minus x to the power of 5 over 2. dy over dx equals 2x plus minus 5 over 2 times x to the power of 3 over 2 equals 0 for maximum or minimum. That is, x open brackets 2 plus minus 5 over 2 times x to the power of 1 over 2 close brackets equals 0, which is satisfied for x equals 0 and for 2 plus minus 5 over 2 x to the power of a half equals 0, that is, for x equals 16 over 25. So there are two solutions. Taking first x equals 0, if x equals minus 0.5, y equals 0.25 plus minus the square root of minus 0.5 to the power of 5, and if x equals plus 0.5, y equals 0.25 plus minus square root of 0.5 to the power of 5. On the one side, y is imaginary, that is, there is no value of y that can be represented by a graph. The latter is therefore entirely on the right side of the axis of y. See figure 30. On plotting the graph, it will be found that the curve goes to the origin as if there were a minimum there, but instead of continuing beyond, as it should do for a minimum, it retraces its steps, forming what is called a cusp. There is no minimum, therefore, although the condition for a minimum is satisfied, namely dy over dx equals 0. It is necessary, therefore, always to check by taking one value on either side. Now, if we take x equals 16 over 25 equals 0.64, if x equals 0.64, y equals 0.7373, and y equals 0.0819, if x equals 0.6, y becomes 0.6389 and 0.0811, and if x equals 0.7, y becomes 0.8996 and 0.0804. This shows that there are two branches of the curve. The upper one does not pass through a maximum, but the lower one does. 7. A cylinder whose height is twice the radius of the base is increasing in volume, so that all its parts keep always in the same proportion to each other, that is, at any instant the cylinder is similar to the original cylinder. When the radius of the base is r feet, the surface area is increasing at the rate of 20 square inches per second. At what rate is its volume then increasing? Area equals S equals 2 times pi r squared plus 2 pi r times 2r equals 6 pi r squared. Volume equals V equals pi r squared times 2r equals 2 pi r cubed. ds over dr equals 12 pi r, dv over dr equals 6 pi r squared. ds equals 12 pi r dr equals 20, dr equals 20 over 12 pi r, dv equals 6 pi r squared dr equals 6 pi r squared times 20 over 12 pi r equals 10r. The volume changes at the rate of 10 r cubic inches. Make other examples for yourself. There are few subjects which offer such a wealth for interesting examples. End of section 20. This Made Easy by Silvanus P. Thompson. Section 21. Exercises 9. 1. What values of x will make y a maximum and a minimum if y equals x squared over x plus 1? Answer. Minimum, x equals 0, y equals 0. Maximum, x equals minus 2, y equals minus 4. 2. What value of x will make y a maximum in the equation? Y equals x over a squared plus x squared. Answer. X equals a. 3. A line of length p is to be cut up into 4 parts and put together as a rectangle. Show that the area of the rectangle will be a maximum if each of its sides is equal to 1/4 p. 4. A piece of string 30 inches long has its two ends joined together and is stretched by 3 pegs so as to form a triangle. What is the largest triangular area that can be enclosed by the string? Answer. 25√3 square inches. 5. Plot the curve corresponding to the equation y equals 10 over x add 10 over 8 minus x. Also find dy over dx and deduce the value of x that will make y a minimum and find that minimum value of y. Answer. Dy over dx equals minus 10 over x squared add 10 over open brackets 8 minus x close brackets squared. Minimum, x equals 4, y equals 5. 6. If y equals x to the power 5 minus 5x, find what values of x will make y a maximum or a minimum. Answer. Max for x equals minus 1, min for x equals 1. 7. What is the smallest square that can be inscribed in a given square? Answer. Join the middle points of the 4 sides. 8. Inscribe in a given cone, the height of which is equal to the radius of the base, a cylinder A, whose volume is a maximum, B, whose lateral area is a maximum, C, whose total area is a maximum. Answer. A. Radius equals 2 over 3r. B. Radius equals r over 2. C. No max. 9. Inscribe in a sphere a cylinder A, whose volume is a maximum, B, whose lateral area is a maximum, C, whose total area is a maximum. Answer. A. Radius equals r root 2/3. B. Radius equals r over root 2. C. Radius equals 0.8506 r. 10. A spherical balloon is increasing in volume if, when its radius is r feet, its volume is increasing at a rate of 4 cubic feet per second. At what rate is its surface then increasing? Answer. At a rate of 8 over r square feet per second. 11. Inscribe in a given sphere a cone whose volume is a maximum. Answer. Radius equals r root 8 over 3. 12. The current C, given by a battery of big N similar voltic cells, is C equals little n times E all over big R plus little n squared over big N, where E, big R, little r are constants, and little n is the number of cells coupled in series. Find the proportion of little n to big N. for which the current is greatest. Answer. Little n equals root big N, big R over little r. End of section 21. Calculus Made Easy by Silvanus P. Thompson. Chapter 12. Curvature of Curves. Returning to the process of successive differentiation, it may be asked, why does anybody want to differentiate twice over? We know that when the variable quantities are space and time, by differentiating twice over we get the acceleration of a moving body, and that in the geometrical interpretation, as applied to curves, dy over dx means the slope of the curve. But what can d2y over dx squared mean in this case? Clearly it means the rate, per unit length of x, at which the slope is changing. In brief, it is a measure of the curvature of the slope. Suppose a slope constant, as in figure 31. Note: Figure 31 shows a graph of a straight positive line with evenly spaced rectangles going up the line underneath. Here, dy over dx is of constant value. Suppose, however, a case in which, like figure 32, the slope itself is getting greater upwards than d open brackets dy over dx close brackets over dx, that is, d2y over dx squared will be positive. Note: Figure 32 shows a positively curved, positive line with evenly spaced rectangles underneath. As the line is curved, the difference in height is increasing for each subsequent rectangle. If the slope is becoming less as you go to the right, as in figure 33, then, even though the curve may be going upward, since the change is such as to diminish its slope, its d2y over dx squared will be negative. Note: Figure 33 shows a negatively curved positive line with the same even rectangles. As it is negatively curved, the difference in height is decreasing for the rectangles. It is now time to initiate you into another secret: how to tell whether the result that you get by equating to zero is a maximum or a minimum. The trick is this: after you have differentiated, so as to get the expression which you equate to zero, you then differentiate a second time and look whether the result of the second differentiation is positive or negative. If d2y over dx squared comes out positive, then you know that the value of y which you got was a minimum, but if d2y over dx squared comes out negative, then the value of y which you got out must be a maximum. That's the rule. The reason of it ought to be quite evident. Think of any curve that has a minimum point in it, like figure 34, where the point of minimum y is marked M and the curve is concave upwards. Note: Figure 34 shows a curve with a minimum labelled M. Before the minimum there is a downward pointing arrow, and after it there is an upward pointing arrow. To the left of M the slope is downward, that is, negative, and is getting less negative. To the right of M the slope has become upward and is getting more and more upward. Clearly the change of slope as the curve passes through M is such that d2y over dx squared is positive, for its operation, as x increases toward the right, is to convert a downward slope into an upward one. Similarly, consider any curve that has a maximum point in it, like figure 35, where the curve is convex and the maximum point is marked M. Note: 35 shows a curve with a maximum labelled M. Before the maximum there is an upward pointing arrow, and after it there is a downward pointing arrow. In this case, as the curve passes through M from left to right, its upward slope is converted into a downward or negative slope, so that in this case the slope of the slope, d2y over dx squared, is negative. Go back now to the examples of the last chapter and verify in this way the conclusions arrived at as to whether in any particular case there is a maximum or a minimum. You will find below a few worked out examples. 1. Find the maximum or minimum of a. Y equals 4x squared minus 9x minus 6. b. Y equals 6 add 9x minus 4x squared. And ascertain if it will be a maximum or a minimum in each case. A. dy over dx equals 8x minus 9 equals 0. X equals 1 1/8 and y equals minus 11.065. d2y over dx squared equals 8. It is positive, hence it is a minimum. B. dy over dx equals 9 minus 8x equals 0. X equals 1 1/8 and y equals 11.065. d2y over dx squared equals minus 8. It is negative, hence it is a maximum. 2. Find the maxima and minima of the function y equals x cubed minus 3x plus 16. dy over dx equals 3x squared minus 3 equals 0. X squared equals 1 and x equals plus minus 1. d2y over dx squared equals 6x. For x equals 1 it is positive. Hence x equals 1 corresponds to a minimum, y equals 14. For x equals minus 1 it is negative. Hence x equals minus 1 corresponds to a maximum, y equals 18. 3. Find the maxima and minima of y equals x minus 1 all over x squared plus 2. dy over dx equals open brackets x squared plus 2 close brackets times 1 minus open brackets x minus 1 close brackets times 2x all over open brackets x squared plus 2 close brackets squared equals 2x minus x squared plus 2 all over open brackets x squared plus 2 close brackets squared equals 0. Or x squared minus 2x minus 2 equals 0, whose solutions are x equals 2.73 and x equals minus 0.73. d2y over dx squared equals minus open brackets x squared plus 2 close brackets squared times open brackets 2x minus 2 close brackets minus open brackets x squared minus 2x minus 2 close brackets open brackets 4x cubed plus 8x close brackets all over open brackets x squared plus 2 close brackets to the power of 4 equals minus 2x to the power of 5 minus 6x to the power of 4 minus 8x cubed minus 8x squared minus 24x plus 8 all over open brackets x squared plus 2 close brackets to the power of 4. The denominator is always positive, so it is sufficient to ascertain the sign of the numerator. If we put x equals 2.73, the numerator is negative, the maximum y equals 0.183. If we put x equals minus 0.73, the numerator is positive, the minimum y equals minus 0.683. 4. The expense C of handling the products in a certain factory varies with the weekly output P according to the relation C equals AP add B over C add P add D, where A, B, C, D are positive constants. For output will the expense be least. dC over dP equals A minus B over open brackets C add P close brackets squared equals 0 for maximum or minimum. Hence A equals B over open brackets C add P close brackets, squared, and p equals plus minus square root of b over a minus c. As the output cannot be negative, p equals positive square root of b over a minus c. Now, d2c over dp squared equals b open brackets 2c add 2p close brackets all over open brackets c add p close brackets to the power of 4, which is positive for all the values of p, hence p equals positive square root b over a minus c corresponds to a minimum. 5. The total cost per hour c of lighting a building with n lamps of a certain kind is c equals n open brackets cl over t add EPCE over 1000 close brackets, where E is the commercial efficiency, watts per candle, P is the candle power of each lamp, T is the average life of each lamp in hours, CL the cost of renewal in pence per hour of use, CE the cost of energy per 1000 watts per hour. Moreover, the relation connecting the average life of a lamp with the commercial efficiency at which it is run is approximately T equals m e to the power of little n, where m and little n are constants depending on the kind of lamp. Find the commercial efficiency for which the total cost of lighting will be least. We have C equals n open brackets CL e to the power of minus little n over m add PCE e over 1000 close brackets. DC over DE equals PCE over 1000 minus little n CL e to the power of minus open brackets little n plus 1 close brackets over m equals 0 for maximum or minimum. E to the power of little n plus 1 equals 1000 times little n CL over MPCE, and E equals root to the little n plus 1 1000 times little n CL over MPCE. This is clearly for minimum, since d2c over de squared equals open brackets little n add 1 close brackets little n CL e to the power of minus open brackets little n add 2 close brackets over m, which is positive for a positive value of E. For a particular type of 16 candle power lamps, CL equals 17 pence, CE equals 5 pence, and it was found that m equals 10 and little n equals 3.6. E equals root to the 4.6 1000 times 3.6 times 17 over 10 times 16 times 5 equals 2.6 watts per candle power. End of section 22. Silvanus P. Thompson, section 23. Exercises 10. You are advised to plot the graph of any numerical example. 1. Find the maxima and minima of y equals x cubed plus x squared minus 10x plus 8. Answer. Max, x equals minus 2.19, y equals 24.19. Min, x equals 1.52, y equals minus 1.38. 2. Given y equals b over a x minus c x squared, find expressions for dy over dx and for d2y over dx squared. Also find the value of x which makes y a maximum or a minimum, and show whether it is maximum or minimum. Answer. dy over dx equals b over a minus 2cx. d2y over dx squared equals minus 2c. X equals b over 2ac, a maximum. 3. Find how many maxima and how many minima there are in the curve, the equation to which is y equals 1 minus x squared over 2 plus x to the power of 4 over 24, and how many in that of which the equation is y equals 1 minus x squared over 2, add x to the power of 4 over 24, minus x to the power of 6 over 720. Answers. A. 1 maximum and 2 minima. B. 1 maximum. X equals 0. Other points unreal. 4. Find the maxima and minima of y equals 2x add 1 add 5 over x squared. Answer. Min. X equals 1.71, y equals 6.14. 5. Find the maxima and minima of y equals 3 over x squared plus x plus 1. Answer. Max. X equals minus 0.5, y equals 4. 6. Find the maxima and minima of y equals 5x over 2 and x squared. Answer. Max. X equals 1.414, y equals 1.7675. Min. X equals minus 1.414, y equals 1.7675. 7. Find the maxima and minima of y equals 3x over x squared minus 3, add x over 2, add 5. Answer. Max. X equals minus 3.565, y equals 2.12. Min. X equals 3.565, y equals 7.88. 8. Divide a number n into two parts in such a way that 3 times the square of one part plus twice the square of the other part shall be a minimum. Answer. 0.4n, 0.6n. 9. The efficiency U of an electric generator at different values of output x is expressed by the general equation U equals x over a plus bx plus cx squared, where a is a constant depending chiefly on the energy losses in the iron, and c a constant depending chiefly on the resistance of the copper parts. Find an expression for that value of the output for which the efficiency will be a maximum. Answer. X equals root a over c. 10. Suppose it to be known that consumption of coal by a certain steamer may be represented by the formula y equals 0.3 add 0.001 v cubed, where y is the number of tons of coal burned per hour, and v is the speed expressed in nautical miles per hour. The cost of wages, interest on capital, and depreciation of that ship are together equal, per hour, to the cost of 1 ton of coal. What speed will make the total cost of a voyage of 1,000 nautical miles a minimum? And, if coal costs 10 shillings per ton, what will that minimum cost of the voyage amount to? Answer. Speed 8.66 nautical miles per hour. Time taken 115.47 hours. Minimum cost £112 and 12 shillings. 11. Find the maxima and minima of y equals plus minus x over 6 square root of x open brackets 10 minus x close brackets. Answer: max and min for x equals 7.5, y equals plus minus 5.414. 12. Find the maxima and minima of y equals 4x cubed minus x squared minus 2x plus 1. Answer: min x equals a half, y equals 0.25. Max x equals minus a third, y equals 1.408. End of section 23. A fraction, we have to perform a rather complicated operation, and, if the fraction is not itself a simple one, the result is bound to be a complicated expression. If we could split the fraction into two or more simpler fractions, such that their sum is equivalent to the original fraction, we could then proceed by differentiating each of these simpler expressions, and the result of differentiating would be the sum of two or more differentials, each one of which is relatively simple, while the final expression, though of course it will be the same as that which could be attained without resorting to this dodge, is thus obtained with much less effort and appears in a simplified form. Let us see how to reach this result. Try first the job of adding two fractions together to form a resultant fraction. Take, for example, the two fractions 1 over x add 1 and 2 over x minus 1. Every schoolboy can add these together and find their sum to be 3x add 1 all over x squared minus 1, and in the same way he can add together three or more fractions. Now this process can certainly be reversed, that is to say, that if this last expression were given, it is certain that it can somehow be split back again into its original components or partial fractions. Only we do not know in every case that may be presented to us how we can so split it. In order to find this out we shall consider a simple case at first, but it is important to bear in mind that all which follows applies only to what are called proper algebraic fractions, meaning fractions like the above, which have the numerator of a lesser degree than the denominator, that is, those in which the highest index of x is less in the numerator than in the denominator. If we have to deal with such an expression as x squared add 2 all over x squared minus 1, we can simplify it by division, since it is equivalent to 1 add 3 over x squared minus 1, and 3 over x squared minus 1 is a proper algebraic fraction to which the operation of splitting into partial fractions can be applied, as explained hereafter. Case 1. If we perform many additions of two or more fractions, the denominators of which contain only terms in x and no terms in x squared, x cubed, or any other powers of x, we always find that the denominator of the final resulting fraction is the product of the denominators of the fractions which were added to form the result. It follows that by factorising the denominator of this final fraction, we can find every one of the denominators of the partial fractions of which we are in search. Suppose we wish to go back from 3x add 1 all over x squared minus 1 to the components which we know are 1 over x add 1 and 2 over x minus 1. If we did not know what these components were, we can still prepare the way by writing 3x add 1 all over x squared minus 1 equals 3x add 1 all over open brackets x add 1 close brackets open brackets x minus 1 close brackets equals blank over x add 1 plus blank over x minus 1, leaving blank the places for the numerators until we know what to put there. We always may assume the sign between the partial fractions to be plus, since, if it be minus, we shall simply find the corresponding numerator to be negative. Now, since the partial fractions are proper fractions, the numerators are mere numbers without x at all, and we can call them a, b, c as we please. So in this case we have 3x add 1 all over x squared minus 1 equals a over x add 1 add b over x minus 1. If now we perform the addition of these two partial fractions, we get a open brackets x minus 1 close brackets add b open brackets x add 1 close brackets all over open brackets x add 1 close brackets open brackets x minus 1 close brackets, and this must be equal to 3x add 1 all over open brackets x plus 1 close brackets open brackets x minus 1 close brackets. And as the denominators in these two expressions are the same, the numerators must be equal, giving us 3x add 1 equals a open brackets x minus 1 close brackets add b open brackets x add 1 close brackets. Now this is an equation with two unknown quantities, and it would seem that we need another equation before we can solve them and find a and b. But there is another way out of this difficulty. The equation must be true for all values of x, therefore it must be true for such values of x as will cause x minus 1 and x plus 1 to become 0, that is, for x equals 1 and for x equals minus 1 respectively. If we make x equals 1, we get 4 equals a times 0 add b times 2, so that b equals 2. And if we make x equals minus 1, we get minus 2 equals a times minus 2 add b times 0, so that a equals 1. Replacing the a and b of the partial fractions by these new values, we find them to become 1 over x add 1 and 2 over x minus 1, and the thing is done. As a farther example, let us take the fraction 4x squared add 2x minus 14 all over x cubed add 3x squared minus x minus 3. The denominator becomes 0 when x is given the value 1, hence x minus 1 is a factor of it, and obviously then the other factor will be x squared add 4x add 3, and this again can be decomposed into open brackets x add 1 close brackets open brackets x add 3 close brackets. So we may write the fraction thus: 4x squared add 2x minus 14 all over x cubed add 3x squared minus x minus 3 equals a over x plus 1 add b over x minus 1 add c over x plus 3, making three partial factors. Proceeding as before, we find 4x squared add 2x minus 14 equals a open brackets x minus 1 close brackets open brackets x add 3 close brackets add b open brackets x add 1 close brackets open brackets x add 3 close brackets add c open brackets x add 1 close brackets open brackets x minus 1 close brackets. Now if we make x equals 1, we get minus 8 equals a times 0 add b open brackets 2 times 4 close brackets add c times 0, that is b equals minus 1. If x equals minus 1, we get minus 12 equals a open brackets minus 2 times 2 close brackets add b times 0 add c times 0, whence a equals 3. If x equals minus 3, we get 16 equals a times 0 add b times 0 add c open brackets minus 2 times minus 4 close brackets, whence c equals 2. So then the partial fractions are 3 over x plus 1 minus 1 over x minus 1 add 2 over x plus 3, which is far easier to differentiate with respect to x than the complicated expression from which it is derived. Case 2. If some of the factors of the denominator contain terms in x squared, and are not conveniently put into factors, then the corresponding numerator may contain a term in x as well as a simple number, and hence it becomes necessary to represent this unknown numerator not by the symbol a, but by ax add b, the rest of the calculation being made as before. Try, for instance, minus x squared minus 3 all over open brackets x squared add 1 close brackets open brackets x add 1 close brackets. Minus x squared minus 3 all over open brackets x squared add 1 close brackets open brackets x plus 1 close brackets equals ax add b all over x squared add 1 add c over x add 1. Minus x squared minus 3 equals open brackets ax add b close brackets open brackets x add 1 close brackets add c open brackets x squared add 1 close brackets. Putting x equals minus 1 we get minus 4 equals c times 2 and c equals minus 2, hence x squared minus 3 equals open brackets ax add b close brackets open brackets x add 1 close brackets minus 2x squared minus 2 and x squared minus 1 equals ax open brackets x add 1 close brackets add b open brackets x add 1 close brackets. Putting x equals 0 we get minus 1 equals b, hence x squared minus 1 equals ax open brackets x add 1 close brackets minus x minus 1, or x squared add x equals ax open brackets x add 1 close brackets, and x add 1 equals a open brackets x add 1 close brackets, so that a equals 1, and the partial fractions are x minus 1 all over x squared add 1 minus 2 over x plus 1. Take as another example the fraction x cubed minus 2 all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets. We get x cubed minus 2 all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets equals ax add b all over x squared add 1 add cx add d all over x squared plus 2 equals open brackets ax add b close brackets open brackets x squared add 2 close brackets add open brackets cx add d close brackets open brackets x squared plus 1 close brackets all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets. In this case the determination of a, b, c, d is not so easy. It will be simpler to proceed as follows. Since the given fraction and the fraction found by adding the partial fractions are equal, and have identical denominators, the numerators must be identically the same. In such a case, and for such algebraic expressions as those with which we are dealing here, the coefficients of the same powers of x are equal and of same sign. Hence, since x cubed minus 2 equals open brackets ax add b close brackets open brackets x squared add 2 close brackets add open brackets cx add d close brackets open brackets x squared add 1 close brackets equals open brackets a add c close brackets x cubed add open brackets b add d close brackets x squared add open brackets 2a add c close brackets x add 2b add d. We have 1 equals a add c, 0 equals b add d, the coefficient of x squared in the left expression being 0, 0 equals 2a add c, and minus 2 equals 2b add d. Here are four equations from which we readily obtain a equals minus 1, b equals minus 2, c equals 2, and d equals 0, so that the partial fractions are 2 open brackets x add 1 close brackets over x squared add 2 minus x add 2 all over x squared add 1. This method can always be used, but the method shown first will be found the quickest in the case of factors in x only. Case 3. When, among the factors of the denominator, there are some which are raised to some power, one must allow for the possible existence of partial fractions having for denominator the several powers of that factor up to the highest. For instance, In splitting the fraction, 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets, we must allow for the possible existence of a denominator x add 1 as well as open brackets x add 1 close brackets squared and x minus 2. It may be thought, however, that since the numerator of the fraction, the denominator of which is open brackets x add 1 close brackets squared, may contain terms in x, we must allow for this in writing ax add b for its numerator, so that 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals ax add b all over open brackets x add 1 close brackets squared add c over x add 1 add d over x minus 2. If, however, we try to find a, b, c and d in this case, we fail, because we get 4 unknowns and we only have 3 relations connecting them. Yet 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals x minus 1 all over open brackets x add 1 close brackets squared add 1 over x add 1 add 1 over x minus 2. But if we write 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals a over open brackets x add 1 close brackets squared add b over x add 1 add c over x minus 2, we get 3x squared minus 2x add 1 equals a open brackets x minus 2 close brackets add b open brackets x add 1 close brackets open brackets x minus 2 close brackets add c open brackets x add 1 close brackets squared, which gives c equals 1 for x equals 2. Replacing c with its value, transposing, gathering like terms and dividing by x minus 2, we get minus 2x equals a add b open brackets x add 1 close brackets, which gives a equals minus 2 for x equals minus 1. Replacing a with its value, we get 2x equals minus 2 add b open brackets x add 1 close brackets, hence b equals 2, so that the partial fractions are 2 over x add 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2, instead of 1 over x add 1 add x minus 1 all over open brackets x add 1 close brackets squared add 1 over x minus 2, stated above as being the fraction from which 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets was obtained. The mystery is cleared if we observe that x minus 1 all over open brackets x add 1 close brackets squared can itself be split into the two fractions 1 over x add 1 minus 2 over open brackets x add 1 close brackets squared, so that the three fractions given are really equivalent to 1 over x add 1 plus 1 over x add 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2 equals 2 over x plus 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2, which are the partial fractions obtained. We see that it is sufficient to allow for one numerical term in each numerator, and that we always get the ultimate partial fractions. When there is a power of a factor of x squared in the denominator, however, the corresponding numerators must be of the form ax add b, for example, 3x minus 1 all over open brackets 2x squared minus 1 close brackets squared open brackets x add 1 close brackets equals ax add b all over open brackets 2x squared minus 1 close brackets squared add cx add d all over 2x squared minus 1 add e over x add 1, which gives 3x minus 1 equals open brackets ax add b close brackets open brackets x add 1 close brackets add open brackets cx add d close brackets open brackets x add 1 close brackets open brackets 2x squared minus 1 close brackets add e open brackets 2x squared minus 1 close brackets squared. For x equals minus 1, this gives e equals minus 4. Replacing, transposing, collecting like terms, and dividing by x add 1, we get 16x cubed minus 16x squared add 3 equals 2cx cubed add 2dx squared add x open brackets a minus c close brackets add open brackets b minus d close brackets. Hence 2c equals 16 and c equals 8. 2d equals minus 16 and d equals minus 8. A minus c equals 0, or a minus 8 equals 0, and a equals 8. And finally, b minus d equals 3, or b equals minus 5. So that we obtain as the partial fractions 8x minus 5 all over open brackets 2x squared minus 1 close brackets squared add 8 open brackets x minus 1 close brackets over 2x squared minus 1 minus 4 over x add 1. It is useful to check the results obtained. The simplest way is to replace x by a single value, say plus 1, both in the given expression and in the partial fractions obtained. Whenever the denominator contains but a power of a single factor, a very quick method is as follows. Taking, for example, 4x add 1 all over open brackets x add 1 close brackets cubed, let x add 1 equal z, then x equals z minus 1. Replacing, we get 4 open brackets z minus 1 close brackets add 1 all over z cubed equals 4z minus 3 all over z cubed equals 4 over z squared minus 3 over z cubed. The partial fractions are, therefore, 4 over open brackets x add 1 close brackets squared minus 3 over open brackets x add 1 close brackets cubed. Application to differentiation. Let it be required to differentiate y equals 5 minus 4x all over 6x squared plus 7x minus 3. We have dy over dx equals minus open brackets 6x squared plus 7x minus 3 close brackets times 4 add open brackets 5 minus 4x close brackets open brackets 12x add 7 close brackets all over open brackets 6x squared add 7x minus 3 close brackets squared equals 24x squared minus 60x minus 23 all over open brackets 6x squared add 7x minus 3 close brackets squared. If we split the given expression into 1 over 3x minus 1 minus 2 over 2x add 3, we get, however, dy over dx equals minus 3 over open brackets 3x minus 1 close brackets squared add 4 over open brackets 2x add 3 close brackets squared, which is really the same result as above split into partial fractions, but the splitting, if done after differentiating, is more complicated, as will easily be seen. When we shall deal with the integration of such expressions, we shall find the splitting into partial fractions a precious auxiliary. End of section 24. Exercises 11. Split into fractions. 1. 3x add 5 all over open brackets x minus 3 close brackets open brackets x add 4 close brackets. Answer. 2 over x minus 3 add 1 over x add 4. 2. 3x minus 4 all over open brackets x minus 1 close brackets open brackets x minus 2, close brackets. Answer. 1 over x minus 1 add 2 over x minus 2. 3. 3x add 5 all over x squared add x minus 12. Answer. 2 over x minus 3 add 1 over x add 4. 4. X add 1 all over x squared minus 7x add 12. Answer. 5 over x minus 4 minus 4 over x minus 3. 5. X minus 8 all over, open brackets, 2x add 3, close brackets, open brackets, 3x minus 2, close brackets. Answer. 19 over 13, open brackets, 2x add 3, close brackets, minus 22 over 13, open brackets, 3x minus 2, close brackets. 6. X squared minus 13x add 26, all over, open brackets, x minus 2, close brackets, open brackets, x minus 3, close brackets, open brackets, x minus 4, close brackets. Answer. 2 over x minus 2, add 4 over x minus 3, minus 5 over x minus 4. 7. X squared minus 3x add 1, all over, open brackets, x minus 1, close brackets, open brackets, x add 2, close brackets, open brackets, x minus 3, close brackets. Answer. 1 over 6, open brackets, x minus 1, close brackets, add 11 over 15, open brackets, x add 2, close brackets, add 1 over 10, open brackets, x minus 3, close brackets. 8. 5x squared add 7x add 1, all over, open brackets, 2x add 1, close brackets, open brackets, 3x minus 2, close brackets, open brackets, 3x add 1, close brackets. Answer. 7 over 9, open brackets, 3x add 1, close brackets, add 71 over 63, open brackets, 3x minus 2, close brackets, minus 5 over 7, open brackets, 2x add 1, close brackets. 9. X squared over x cubed minus 1. Answer. 1 over 3, open brackets, x minus 1, close brackets, add 2x add 1, all over 3, open brackets, x squared add x add 1, close brackets. 10. X to the power 4 add 1, all over x cubed add 1. Answer. X add 2 over 3, open brackets, x add 1, close brackets, add 1 minus 2x, all over 3, open brackets, x squared minus x add 1, close brackets. 11. 5x squared add 6x add 4, all over, open brackets, x add 1, close brackets, open brackets, x squared add x add 1, close brackets. Answer. 3 over x add 1 add 2x add 1, all over x squared add x add 1. 12. X over, open brackets, x minus 1, close brackets, open brackets, x minus 2, close brackets, squared. Answer. 1 over x minus 1 minus 1 over x minus 2 add 2 over, open brackets, x minus 2, close brackets, squared. 13. X over, open brackets, x squared minus 1, close brackets, open brackets, x add 1, close brackets. Answer. 1 over 4, open brackets, x minus 1, close brackets, minus 1 over 4, open brackets, x add 1, close brackets, add 1 over 2, open brackets, x add 1, close brackets, squared. 14. X add 3, all over, open brackets, x add 2, close brackets, squared, open brackets, x minus 1, close brackets. Answer. 4 over 9 open brackets x minus 1 close brackets minus 4 over 9 open brackets x add 2 close brackets minus 1 over 3 open brackets x add 2 close brackets squared. 15. 3x squared add 2x add 1 all over open brackets x add 2 close brackets open brackets x squared add x add 1 close brackets squared. Answer 1 over x add 2 minus x minus 1 all over x squared add x add 1 minus 1 over open brackets x squared add x add 1 close brackets squared. 16. 5x squared add 8x minus 12 all over open brackets x add 4 close brackets cubed. Answer 5 over x add 4 minus 32 over open brackets x add 4 close brackets squared add 36 over open brackets x add 4 close brackets cubed. 17. 7x squared add 9x minus 1 all over open brackets 3x minus 2 close brackets to the power 4. Answer 7 over 9 open brackets 3x minus 2 close brackets squared add 55 over 9 open brackets 3x minus 2 close brackets cubed add 73 over 9 open brackets 3x minus 2 close brackets to the power 4. 18. X squared over open brackets x cubed minus 8 close brackets open brackets x minus 2 close brackets. Answer 1 over 6 open brackets x minus 2 close brackets add 1 over 3 open brackets x minus 2 close brackets squared minus x over 6 open brackets x squared plus 2x plus 4 close brackets. End of section 25. With a function y equals 3x, it can be expressed in the form x equals y over 3. This latter form is called the inverse function to the one originally given. If y equals 3x, dy over dx equals 3. If x equals y over 3, dx over dy equals 1/3. And we see that dy over dx equals 1 over dx over dy, or dy over dx times dx over dy equals 1. Consider y equals 4x squared. Dy over dx equals 8x. The inverse function is x equals y to the power of half over 2. And dx over dy equals 1 over 4 square root y equals 1 over 4 times 2x equals 1 over 8x. Here again, dy over dx times dx over dy equals 1. It can be shown that for all functions which can be put into the inverse form, one can always write dy over dx times dx over dy equals 1, or dy over dx equals 1 over dx over dy. It follows that, being given a function, if it be easier to differentiate the inverse function, this may be done, and the reciprocal of the differential coefficient of the inverse function gives the differential coefficient of the given function itself. As an example, suppose that we wish to differentiate y equals the square root of 3 over x minus 1. We have seen one way of doing this, by writing u equals 3 over x minus 1 and finding dy over du and du over dx. This gives dy over dx equals minus 3 over 2x squared square root of 3 over x minus 1. If we had forgotten how to proceed by this method, or wished to check our result by some other way of obtaining the differential coefficient, or for any other reason we could not use the ordinary method, we can proceed as follows. The inverse function is 3 over 1 add y squared. Dx over dy equals minus 3 times 2y over open brackets 1 add y squared close brackets squared equals minus 6y over open brackets 1 add y squared close brackets squared. Hence dy over dx equals 1 over dx over dy equals minus open brackets 1 add y squared close brackets squared over 6y equals minus open brackets 1 add 3 over x minus 1 close brackets squared all over 6 times the square root of 3 over x minus 1 equals minus 3 over 2x squared square root 3 over x minus 1. Let us take as another example y equals 1 over cube root of theta add 5. The inverse function is theta equals 1 over y cubed minus 5, or theta equals y to the power of minus 3 minus 5, and d theta over dy equals minus 3y to the power of minus 4 equals minus 3 cube root of open brackets theta add 5 close brackets to the power 4. It follows that dy over d theta equals minus 1 over 3 times the square root of open brackets theta add 5 close brackets to the power 4, as might have been found otherwise. We shall find this dodge most useful later on. Meanwhile, you are advised to become familiar with it by verifying by its means the results obtained in exercises 1, page 24, numbers 5, 6, 7, examples, page 67, numbers 1, 2, 4, and exercises 6, page 72, numbers 1, 2, 3, and 4. You will surely realise from this chapter and the preceding that in many respects the calculus is an art rather than a science, an art only to be acquired, as all other arts are, by practice. Hence you should work many examples, and set yourself other examples, to see if you can work them out, until the various artifices become familiar by use. End of section 26.
Reading by Paul King, pjk.scripts.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On the True Compound Interest and the Law of Organic Growth, Part 1a. Let there be a quantity growing in such a way that the increment of its growth during a given time shall always be proportional to its own magnitude. This resembles the process of reckoning interest on money at some fixed rate, for the bigger the capital, the bigger the amount of interest on it in a given time. Now we must distinguish clearly between two cases in our calculation according as the calculation is made by what the arithmetic books call simple interest, or by what they call compound interest. For in the former case the capital remains fixed, while in the latter the interest is added to the capital, which therefore increases by successive additions. 1. At simple interest. Consider a concrete case. Let the capital at start be £100, and then the rate of interest be 10% per annum. Then the increment to the owner of the capital will be £10 every year. Let him go on drawing his interest every year and hoard it by putting it by in a stocking or locking it up in his safe. Then if he goes on for 10 years, by the end of that time he will have received 10 increments of £10 each, or £100, making, with the original 100, a total of £200 in all. His property would have doubled itself in 10 years. If the rate of interest had been 5%, he would have had to hoard it for 20 years to double his property. If it had been only 2%, he would have had to hoard it for 50 years. It is easy to see that if the value of the yearly interest is 1 over n of the capital, he must go on hoarding for n years in order to double his property. Or if y be the original capital and the yearly interest is y over n, then at the end of n years his property will be y plus n times y over n equals 2y. 2. At compound interest. As before, let the owner begin with a capital of £100, earning interest at the rate of 10% per annum, but instead of hoarding the interest, Let it be added to the capital each year so that the capital grows year by year. Then at the end of 1 year the capital will have grown to £110. And in the second year, still at 10%, this will earn £11 interest. He will start the third year with £121, and the interest on that will be £12 2 shillings, so that he starts the fourth year with £133 2 shillings, and so on. It is easy to work it out, and to find that at the end of the 10 years the total capital would have grown to £259 7 shillings 6 pence. In fact, we see that at the end of each year, each pound would have earned 1/10 of a pound, and therefore, if this is always added on, each year multiplies the capital by 11/10, and if continued for 10 years, which will multiply by this factor 10 times over, we will multiply the original capital by 2.59374. Let us put this into symbols. Put y0 for the original capital, 1/n for the fraction added on at each of the n operations, and y sub n for the value of the capital at the end of the nth operation. Then y sub n equals y0 multiplied by open bracket 1 plus 1/n close bracket raised to the power n. But this mode of reckoning compound interest once a year is really not quite fair, for even during the first year the £100 ought to have been growing. At the end of half a year it ought to have been at least £105, and certainly it would have been fairer had the interest for the second half of the year been calculated on £105. This would be equivalent to calling it 5% per half year with 20 operations, therefore at each of which the capital is multiplied by 21/20. If reckoned this way, by the end of 10 years the capital would have grown to £265 6 shillings 7 pence for open bracket 1 plus 1/20 close bracket to the power 20 equals 2.653. But even so, this process is still not quite fair, for by the end of the first month there will be some interest earned, and a half yearly reckoning assumes that the capital remains stationary for 6 months at a time. Suppose we divided the year into 10 parts and reckon a 1% interest for each 10th of the year. We now have 100 operations lasting over 10 years, or y sub n equals £100 multiplied by open bracket 1 plus 1/100 close bracket to the power 100, which works out to £270 9 shillings 7½ pence. Even this is not final. Let the 10 years be divided into 1,000 periods, each of 1/100th of a year, the interest being 1/10% for each period. Then y sub n equals £100 multiplied by open bracket 1 plus 1/1000 close bracket raised to the power of 1000, which works out to £271 13 shillings 10 pence. Go even more minutely and divide the 10 years into 10,000 parts, each of 1/1000th of a year, with interest at 1/100th of 1%. Then y sub n equals £100 multiplied by open bracket 1 plus 1/10,000 close bracket to the power of 10,000, which amounts to £271 16 shillings and 3½ pence. Finally, it will be seen that what we are trying to find in reality is the ultimate value of the expression 1 plus 1/n raised to the power n, which, as we see, is greater than 2, and which, as we take n larger and larger, grows closer and closer to a particular limiting value. However big you make n, the value of this expression grows nearer and nearer to the figure 2.71828, and so on, a number never to be forgotten. Let us take geometrical illustrations of these things. In figure 36, OP stands for the original value. OT is the whole time during which the value is growing. It is divided into 10 periods, in each of which there is an equal step up. Here dy by dx is a constant, and if each step up is 1/10 of the original OP, then by 10 such steps the height is doubled. If we had taken 20 steps, each of half the height shown, at the end the height would still be just doubled, or n such steps, each of 1/n, the original height OP, would suffice to double the height. This is the case of simple interest. Here is 1 growing until it becomes 2. In figure 37, we have the corresponding illustration of the geometrical progression. Each of the successive ordinates is to be 1 plus 1/n, that is, n plus 1/n times as high as its predecessor. The steps up are not equal, because each step up is now 1/n of the ordinate of that part of the curve. If we had literally 10 steps, with 1 plus 1/10 for the multiplying factor, the final total would be open bracket 1 plus 1/10 close bracket to the power 10, or 2.594 times the original 1. But if we only take n sufficiently large and the corresponding 1/n sufficiently small, then the final value open bracket 1 plus 1/n close bracket raised to the power n, to which unity will grow to be 2.71828. Epsilon. To this mysterious number 2.7182818, etc., the mathematicians have assigned as a symbol the Greek letter epsilon. All schoolboys know that the Greek letter pi stands for 3.141592, etc., but how many of them know that epsilon means 2.71828? Yet it is an even more important number than pi. What then is epsilon? Suppose we were to let 1 grow at simple interest till it became 2. Then, if at the same nominal rate of interest and for the same time we were to let 1 grow at a true compound interest instead of simple, it would grow to the value epsilon. This process of growing proportionately at every instant to the magnitude of that instant some people call a logarithmic rate of growing. Unit logarithmic rate of growth is that rate which in unit time will cause 1 to grow to 2.718281. It might also be called the organic rate of growing, because it is characteristic of organic growth, in certain circumstances, that the increment of the organism in a given time is proportional to the magnitude of the organism itself. If we take 100% as the unit of rate, and any fixed period as the unit of time, then the result of letting 1 grow arithmetically at unit rate for unit time will be 2, while the result of letting 1 grow logarithmically at unit rate for the same time will be 2.71828, and so on. A little more about epsilon. We have seen that we require to know what value is reached by the expression open bracket 1 plus 1/n close bracket to the power n, where n becomes indefinitely great. Arithmetically, here are tabulated a lot of values which anyone can calculate out by the help of an ordinary table of logarithms, got by assuming n equals 2, n equals 5, n equals 10, and so on, up to n equals 10,000. Open bracket 1 plus 1/2 close bracket to the power 2 equals 2.25. Open bracket 1 plus 1/5 close bracket to the power 5 equals 2.488. Open bracket 1 plus 1/10 close bracket to the power 10 equals 2.594. Open bracket 1 plus 1/20 close bracket to the power 20 equals 2.653. Open bracket 1 plus 1/100 close bracket to the power 100 equals 2.705. Open bracket 1 plus 1/1000 close bracket to the power of 1000 equals 2.7169. 1 plus 1/10 10,000 close bracket to the power 10,000 equals 2.7181. It is, however, worthwhile to find another way of calculating this immensely important figure. Accordingly, we will avail ourselves of the binomial theorem and expand the expression open bracket 1 plus 1 over n close bracket to the power n in that well-known way. The binomial theorem gives the rule that open bracket a plus b close bracket to the power n equals a to the n plus n choose 1 times a to the power n minus 1 times b plus n choose 2 times a to the power n minus 2b squared plus n choose 3 times a to the power n minus 3b cubed plus etc. Putting a equals 1 and b equals 1 over n, we get open bracket 1 plus 1 over n close bracket to the power n equals 1 plus 1 plus n choose 2 times 1 over n squared plus n choose 3 times 1 over n cubed plus n choose 4 times 1 over n to the power 4, and so on. Now if we suppose n to become indefinitely great, say a billion or a billion billions, then n minus 1, n minus 2, and n minus 3, etc. will all be sensibly equal to n, and then the series becomes epsilon equals 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, etc. By taking this rapidly convergent series to as many terms as we please, we can work out the sum to any desired point of accuracy. Here is the working for 10 terms. 1.000000. Dividing by 1, we get the same thing, 1 followed by a decimal point and 6 zeros. Dividing by 2, we get 0 followed by a decimal point, then a 5 and 5 zeros. Dividing by 3, 0.166667. Dividing by 4, 0.041667. Dividing by 5, 0.008333. Dividing by 6, 0.001389. Dividing by 7, 0.000198. Divided by 8, 0.000025. And finally, dividing by 9, 0.000002. And when we add these numbers up, the total becomes 2.718281. Epsilon is incommensurable with 1 and resembles pi in being an interminable non-recurrent decimal. The exponential series. We shall have need of yet another series. Let us again, making use of the binomial theorem, expand the expression open bracket 1 plus 1 over n close bracket to the power n times x, which is the same as epsilon to the power x when we make n indefinitely great. Epsilon to the power x equals 1 to the power nx plus nx choose 1 times 1 over n plus nx choose 2 times 1 over n squared plus nx choose 3 times 1 over n cubed plus and so on. When this is expanded without simplifying, 1 plus x plus 1 over 2 factorial multiplied by the fraction in the numerator n squared x squared minus nx, and in the denominator n squared, plus the next term 1 over 3 factorial multiplied by the fraction in the numerator n cubed x cubed minus 3n squared x squared plus 2nx divided by in the denominator n cubed plus and so on equals 1 plus x plus the fraction in the numerator x squared minus x over n, and in the denominator 2 factorial plus the fraction in the numerator x cubed minus 3x squared over n plus 2x over n squared divided by in the denominator 3 factorial plus etc. But when n is made infinitely great, this simplifies down to the following. e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on. This series is called the exponential series. The great reason why epsilon is regarded of importance is that epsilon to the power x possesses a property not possessed by any other function of x, that when you differentiate its value remains unchanged. In other words, its differential coefficient is the same as itself. This can be seen instantly by differentiating it with respect to x thus. d to the x by dx equals 0 plus 1 plus 2x over 2 factorial plus 3x squared over 3 factorial plus 4x cubed over 4 factorial plus 5x to the fourth over 5 factorial, etc., which equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc., which is exactly the same as the original series. End of section 27. Read by Paul King, Mississauga, Ontario, pjk.scripps.mit.edu/pkj. By Paul King, pjk.scripps.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On True Compound Interest and the Law of Organic Growth, Part 1b. Now we might have gone to work the other way and said, let's find a function of x such that its differential coefficient is the same as itself. Or, is there any expression involving only powers of x which is unchanged by differentiation? Accordingly, let us assume, as a general expression, that y equals a plus bx plus cx squared plus dx cubed plus ex fourth, etc., in which the coefficients a, b, c, d, and e, and so on, will have to be determined, and differentiated. dy by dx would then equal b plus 2cx plus 3dx squared plus 4ex cubed, etc. Now, if this new expression is really to be the same as that from which it was derived, it is clear that a must equal b, that c equals b over 2, which also equals a over 1 times 2, and that d equals c over 3, which also equals a over 3 factorial, and that e equals d over 4, which is also equal to a over 4 factorial. And the law of change is therefore that y equals a outside the bracket 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on, close bracket. If now we take a equals 1 for the sake of further simplicity, we have y equals 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. Differentiating at any number of times will give always the same series over and over again. If now we take the particular case of a equals 1 and evaluate the series, we shall get simply when x equals 1, y equals 2.718281, etc., that is y equals epsilon. When x equals 2, y equals 2.718281, etc., squared, that is y equals epsilon squared, and when x equals 3, y equals 2.718281, etc., cubed, that is y equals epsilon cubed. And therefore, when x equals x, y equals 2.71281, etc., to the power x, that is y equals epsilon to the power x. Thus finally demonstrating that epsilon to the x power plus 1 over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. Note how to read exponentials. For the benefit of those who have no tutor at hand, it may be of use to state that epsilon to the power x is read as epsilon to the xth power, or some people read it exponential x. So epsilon to the power pt is read epsilon to the ptth power, or exponential pt. Take some similar expressions. Thus, epsilon to the power minus 2 is read epsilon to the minus 2 power, or exponential minus 2. Epsilon to the power minus ax is read epsilon to the minus axth, or exponential minus ax. Of course, it follows that epsilon to the power y remains unchanged if differentiated with respect to y. Also, epsilon to the power ax, which is equal to open bracket epsilon to the power a close bracket to the power x, will, when differentiated with respect to x, be a multiplied by epsilon to the power ax, because a is a constant. Natural or Naperian logarithms. Another reason why epsilon is important is because it was made by Napier, the inventor of logarithms, the basis of his system. If y is the value of epsilon to the power x, then x is the logarithm to the base epsilon of y. Or if y equals epsilon to the power x, then x equals log base epsilon of y. The two curves plotted in figures 38 and 39 represent these equations. The first curve, figure 38, has the graph plotted by the following xy coordinates. The point x equals 0, y equals 1, the point x equals 0.5, y equals 1.65, the point x equals 1, y equals 2.71, the point x equals 1.5, y equals 4.5, and the point x equals 2, y equals 7.39. For the second graph in figure 39, it possesses the points x equals 0, y equals 1, which you notice is the reverse of the first point of the last graph, x equals 0.69, y equals 2, x equals 1.1, y equals 3, x equals 1.39, y equals 4, x equals 2.08, y equals 8. It will be seen that, though the calculations yield different points for plotting, yet the result is identical. The two equations really mean the same thing. As many persons who use ordinary logarithms, which are calculated to base 10 instead of base epsilon, are unfamiliar with the natural logarithms, it may be worthwhile to say a word about them. The ordinary rule that adding logarithms gives logarithms of the product still holds good, or log base epsilon of a plus log base epsilon of b equals log base epsilon of a times b. Also, the rule of powers holds good. N multiplied by the log base epsilon of a equals log base epsilon of a to the power n. But as 10 is no longer the basis, one cannot multiply by 100 or 1000 by merely adding 2 or 3 to the index. One can change the natural logarithm to the ordinary logarithm simply by multiplying it by 0.4343, or log base 10 of x equals 0.4343 log base epsilon of x, and conversely log base epsilon of x equals 2.3026 multiplied by log base 10 of x. A useful table of Naperian logarithms, also called natural logarithms or hyperbolic logarithms. Natural log of 1, 0. Natural log of 1.1, 0.0953. Natural log of 1.2, 0.1823. Natural log of 1.5, 0.4055. Natural log of 1.7, 0.5306. Natural log of 2.0, 0.6931. Natural log of 2.2, 0.7885. Natural log of 2.5, 0.9163. Natural log of 2.7, 0.9933. Natural log of 2.8, 1.0296. Natural log of 3.0, 1.0986, natural log of 3.5, 1.2528, natural log of 4.0, 1.3863, natural log of 4.5, 1.5041, natural log of 5.0, 1.6094, natural log of 6, 1.7918, natural log of 7, 1.9459, natural log of 8, 2.0794, natural log of 9, 2.1972, natural log of 10, 2.3026, natural log of 20, 2.9957, natural log of 50, 3.9120, natural log of 100, 4.6052, natural log of 200, 5.2983, natural log of 500, 6.2146, natural log of 1000, 6.9078, natural log of 2000, 7.6009, natural log of 5000, 8.5172, natural log of 10,000, 9.2103, natural log of 20,000, 9.9035. Exponential and logarithmic equations. Now let us try our hands at differentiating certain expressions that contain logarithms or exponentials. Take the equation y equals log base epsilon x. First transform this into epsilon to the power y equals x. Whence, since the differential of epsilon to the power y with regard to y is the original function unchanged, dx by dy equals epsilon to the power y. And reverting from the inverse to the original function, dy by dx equals 1 over dx by dy equals 1 over e to the power y equals 1 over x. Now this is a very curious result. It may be written d of log base epsilon x by dx equals x to the power minus 1. Note that x to the minus 1 is a result that we could never have got by the rule for differentiating powers. That rule is to multiply by the power and reduce the power by 1. Thus differentiating x cubed gave us 3x squared, and differentiating x squared gave us 2x to the power 1. But differentiating x to the 0 does not give us x to the power minus 1, or 0 times x to the power minus 1, because x to the power 0 is itself 1 and is a constant. We shall have to come back to this curious fact that differentiating log base epsilon x gives us 1 over x when we reach the chapter on integrating. Now try to differentiate y equals log base epsilon of the binomial x plus a. That is, e to the power y equals x plus a. We have d of x plus a by dy equals epsilon to the power y. Since the differential of epsilon to the power y remains epsilon to the power y, this gives dx by dy equals epsilon to the power y equals x plus a. Hence, reverting to the original function, we get dy by dx equals 1 over dx by dy equals 1 over x plus a. Next try y equals log base 10 of x. First change to natural logarithms by multiplying by the modulus 0.4343. This gives us y equals 0.4343 log base epsilon of x, whence dy by dx equals 0.4343 divided by x. The next thing is not quite so simple. Try this. Y equals a to the power x. Taking the logarithm of both sides, we get log base epsilon y equals x multiplied by log base epsilon of a. So x equals log base epsilon of y divided by log base epsilon of a, which equals 1 over log base epsilon a multiplied by log base epsilon y. Since 1 over log base epsilon a as a constant, we get dx by dy, which equals 1 over log base epsilon of a multiplied by 1 over y equals 1 over open bracket a to the power x times log base epsilon of a close bracket. Hence, reverting to the original function, dy by dx equals 1 over dx by dy equals a to the x multiplied by log base epsilon a. We see that since dx by dy multiplied by dy by dx equals 1 and dx by dy equals 1 over y multiplied by 1 over log base epsilon a, 1 over y multiplied by dy by dx equals log base epsilon a. We shall find that whenever we have an expression such as log base epsilon y equals a function of x, we always have 1 over y multiplied by dy by dx equals the differential coefficient of the function of x, so that we could have written it at once from log base epsilon y equals x multiplied by log base epsilon of a. 1 over y dy by dx equals log base epsilon a, and dy by dx equals a to the x multiplied by log base epsilon of a. Let us now attempt further examples. Example 1. Y equals epsilon to the power negative ax. Let negative ax equal z, then y equals epsilon to the power z. dy by dx equals epsilon to the power z. dz by dx equals negative a. Hence, dy by dx equals negative a epsilon to the power negative ax. Or thus, log base epsilon to the power y equals negative ax. 1 over y multiplied by dy by dx equals negative a. dy by dx equals negative ay equals negative a epsilon to the power negative ax. Example 2. Y equals epsilon raised to the power x squared over 3. Let x squared over 3 equal z, then y equals epsilon to the power z. dy by dz is epsilon to the power z. dz by dx equals 2x over 3. dy by dx equals 2x over 3 multiplied by epsilon raised to the power x squared over 3. Or thus, log base epsilon of y equals x squared over 3. 1 over y dy by dx equals 2x over 3. dy by dx equals 2x over 3 multiplied by epsilon raised to the power of x squared over 3. Example 3. Y equals epsilon raised to the power 2x over x plus 1. Log base epsilon of y equals 2x over x plus 1. 1 over y dy by dx equals, in the numerator, 2 times open bracket x plus 1 close bracket minus 2x. In the denominator, open bracket x plus 1 close bracket raised to the power 2. Hence, dy by dx equals the fraction 2 divided by open bracket x plus 1 close bracket raised to the power 2, and the fraction is multiplied by epsilon raised to the fraction 2x divided by open bracket x plus 1 close bracket. Check by writing 2x divided by open bracket x plus 1 close bracket equals z. Example 4. Y equals epsilon raised to the square root of the quantity open bracket x squared plus a close bracket. Log base epsilon of y equals open bracket x squared plus a close bracket raised to the power of 1/2. 1 over y dy by dx equals x divided by open bracket x squared plus a close bracket raised to the power of 1/2. And dy by dx equals the fraction in the numerator x multiplied by epsilon raised to the square root x squared plus a divided by, in the denominator, open bracket x squared plus a close bracket raised to the power of 1/2. For if open bracket x squared plus a close bracket raised to the power of 1/2 equals u and x squared plus a equals v, then u equals v to the 1/2. du by dv equals 1 over 2v to the 1/2. dv by dx equals 2x, du by dx equals x in the numerator divided by, in the denominator, open bracket x squared plus a close bracket to the power of 1/2. Check by writing square root of the quantity x squared plus a equals z. Example 5. Y equals log open bracket a plus x cubed. Let a plus x cubed equal z. Then y equals log base epsilon of z. dy by dz equals 1 over z. dz by dx equals 3x squared. Hence dy by dx equals 3x squared divided by the quantity a plus x cubed. Example 6. Y equals log base epsilon open bracket 3x squared plus the square root of the quantity a plus x squared. Close bracket. Let 3x squared equals the square root of the quantity a plus x squared equals z. Then y equals log base epsilon of z. dy by dz equals 1 over z. dz by dx equals 6x plus the fraction in the numerator x divided by the denominator the square root of the quantity x squared plus a. dy by dx equals, in the numerator, open bracket 6x plus the fraction x divided by square root of open bracket x plus a close bracket n numerator divided by the denominator 3x squared plus the square root of open bracket a plus x squared close bracket n denominator. All of this equals, in the numerator, x times open bracket 1 plus 6 times the square root of the quantity x squared plus a n square root n numerator divided by the denominator open bracket 3x squared plus the square root of open bracket x squared plus a close bracket times the square root of the quantity x squared plus a and denominator. Example 7. Y equals open bracket x plus 3 close bracket raised to the power 2 multiplied by the square root of open bracket x minus 2 close bracket. We start with log base epsilon of y equals 2 log base epsilon of the quantity open bracket x plus 3 close bracket plus 1/2 log base epsilon of the quantity open bracket x minus 2 close bracket. 1 over y dy by dx, and that equals 2 over x plus 3 plus 1 over 2 times x minus 2. dy by dx equals open bracket x plus 3 close bracket raised to the power 2 multiplied by the square root of the quantity x minus 2 multiplied by open bracket in the numerator 2 divided by, in the denominator, open bracket x plus 3 close bracket plus, in the numerator, 1 divided by, in the denominator, 2 times open bracket x minus 2 close bracket and close bracket for the expression. Example 8. Y equals open bracket x squared plus 3 close bracket to the power 3 multiplied by open bracket x cubed minus 2 close bracket to the power of 2/3. The log base epsilon of y equals 3 log base epsilon of the quantity open bracket x squared plus 3 close bracket plus 2/3 multiplied by log base epsilon open bracket x cubed minus 2 close bracket. 1 over y dy by dx equals 3 times 2x divided by open bracket x squared plus 3 plus 2/3 multiplied by the fraction in the numerator 3x squared divided by, in the denominator, open bracket x cubed minus 2 close bracket equals 6x divided by open bracket x squared plus 3 close bracket plus 2x squared divided by open bracket x cubed minus 2 close bracket. For if y equals log base epsilon of the quantity open bracket x squared plus 3 close bracket, then x squared plus 3 equals z and u equals log base epsilon of z. Thus du by dz equals 1 over z, dz by dx equals 2x, du by dx equals 2x divided by the quantity open bracket x squared plus 3 close bracket. Similarly, if v equals log base epsilon open bracket x cubed minus 2 close bracket, dv by dx equals 3x squared divided by open bracket x cubed minus 2 close bracket, and dy by dx equals open bracket x squared plus 3 close bracket cubed times open bracket x cubed minus 2 close bracket to the power of 2/3, all multiplied by open bracket 6x divided by open bracket x squared plus 3 close bracket plus 2x squared divided by open bracket x cubed minus 2 close bracket close bracket. Example 9. Y equals the square root of open bracket x squared plus a close bracket divided by the cube root of open bracket x cubed minus a close bracket. Log base epsilon of y equals 1/2 multiplied by log base epsilon of open bracket x squared plus a close bracket minus 1/3 log base epsilon open bracket x cubed minus a close bracket. 1 over y dy by dx equals 1/2 multiplied by the fraction 2x over open bracket x squared plus a close bracket minus 1/3 multiplied by the fraction 3x squared in the numerator divided by in the denominator open bracket x cubed minus a close bracket equals x over open bracket x squared plus a close bracket minus x squared divided by open bracket x cubed minus a close bracket. And dy by dx equals the square root of the quantity open bracket x squared plus a close bracket divided by the cube root of the quantity open bracket x cubed minus a close bracket, all multiplied by open bracket x over open bracket x squared plus a close bracket minus x squared divided by open bracket x cubed minus a close bracket close bracket. Example 10. Y equals 1 divided by log base epsilon of x. dy by dx equals in the numerator open bracket log base epsilon of x times 0 minus 1 times 1 over x close bracket divided by log squared base epsilon of x equals -1 divided by x log squared base epsilon of x. Example 11. Y equals cube root of log base epsilon x equals log base epsilon of x to the power of 1/3. Let z equal log base epsilon of x and y equals z to the 1/3. dy by dz equals 1/3 z to the negative 2/3. dz by dx equals 1 over x. dy by dx equals 1 over 3x multiplied by the cube root of the square of the base epsilon log of x. Example 12. Y equals 1 over a to the x all to the power of a times x. Log base epsilon of y equals ax multiplied by open bracket log base epsilon of 1 minus log base epsilon of a to the x close bracket equals -ax times the base epsilon log of a to the x. 1 over y dy by dx equals -ax times a to the x times log base epsilon of a minus a times log base epsilon of a to the x. dy by dx equals -1 over a to the x to the power of ax multiplied by open bracket x times a to the x plus 1 times log base epsilon of a plus a times log base epsilon of a to the x. Close bracket. End of part 28. Reading by Paul King, pjk.scripts.mit.edu/pkj. pjk.scripts.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson, Section 29. Exercises 12. Question 1. Differentiate y equals b times open bracket epsilon to the exponent ax. Take away epsilon to the exponent negative ax, close bracket. Answer: ab multiplied by open bracket, epsilon to the exponent ax plus epsilon to the exponent negative ax, close bracket. Question 2. Find the differential coefficient with respect to t of the expression u equals at squared plus 2 times the natural log of t. Answer: 2at plus 2 over t. Question 3. If y equals n to the power t, find d of natural log of y by dt. Answer: the natural log of n. Question 4. Show that if y equals 1 over b times a to the power bx divided by the natural log of a, then dy by dx equals a to the bx. Question 5. If w is pv to the power n, find dw by dv. Answer: npv to the power n minus 1. Question 6. Differentiate y equals the natural log of x to the n. Answer: n over x. Question 7. Differentiate y equals 3 times epsilon to the power negative x over x minus 1. Answer: 3 times epsilon to the power of negative x over x minus 1, all divided by the quantity x minus 1 all squared. Question 8. Differentiate y equals the quantity 3x squared plus 1 multiplied by epsilon to the power of negative 5x. Answer: 6x times epsilon to the power negative 5x, subtract 5 times the quantity 3x squared plus 1 close bracket times epsilon to the power negative 5x. Question 9. Differentiate y equals the natural log of the quantity x to the a plus a. Answer: ax to the power a minus 1 all divided by x to the a plus a. Question 10. Differentiate y equals the quantity 3x squared minus 1 times the quantity root x plus 1. Answer: open bracket the fraction 6x over the quantity 3x squared minus 1 plus the fraction 1 over 2 times the quantity root x plus x, close bracket, multiplied by the binomial 3x squared minus 1 times the binomial root x plus 1. Question 11. Differentiate the natural log of x plus 3 all divided by x plus 3. Answer: the quantity 1 minus natural log of x plus 3 all divided by x plus 3 quantity squared. Question 12. Differentiate y equals a to the x times x to the a. Answer: a to the x times the quantity open bracket a times x to the a minus 1 plus x to the a times the natural log of a, close bracket. Question 13. It was shown by Lord Kelvin that the speed of signaling through a submarine cable depends on the value of the ratio of the external diameter of the core to the diameter of the enclosed copper wire. If this ratio is called y, then the number of signals s that can be sent per minute can be expressed by the formula s equals a times y squared times the natural log of 1 over y, where a is a constant depending on the length and the quality of the materials. Show that if these are given, s will be a maximum if y equals 1 divided by the square root of epsilon. No answer was given to this problem. Question 14. Find the maximum or minimum of y equals x cubed minus the natural log of x. Answer: minimum y equals 0.7 for x equals 0.694. Question 15. Differentiate y equals the natural log of the quantity a times x times epsilon to the power x. Answer: the quantity 1 plus x divided by x. Question 16. Differentiate y equals the quantity, open bracket, natural log of ax, close bracket, all to the power 3. Answer: 3 over x times, open bracket, the natural log of ax, close bracket, to the power 2. End of section 29. Reading by Paul King. pjk.scripts.mit.edu/pkj.
The logarithmic curve. Let us return to the curve which has its successive ordinates in geometrical progression, such as that represented by the equation y equals bp to the x power. We can see, by putting x equals 0, that b is the initial height of y. Then, when x equal 1, y equal bp, x equals 2, y equals bp squared, x equals 3, y equals bp to the third power, etc. Also, we see that p is the numerical value of the ratio between the height of any ordinate and that of the next preceding it. In Figure 40, we have taken p as 6 over 5, each ordinate being 6/5 as high as the preceding one. If two successive ordinates are related together, thus, in a constant ratio, their logarithms will have a constant difference, so that if we should plot out a new curve, Figure 41, with values of log base epsilon of y as ordinates, it would be a straight line sloping up by equal steps. In fact, it follows from the equation that log base epsilon of y equals log base epsilon of b plus x times log base epsilon of p, whence log base epsilon of y minus log base epsilon of b equals x times log base epsilon of p. Now, since log base epsilon of p is a mere number and may be written as log base epsilon of p equals a, it follows that log base epsilon of y over b equals ax, and the equation takes the new form, y equals b epsilon to the ax power. End of section 30. The die-away curve. If we were to take p as a proper fraction, less than unity, the curve would obviously tend to sink downwards, as in Figure 42, where each successive ordinate is 3/4 of the height of the preceding one. The equation is still y equal bp to the x power, but since p is less than 1, log base epsilon of p will be a negative quantity, and may be written negative a, so that p equal epsilon to the negative a power. And now our equation for the curve takes the form y equal b epsilon to the negative ax power. The importance of this expression is that in the case where the independent variable is time, the equation represents the course of a great many physical processes in which something is gradually dying away. Thus, the cooling of a hot body is represented, in Newton's celebrated law of cooling, by the equation theta sub t equals theta sub 0 epsilon to the negative at power, where theta sub 0 is the original excess of temperature of a hot body over that of its surroundings, theta sub t the excess of temperature at the end of time t, and a is a constant, namely, the constant of decrement depending on the amount of surface exposed by the body, and on its coefficients of conductivity and emissivity, etc. A similar formula, Q sub t equals Q sub 0 epsilon to the negative at power, is used to express the charge of an electrified body originally having a charge Q sub 0, which is leaking away with a constant of decrement A, which constant depends in this case on the capacity of the body and on the resistance of the leakage path. Oscillations given to a flexible spring die out after a time, and the dying out of the amplitude of the motion may be expressed in a similar way. In fact, epsilon to the negative at power serves as a die-away factor for all those phenomena in which the rate of decrease is proportional to the magnitude of that which is decreasing, or where, in our usual symbols, dy over dt is proportional at every moment to the value that y has at that moment, for we have only to inspect the curve, figure 42 above, to see that, at every part of it, the slope, dy over dx, is proportional to the height, y, the curve becoming flatter as y grows smaller. In symbols thus, y equal b epsilon to the negative ax power, or log base epsilon of y equals log base epsilon of b minus ax log base epsilon of epsilon equals log base epsilon of b minus ax, and, differentiating, 1 over y times dy over dx equals negative a. Hence, dy over dx equal b epsilon to the negative ax power times negative a equal negative ay. Or, in words, the slope of a curve is downward and proportional to y and to the constant a. We should have got the same result if we had taken the equation in the form y equal bp to the x power, for then dy over dx equal bp to the x power times log base epsilon of p. But log base epsilon of p equal negative a, giving us dy over dx equal y times negative a equals negative ay, as before. The time constant. In the expression for the die-away factor, epsilon to negative at power, the quantity a is the reciprocal of another quantity known as the time constant, which we may denote by the symbol T. Then the die-away factor will be written epsilon to the negative t over T power, and it will be seen by making t equal T that the meaning of T, or of 1 over a, is that this is the length of time which it takes for the original quantity, called theta sub 0 or q sub 0 in the preceding instances, to die away 1 over epsilon part, that is, to 0.3678 of its original value. The value of epsilon to the x power and epsilon to the negative x power are continually required in different branches of physics, and as they are given in very few sets of mathematical tables, some of the values are tabulated on page 157 for convenience. As an example of the use of this table, suppose there is a hot body cooling, and that at the beginning of the experiment, that is, when t equals 0, it is 72 degrees hotter than the surrounding objects, and if the time constant of its cooling is 20 minutes, that is, if it takes 20 minutes for its excess of temperature to fall to 1 over epsilon part of 72 degrees, then we can calculate to what it will have fallen in any given time t. For instance, let t be 60 minutes. Then t over T equal 60 divided by 20 equal 3. and we shall have to find the value of epsilon to the negative 3, and then multiply the original 72 degrees by this. The table shows that epsilon to the negative 3 power is 0.0498, so that at the end of 60 minutes the excess of temperature will have fallen to 72 degrees times 0.0498 equals 3.586 degrees. The values tabulated on page 157. When x is 0.00, epsilon to the x power is 1.0000, epsilon to the negative x power 1.0000, 1 minus epsilon to the negative x power 0.000. When x is 0.10, epsilon to the x power is 1.1052, epsilon to the negative x power 0.9048, 1 minus epsilon to the negative x power 0.0952. When x is 0.20, epsilon to the x power is 1.2214, epsilon to the negative x power is 0.8187, 1 minus epsilon to the negative x power 0.1813. When x is 0.50, epsilon to the x power is 1.6487, epsilon to the negative x power 0.6065, 1 minus epsilon to the negative x power 0.3935. When x is 0.75, epsilon to the x power is 2.1170, epsilon to the negative x power 0.4724, 1 minus epsilon to the negative x power 0.5276. When x is 0.90, epsilon to the x power is 2.4596, epsilon to the negative x power is 0.4066, 1 minus epsilon to the negative x power is 0.5934. When x is 1.00, epsilon to the x power is 2.7183, epsilon to the negative x power 0.3679, 1 minus epsilon to the negative x power 0.6321. When x is 1.10, epsilon to the x power is 3.0042, epsilon to the negative x power is 0.3329, 1 minus epsilon to the negative x power is 0.6671. When x is 1.20, epsilon to the x power is 3.3201, epsilon to the negative x power is 0.3012, 1 minus epsilon to the negative x power is 0.6988. When x is 1.25, epsilon to the x power is 3.4903, epsilon to the negative x power is 0.2865, 1 minus epsilon to the negative x power is 0.7135. When x is 1.50, epsilon to the x power is 4.4817, epsilon to the negative x power is 0.2231. 1 minus epsilon to the negative x power is 0.7769. When x is 1.75, epsilon to the x power is 5.755. Epsilon to the negative x power is 0.1738. 1 minus epsilon to the negative x power is 0.8262. When x is 2.0, epsilon to the x power is 7.389. Epsilon to the negative x power is 0.1353. 1 minus epsilon to the negative x power is 0.8647. When x is 2.50, Epsilon to the x power is 12.182. Epsilon to the negative x power is 0.0821. 1 minus epsilon to the negative x power is 0.9179. When x is 3.0, epsilon to the x power is 20.086. Epsilon to the negative x power is 0.0498. 1 minus epsilon to the negative x power is 0.9502. When x is 3.50, epsilon to the x power is 33.115. Epsilon to the negative x power is 0.0302. 1 minus epsilon to the negative x power is 0.9698. When x is 4.00, epsilon to the x power is 54.598. Epsilon to the negative x power is 0.0183. 1 minus epsilon to the negative x power is 0.9817. When x is 4.50, epsilon to the x power is 90.017. Epsilon to the negative x power is 0.0111. 1 minus epsilon to the negative x power is 0.9889. When x is 5.0, epsilon to the x power is 148.41. Epsilon to the negative x power is 0.0067. 1 minus epsilon to the negative x power is 0.9933. When x is 5.50, epsilon to the x power is 244.69. Epsilon to the negative x power is 0.0041. 1 minus epsilon to the negative x power is 0.9959. When x is 6.00, epsilon to the x power is 403.43. Epsilon to the negative x power is 0.00248. 1 minus epsilon to the negative x power is 0.99752. When x is 7.50, epsilon to the x power is 1808.04. Epsilon to the negative x power is 0.00055. 1 minus epsilon to the negative x power is 0.99947. When x equals 10, epsilon to the x power is 22,026.5. Epsilon to the negative x power is 0.000045. 1 minus epsilon to the negative x power is 0.999955. Further examples. 1. The strength of an electric current in a conductor at a time t seconds after the application of the electromotive force producing it is given by the expression C equal E over R, open brace, 1 minus epsilon to the negative RT over L power, close brace. The time constant is L over R. If E equal 10, R equal 1, L equals 0.01, then when t is very large, the term epsilon to the negative RT over L power becomes 1, and C equals E over R equals 10. Also, L over R equals T equals 0.01. Its value at any time may be written C equals 10 minus 10 epsilon to the negative t over 0.01 power, the time constant being 0.01. This means that it takes 0.01 seconds for the variable term to fall by 1 over epsilon equals 0.3678 of its initial value, 10 epsilon to the negative 0 over 0.01 power equals 10. To find the value of the current when t equals 0.001 seconds, say t over uppercase T equals 0.1, epsilon to the negative 0.1 power equal 0.9048 from table. It follows that after 0.001 second, the variable term is 0.9048 times 10 equal 9.048, and the actual current is 10 minus 9.048 equal 0.952. Similarly, at the end of 0.1 seconds, t over uppercase T equals 10, epsilon to the negative 10 power equals 0.000045. The variable term is 10 times 0.000045 equals 0.00045, the current being 9.9995. 2. The intensity of uppercase I of a beam of light which has passed through a thickness L centimeters of some transparent medium is uppercase I equals uppercase I sub 0 epsilon to the negative uppercase KL power, where uppercase I sub 0 is the initial intensity of the beam, and uppercase K is a constant of absorption. This constant is usually found by experiments. If it be found, for instance, that a beam of light has its intensity diminished by 18% in passing through 10 centimeters of a certain transparent medium, this means that 82 equals 100 times epsilon to the negative uppercase K times 10 power, or epsilon to the negative 10 uppercase K power equals 0.82. And from the table one sees that 10 uppercase K equals 0.20, very nearly. Hence, uppercase K equals 0.02. To find the thickness that will reduce the intensity to half its value, one must find the value of L, which satisfies the equality 50 equal 100 times epsilon to the negative 0.02 L power, or 0.5 equal epsilon to the negative 0.02 L power. It is found by putting this equation in its logarithmic form, namely, log 0.5 equal negative 0.02 times L times log epsilon, which gives L equal negative 0.3010 over negative 0.02 times 0.4343 equal 34.7 centimeters nearly. 3. The quantity uppercase Q of a radioactive substance which has not yet undergone transformation is known to be related to the initial quantity uppercase Q sub 0 of the substance by the relation uppercase Q equal uppercase Q sub 0 epsilon to the negative lambda t power, where lambda is a constant and t the time in seconds elapsed since the transformation began. For radium uppercase A, if time is expressed in seconds, experiment shows that lambda equal 3.85 times 10 to the negative 3 power. Find the time required for transforming half the substance. This time is called the mean life of the substance. We have 0.5 equal epsilon to the negative 0.00385 t. Log 0.5 equal negative 0.00385 t times log epsilon, and t equal 3 minutes very nearly. End of section 31. Exercises 13. 1. Draw the curve y equal b epsilon to the negative t over uppercase T, where b equals 12, uppercase T equal 8, and t is given various values from 0 to 20. Answer. Let t over uppercase T equal x, therefore t equal 8x, and use the table on page 157. 2. If a hot body cools so that in 24 minutes its excess of temperature has fallen to half the initial amount, deduce the time constant and find how long it will be in cooling down to 1% of the original excess. Answer. T equals 34.627, 159.46 minutes. 3. Plot the curve y equals 100 times the quantity 1 minus epsilon to the negative 2t power. Answer. Take 2t equal x and use the table on page 157. 4. The following equations give very similar curves. 1. Y equal ax over x plus b. 2. Y equal a times the quantity 1 minus epsilon to the negative x over b power. 3. Y equal a over 90-degree arctangent of x over b. Draw all three curves, taking a equal 100 millimeters, b equals 30 millimeters. 5. Find the differential coefficient of y with respect to x if a. Y equals x to the x power, b. Y equals the quantity to the x power of epsilon to the x power, c. Y equals epsilon to the x power to the x power. Answer. A. X to the x power times the quantity 1 plus log base epsilon of x. B. 2x times the quantity to the x power of epsilon to the x power. C. Epsilon to the x power to the x power times x to the x power times the quantity 1 plus the log base epsilon of x. 6. For thorium uppercase A, the value of lambda is 5. Find the mean life, that is, the time taken by the transformation of a quantity uppercase Q of thorium uppercase A equal to half the initial quantity uppercase Q sub 0 in the expression. Q equal Q sub 0 epsilon to the negative lambda t, t being in seconds. Answer. 0.14 seconds. 7. A condenser of capacity uppercase K equals 4 times 10 to the negative 6 power. Charge to a potential of uppercase V sub 0 equals 20 is discharging through a resistance of 10,000 ohms. Find the potential uppercase V after A. 0.1 seconds, B. 0.01 second, assuming that the fall of potential follows the rule uppercase V equals uppercase V sub 0 epsilon to the negative t over uppercase K uppercase R power. Answer. A. 1.642, B. 15.58. 8. The charge uppercase Q of an electrified insulated metal sphere is reduced from 20 to 16 units in 10 minutes. Find the coefficient mu of leakage if uppercase Q equals uppercase Q sub 0 times epsilon to the negative mu t power. Q sub 0 being the initial charge and t being in seconds. Hence find the time taken by half the charge to leak away. Answer. Mu equals 0.00037. 31 to the m power times 1/4. 9. The dampening on a telephone line can be ascertained from the relation I equals I sub 0 epsilon to the negative beta L, where I is the strength after t seconds of a telephonic current of initial strength I sub 0. L is the length of the line in kilometers, and beta is a constant. For the Franco-English submarine cable laid in 1910, beta equaled 0.0114. Find the dampening at the end of the cable, 40 kilometers, and the length along which I is still 8% of the original current. Limiting value of very good audition. Answer. I is 63.4% of I sub 0, 220 kilometers. 10. The pressure P of the atmosphere at an altitude h kilometers is given by P equals P sub 0 epsilon to the negative kh power. P sub 0 being the pressure at sea level, 760 millimeters, the pressure at 10, 20, and 50 kilometers being 199.2, 42.2, 0.32 respectively, find K in each case. Using the mean value of K, find the percentage error in each case. Answer. 0.133, 0.145, 0.155, mean 0.144, negative 10.2%, negative 0.9%, positive 77.2%. 11. Find the minimum or maximum of y equals x to the x power. Answer. Minimum for x equals 1 over epsilon. 12. Find the minimum or maximum of y equals x to the 1 over x power. Answer. Maximum for x equals epsilon. 13. Find the minimum or maximum of y equals xa to the 1 over x power. Answer. Minimum for x equals log base epsilon of a. End of section 32.
Thompson. Chapter 15. How to deal with sines and cosines. Greek letters being usual to denote angles, we will take as the usual letter for any variable angle the letter theta. Let us consider the function y equals sine theta. What we have to investigate is the value of d sine theta over d theta, or in other words, if the angle theta varies, we have to find the relation between the increment of the sine and the increment of the angle, both increments being indefinitely small in themselves. Examine figure 43, wherein, if the radius of the circle is unity, the height of y is the sine and theta is the angle. Now, if theta is supposed to increase by the addition to it of the small angle d theta, an element of angle, the height of y, the sine, will be increased by a small element dy. The new height, y plus dy, will be the sine of the new angle theta plus d theta, or, stating it as an equation, y plus dy equals sine of the sum of theta plus d theta, and subtracting from this the first equation gives dy equals sine of the sum of theta plus d theta minus sine theta. The quantity on the right-hand side is the difference between two sines, and books on trigonometry tell us how to work this out. For they tell us that if m and n are two different angles, sine m minus sine n equals 2 multiplied by the cosine of the quantity m plus n over 2 multiplied by the sine of the quantity m minus n over 2. If then we put m equals theta plus d theta for one angle and n equals theta for the other, we may write dy equals 2 multiplied by the cosine of the quantity theta plus d theta plus theta over 2 multiplied by the sine of the quantity theta plus d theta minus theta over 2. Or dy equals 2 multiplied by the cosine of the quantity theta plus 1/2 d theta multiplied by the sine of 1/2 d theta. But if we regard d theta as indefinitely small, then in the limit we may neglect half d theta by comparison with theta, and may also take sine half d theta as being the same as half d theta. The equation then becomes dy equals 2 times cosine theta times 1/2 d theta. dy equals cosine theta times d theta, and finally dy over d theta equals cosine theta. The accompanying curves, figures 44 and 45, show, plotted to scale, the values of y equals sine theta and dy over d theta equals cosine theta for the corresponding values of theta. Take next the cosine. Let y equals cosine theta. Now cosine theta equals the sine of the quantity pi over 2, that fraction minus theta. Therefore, dy equals d of the sine of the quantity pi over 2, that fraction minus theta, which equals the cosine of the quantity pi over 2, that fraction minus theta, that cosine multiplied by d negative theta, which equals the cosine of the quantity pi over 2, that fraction minus theta, that cosine multiplied by negative d theta. dy over d theta equals negative cosine of the quantity pi over 2, that fraction minus theta, and it follows that dy over d theta equals negative sine theta. Lastly, take the tangent. Let y equal tangent theta. dy equals the tangent of the quantity theta plus d theta, that tangent minus tangent theta. Expanding, as shown in books on trigonometry, the tangent of the quantity theta plus d theta equals the fraction, the numerator is tangent theta plus tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta. Whence dy equals the fraction, the numerator is tangent theta plus tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta, that fraction minus tangent theta, which equals the fraction, the numerator is 1 plus tangent squared theta, that addition multiplied by tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta. Now remember that if d theta is indefinitely diminished, the value of tangent d theta becomes identical with d theta, and tangent theta multiplied by d theta is negligibly small compared with 1, so that the expression reduces to dy equals the fraction, the numerator is 1 plus tangent squared theta, that addition multiplied by d theta, the denominator is 1. So that dy over d theta equals 1 plus tangent squared theta, or dy over d theta equals secant squared theta. Collecting these results, we have y, dy over d theta, sine theta, cosine theta, cosine theta minus sine theta, tangent theta, secant squared theta. Sometimes in mechanical and physical questions, as for example in simple harmonic motion and in wave motions, we have to deal with angles that increase in proportion to the time. Thus, if T be the time of one complete period or movement round the circle, then since the angle all round the circle is 2 pi radians or 360 degrees, the amount of angle moved through in time t will be theta equals 2 times pi times the fraction t over T in radians. Theta equals 360 times t over T in degrees. If the frequency, or number of periods per second, be denoted by n, then n equals 1 over capital T, and we may then write theta equals 2 pi n small t. Then we shall have y equals the sine of the multiple of 2 pi n small t. If now we wish to know how the sine varies with respect to time, we must differentiate with respect not to theta but to small t. For this we must resort to the artifice explained in chapter 9, page 66, and put dy over d small t equals dy over d theta times d theta over d small t. Now d theta over d small t will obviously be 2 pi n, so that dy over d small t equals cosine theta times 2 pi n, which equals 2 pi n times the cosine of 2 pi n small t. Similarly, it follows that d cosine of 2 pi n small t over d small t equals negative 2 pi n multiplied by the sine of 2 pi n small t. End of section 33. Recording by Son of the Exiles.
How to deal with sines and cosines, Part 2. Second differential coefficient of sine or cosine. We have seen that when sine theta is differentiated with respect to theta, it becomes cos theta, and that when cos theta is differentiated with respect to theta, it becomes minus sine theta, or, in symbols, d squared of sine theta over d theta squared is equal to minus sine theta. So we have this curious result that we have found a function such that if we differentiate it twice over, we get the same thing from which we started, but with the sign changed from plus to minus. The same thing is true for the cosine. For differentiating cos theta gives us minus sine theta, and differentiating minus sine theta gives us minus cos theta, or thus d squared cos theta over d theta squared is equal to minus cos theta. Sines and cosines are the only functions of which the second differential coefficient is equal and of opposite sign to the original function. Examples. With what we have so far learned, we can now differentiate expressions of a more complex nature. 1. Y is equal to arc sine x. If y is the arc whose sine is x, then x equals sine y. dx over dy is equal to cos y. Passing now from the inverse function to the original one, we get dy over dx is equal to 1 over dx over dy, which is equal to 1 over cos y. Now, cos y is equal to 1 minus the square root of 1 minus sine squared y, which is equal to the square root of 1 minus x squared. Hence, dy over dx is equal to 1 over square root of 1 minus x squared. A rather unexpected result. 2. Y is equal to cos cubed theta. This is the same as y is equal to cos theta cubed. Let cos theta be equal to v, then y be equal to v cubed. dy over dv is 3v squared. dv over d theta is equal to minus sine theta, and dy over d theta is equal to dy over dv times dv over d theta, which is equal to minus 3 cos squared theta sine theta. 3. Y is equal to sine brackets x plus a close brackets. Let x plus a be equal to v, then y is equal to sine of v. dy over dv is equal to cos v. dv over dx is equal to 1, and dy over dx is equal to cos of open brackets x plus a close brackets. 4. Y is equal to log base e of sine theta. Let sine theta be equal to v, y equal to log base e of v, then dy over dv is equal to 1 over v, and dv over d theta is equal to cos theta. dy over d theta is equal to 1 over sine theta times cos theta, which is equal to cotangent of theta. 5. y is equal to cotangent of theta, which is equal to cos theta over sine theta. dy over d theta is equal to minus sine squared theta minus cos squared theta divided by sine squared theta is equal to minus, open brackets, 1 plus cot squared theta, close brackets, which is equal to minus cosecant squared theta. 6. Y is equal to tan 3 theta. Let 3 theta be equal to v, y be equal to tan v, and dy over dv be equal to secant square of v. dv over d theta is equal to 3. dy over d theta is equal to 3 secant squared of 3 theta. 7. Y is equal to square root of 1 plus 3 tan squared of theta. Y is equal to 1 plus 3 tan squared theta in brackets to the power of 1/2. Let 3 tan squared theta be equal to v. Y is equal to, open brackets, 1 plus v, close brackets, to the power of 1/2. dy over dv is equal to 1 over 2 square root of 1 plus v. See page 67. dv over d theta is equal to 6 tan theta secant squared theta. For if tan theta is equal to u, v is equal to 3u squared, dv over du is equal to 6u, du over d theta is equal to secant squared of theta. Hence, dv over d theta is equal to 6, open brackets, tan theta secant squared theta, close brackets. Hence, dy over d theta is equal to 6 tan theta secant squared theta over 2 times the square root of 1 plus 3 tan squared theta. 8. Y is equal to sine x cos x. dy over dx is equal to sine x times minus sine x plus cos x times cos x, which is equal to cos squared x minus sine squared x. End of section 34. Recording by Eelme.
Exercises 14. 1. Differentiate the following. 1. Y equal a sine of the quantity theta minus pi over 2. 2. Y equal sine squared theta and y equal sine 2 theta. 3. Theta and dy over d theta equal 2 cosine 2 theta. 3. dy over d theta equal 3 sine squared theta cosine theta and dy over d theta equal 3 cosine 3 theta. 2. Find the value of theta for which sine theta times cosine theta is a maximum. Answer. Theta equals 45 degrees, or pi over 4 radians. 3. Differentiate y equal 1 over 2 pi times cosine 2 pi nt. Answer. dy over dt equal negative n sine 2 pi nt. 4. If y equal sine a to the x power, find dy over dx. Answer. A to the x power log base epsilon of a cosine a to the x power. 5. Differentiate y equal log to base epsilon of cosine x. Answer. Cosine x over sine x equal cotan x. 6. Differentiate y equal 18.2 sine of the quantity x plus 26 degrees. Answer. 18.2 cosine of the quantity x plus 26 degrees. 7. Plot the curve y equal 100 sine the quantity theta minus 15 degrees and show that the slope of the curve at theta equals 75 degrees is half the maximum slope. Answer. The slope is dy over d theta equal 100 cosine of the quantity theta minus 15 degrees, which is a maximum when the quantity theta minus 15 degrees equals 0 or theta equals 15 degrees. The value of the slope being then equal 100. When theta equals 75 degrees, the slope is 100 cosine the quantity 75 degrees minus 15 degrees equals 100 cosine of 60 degrees equals 100 times 1/2 equal 50. 8. If y equals sine theta times sine 2 theta, find dy over d theta. Answer. Cosine theta sine 2 theta plus 2 cosine 2 theta sine theta equals 2 sine theta of the quantity cosine squared theta plus cosine 2 theta equals 2 sine theta of the quantity 3 cosine squared theta minus 1. 9. If y equal a times the tangent to the m power of theta to the n power, find the differential coefficient of y with respect to theta. Answer. amn theta to the n minus 1 power, tangent to the m minus 1 power of theta to the n power, secant squared theta to the n power. 10. Differentiate y equal epsilon to the x power sine squared of x. Answer. Epsilon to the x power times the quantity sine squared x plus sine 2x. Epsilon to the x power times the quantity sine squared x plus 2 sine 2x plus 2 cosine 2x. 11. Differentiate the three equations of exercises 13, number 4, and compare their differential coefficients as to whether they are equal or nearly equal for very small values of x, or for very large values of x, or for values of x in the neighborhood of x equal 30. Answers. 1. dy over dx equal ab over the quantity squared x plus b. 2. a over b times epsilon to the negative x over b power. 3. 1 over 90 degrees times ab over the quantity b squared plus x squared. 12. Differentiate the following. 1. Y equal secant x. 2. Y equal arc cosine x. 3. Y equal arc tangent x. 4. Y equal arc secant x. 5. Y equal tangent x times the square root of 3 secant x. Answers. 1. dy over dx equal secant x tangent x. 2. dy over dx equal negative 1 over the square root of 1 minus x squared. 3. dy over dx equal 1 over 1 plus x squared. 4. dy over dx equal 1 over x times the square root of x squared minus 1. 5. dy over dx equal the square root of 3 secant x times the quantity 3 secant squared x minus 1 all over 2. 13. Differentiate y equals sine of the quantity to the 2.3 power of 2 theta plus 3. Answer. dy over d theta equals 4.6 times the quantity to the 1.3 power of 2 theta plus 3, cosine of the quantity to the 2.3 power of 2 theta plus 3. 14. Differentiate y equal theta cubed plus 3 sine of the quantity theta plus 3 minus 3 to the sine theta power minus 3 to the theta power. Answer. dy over d theta equals 3 theta squared plus 3 cosine of the quantity theta plus 3 minus log base epsilon of 3 times the quantity cosine theta times 3 to the sine theta power plus 3 theta. 15. Find the maximum or minimum of y equal theta cosine theta. Answer. Theta equals cotangent theta. Theta equals plus or minus 0.86 is maximum for positive theta, minimum for negative theta. End of section 35.
We sometimes come across quantities that are functions of more than one independent variable. Thus, we may find a case where y depends on two other variable quantities, one of which we will call u and the other v. In symbols, y equals f open brackets u, v close brackets. Take the simplest concrete case. Let y equals u times v. What are we to do? If we were to treat v as a constant and differentiate with respect to u, we should get dy subscript v equals v du, or if we treat u as a constant and differentiate with respect to v, we should have dy subscript u equals u dv. The little letters here put as subscripts are to show which quantity has been taken as constant in the operation. Another way of indicating that the differentiation has been performed only partially, that is, has been performed only with respect to one of the independent variables, is to write the differential coefficients with Greek deltas, like delta instead of little d. In this way, delta y over delta u equals v, and delta y over delta v equals u. If we put in these values for v and u respectively, we shall have dy subscript v equals delta y over delta u du, and dy subscript u equals delta y over delta v dv, which are partial differentials. But, if you think of it, you will observe that the total variation of y depends on both these things at the same time. That is to say, if both are varying, the real dy ought to be written dy equals delta y over delta u du add delta y over delta v dv, and this is called a total differential. In some books it is written dy equals open brackets dy over du close brackets du add open brackets dy over dv close brackets dv. Example 1. Find the partial differential coefficients of the expression w equals 2ax squared add 3bxy add 4cy cubed. The answers are delta w over delta x equals 4ax add 3by, and delta w over delta y equals 3bx add 12cy squared. The first is obtained by supposing y constant, the second is obtained by supposing x constant. Then dw equals open brackets 4ax add 3by close brackets dx add open brackets 3bx add 12cy squared close brackets dy. Example 2. Let z equals x to the power of y. Then, treating first y and then x as constant, we get in the usual way delta z over delta x equals y times x to the power of y minus 1, and delta z over delta y equals x to the power of y times log base ex, so that dz equals y times x to the power of y minus 1 dx add x to the power of y log base ex dy. Example 3. A cone having height h and radius of base r has volume v equals 1/3 pi r squared h. If its height remains constant, while r changes, the ratio of change of volume with respect to radius is different from the ratio of change of volume with respect to height which would occur if the height were varied and the radius kept constant, for delta v over delta r equals 2 pi over 3 rh. Delta v over delta h equals pi over 3 r squared. The variation when both the radius and the height change is given by dv equals 2 pi over 3 times rh dr, add pi over 3 times r squared dh. Example 4. In the following example, big F and little f denote two arbitrary functions of any form whatsoever. For example, they may be sine functions, or exponentials, or mere algebraic functions of the two independent variables t and x. This being understood, let us take the expression y equals big F open brackets x add at close brackets add little f open brackets x minus at close brackets, or y equals big F as a function of w add little f as a function of v, where w equals x add at and v equals x minus at. Then delta y over delta x equals delta big F as a function of w over delta w times delta w over delta x add delta little f as a function of v over delta v times delta v over delta x equals big F as a function of w prime times 1 add little f as a function of v prime times 1, where the figure 1 is simply the coefficient of x in w and v, and delta squared y over delta x squared equals big F as a function of w double primed add little f as a function of v double primed. Also, delta y over delta t equals delta big F as a function of w over delta w times delta w over delta t add delta little f as a function of v over delta v times delta v over delta t equals big F as a function of w primed times a minus little f as a function of v primed times a, and delta squared y over delta t squared equals big F as a function of w double primed times a squared add little f as a function of v double primed times a squared, whence delta squared y over delta t squared equals a squared delta squared y over delta x squared. This differential equation is of immense importance in mathematical physics. End of section 36. By Silvanus P. Thompson. Chapter 16, Partial Differentiation, Part 2. Maxima and minima of functions of two independent variables. Example 5. Let us take up again exercise 9, page 107, number 4. Let x and y be the length of two of the portions of the string. The third is 30 minus open brackets x add y close brackets, and the area of the triangle is a equals the square root of s open brackets s minus x close brackets open brackets s minus y close brackets open brackets s minus 30 plus x plus y close brackets, where s is the half perimeter 15, so that a equals the square root of 15p, where p equals open brackets 15 minus x close brackets open brackets 15 minus y close brackets open brackets x add y minus 15 close brackets equals xy squared add x squared y minus 15x squared minus 15y squared minus 45xy add 450x add 450y minus 3375. Clearly a is maximum when p is maximum. dp equals delta p over delta x dx add delta p over delta y dy. For a maximum, clearly it will not be a minimum in this case, one must have simultaneously delta p over delta x equals 0 and delta p over delta y equals 0, that is, 2xy minus 30x add y squared minus 45y add 450 equals 0, and 2xy minus 30y add x squared minus 45x add 450 equals 0. An immediate solution is x equals y. If we now introduce this condition in the value of p, we find p equals open brackets 15 minus x close brackets squared open brackets 2x minus 15 close brackets equals 2x cubed minus 75x squared add 900x minus 3375. The maximum or minimum dp over dx equals 6x squared minus 150x add 900 equals 0, which gives x equals 15 or x equals 10. Clearly x equals 15 gives the minimum area, x equals 10 gives the maximum, for d2p over dx squared equals 12x minus 150, which is plus 30 for x equals 15 and minus 30 for x equals 10. Example 6. Find the dimensions of an ordinary railway coal truck with rectangular ends, so that for a given volume V, the area of sides and floor together is as small as possible. The truck is a rectangular box open at the top. Let x be the length and y the width, and the depth is v over xy. The surface area is S equals xy add 2v over x add 2v over y. ds equals delta s over delta x dx add delta s over delta y dy equals open brackets y minus 2v over x squared close brackets dx add open brackets x minus 2v over y squared close brackets dy. For minimum, clearly it won't be a maximum here. Y minus 2v over x squared equals 0. X minus 2v over y squared equals 0. Here also, an immediate solution is x equals y, so that s equals x squared plus 4v over x. ds over dx equals 2x minus 4v over x squared equals 0 for minimum, and x equals the cube root of 2v. End of section 37. Made easy by Silvanus P. Thompson. Section 38. Exercises 15. 1. Differentiate the expression x cubed over 3 minus 2x cubed y minus 2y squared x add y over 3 with respect to x alone and with respect to y alone. Answer. X squared minus 6x squared y minus 2y squared. 1/3 minus 2x cubed minus 4xy. 2. Find the partial differential coefficients with respect to x, y and z of the expression x squared yz plus xy squared z plus xyz squared plus x squared y squared z squared. Answer. 2xyz add y squared z add z squared y add 2xy squared z squared. 2xyz add x squared z add x z squared add 2x squared y z squared. 2xyz add x squared y add x y squared add 2x squared y squared z. 3. Let r squared equals open brackets x minus a close brackets squared add open brackets y minus b close brackets squared add open brackets z minus c close brackets squared. Find the value of delta r over delta x, add delta r over delta y, add delta r over delta z. Also find the value of delta squared r over delta x squared, add delta squared r over delta y squared, add delta squared r over delta z squared. Answer. 1 over r, open brackets x minus a close brackets add open brackets y minus b close brackets add open brackets, z minus c, close brackets, equals, open brackets, x add y add z, close brackets, minus, open brackets, a add b add c, close brackets, all over r, 3 over r. 4. Find the total differential of y equals u to the power of v. Answer. dy equals v u to the power of v minus 1 du add u to the power of v log base e u dv. 5. Find the total differential of y equals u cubed sin v of y equals open brackets sin x close brackets to the power of u and of y equals log base e u all over v. Answer. dy equals 3 sin v u squared du add u cubed cos v dv. dy equals u sin x to the power of u minus 1 cos x dx add open brackets sin x close brackets to the power of u log base e sin x du. dy equals 1 over v times 1 over u du minus log base e u times 1 over v squared dv. 6. Verify that the sum of three quantities x, y, z, whose product is a constant k, is maximum when these three quantities are equal. 7. Find the maximum or minimum of the function u equals x add 2xy add y. Answer. Minimum for x equals y equals minus a half. 8. The Post Office regulations state that no parcel is to be of such a size that its length plus its girth exceeds 6 feet. What is the greatest volume that can be sent by post? A. In the case of a package of rectangular cross section. B. In the case of a package of circular cross section. Answer. A. Length 2 feet, width equals depth equals 1 foot. Volume equals 2 cubic feet. B. Radius equals 2 over pi feet equals 7.46 inches. Length equals 2 feet. Volume equals 2.54. 9. Divide pi into 3 parts such that the continued product of their signs may be a maximum or minimum. Answer. All 3 parts equal, the product is maximum. 10. Find the maximum or minimum of u equals e to the power of x add y all over xy. Answer. Minimum for x equals y equals 1. 11. Find the maximum and minimum of u equals y add 2x minus 2 log base ey minus log base ex. Answer. Minimum, x equals a half and y equals 2. 12. A Telfordge bucket of given capacity has the shape of a horizontal isosceles triangular prism, with the apex underneath and the opposite face open. Find its dimensions in order that the least amount of iron sheet may be used in its construction. Answer. Angle at apex equals 90 degrees. Equal sides equals length equals the cube root of 2v. End of section 38.
Calculus Made Easy by Silvanus P. Thompson. Chapter 17. Integration, Part 1. The great secret has already been revealed that this mysterious symbol, the integral sign, which is, after all, only a long s, merely means the sum of, or the sum of all such quantities as. It therefore resembles that other symbol, the Greek sigma, which is also a sign of summation. There is this difference, however, in the practice of mathematical men, as to the use of these signs, that while sigma is generally used to indicate the sum of a number of finite quantities, the integral sign is generally used to indicate the summing up of a vast number of small quantities of indefinitely minute magnitude, mere elements, in fact, that go to make up the total required. Thus, integral dy equals y, and integral dx equals x. Anyone can understand how the whole of anything can be conceived of as made up of a lot of little bits, and the smaller the bits, the more of them there will be. Thus, a line 1 inch long may be conceived as made up of 10 pieces, each 1/10 of an inch long, or of 100 parts, each part being 1/100th of an inch long, or of 1,000,000 parts, each of which is 1/1,000,000th of an inch long. Or, pushing the thought to the limits of conceivability, it may be regarded as made up of an infinite number of elements, each of which is infinitesimally small. Yes, you will say, but what is the use of thinking of anything that way? Why not think of it straight off, as a whole? The simple reason is that there are a vast number of cases in which one cannot calculate the bigness of the thing as a whole without reckoning up the sum of a lot of small parts. The process of integrating is to enable us to calculate totals that otherwise we should be unable to estimate directly. Let us first take one or two simple cases to familiarize ourselves with this notion of summing up a lot of separate parts. Consider the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus etc. Here, each member of the series is formed by taking it half the value of the preceding. What is the value of the total if we could go on to an infinite number of terms? Every schoolboy knows that the answer is 2. Think of it, if you like, as a line. Begin with 1 inch, add a ½ inch, add a quarter, add an eighth, and so on. If at any point of the operation we stop, there will still be a piece wanting to make up the whole 2 inches, and the piece wanting will always be the same size as the last piece added. Thus, if after having put together 1, 1/2, and 1/4, we stop, there will be 1/4 wanting. If we go on till we have added 1/64, there will still be 1/64 wanting. The remainder needed will always be equal to the last term added. By an infinite number of operations only should we reach the actual 2 inches. Practically, we should reach it when we got to pieces so small that they could not be drawn. That would be after about 10 terms, for the 11th term is 1/1024th. If we want to go so far that not even a Whitworth's measuring machine would detect it, we should merely have to go to about 20 terms. A microscope would not show even the 18th term. So the infinite number of operations is no such dreadful thing after all. The integral is simply the whole lot. But, as we shall see, there are cases in which the integral calculus enables us to get at the exact total that there would be as the result of an infinite number of operations. In such cases, the integral calculus gives us a rapid and easy way of getting at a result that would otherwise require an interminable lot of elaborate working out. So we had best lose no time in learning how to integrate. End of section 39. Made Easy by Silvanus P. Thompson. Chapter 17. Integration, Part 2. Slopes of curves and the curves themselves. Let us make a little preliminary inquiry about the slopes of curves, for we have seen that differentiating a curve means finding an expression for its slope, or for its slopes at different points. Can we perform the reverse process of reconstructing the whole curve if the slope or slopes are prescribed for us? Go back to case 2 on page 82. Here we have the simplest of curves, a sloping line with the equation y equals ax plus b. We know that here b represents the initial height of y when x equals 0, and that a, which is the same as dy over dx, is the slope of the line. The line has a constant slope. All along it the elementary triangles have the same proportion between height and base. Suppose we were to take the dx's and dy's of finite magnitude so that 10 dx's made up 1 inch. Then there would be 10 little triangles. Now suppose that we were ordered to reconstruct the curve, starting merely from the information that dy over dx equals a. What could we do? Still taking the little d's as of finite size, we could draw 10 of them, all with the same slope, and then put them together end to end, like this. And, as the slope is the same for all, they would join to make, as in Figure 48, a sloping line, sloping with the correct slope dy over dx equals a. And whether we take the dy's and dx's as finite or infinitely small, as they are all alike, clearly y over x equals a, if we reckon y as the total of all the dy's and x as the total of all the dx's. But whereabouts are we to put this sloping line? Are we to start at the origin, uppercase O, or higher up? As the only information we have is as to the slope, we are without any instructions as to the particular height above uppercase O. In fact, the initial height is undetermined. The slope will be the same, whatever the initial height. Let us therefore make a shot at what may be wanted, and start the sloping line at a height uppercase C above uppercase O. That is, we have the equation y equals ax plus uppercase C. It becomes evident now that in this case the added constant means a particular value that y has when x equals 0. Now let us take a harder case, that of a line the slope of which is not constant, but turns up more and more. Let us assume that the upward slope gets greater and greater in proportion as x grows. In symbols this is dy over dx equals ax. Or, to give a concrete case, take a equals 1/5, so that dy over dx equals 1/5 x. Then we had best begin by calculating a few of the values of the slope at different values of x, and also draw little diagrams of them. When x equals 0, dy over dx equals 0. X equals 1, dy over dx equals 0.2. X equals 2, dy over dx equals 0.4. X equals 3, dy over dx equals 0.6. X equals 4, dy over dx equals 0.8. X equals 5, dy over dx equals 1.0. Now try to put the pieces together, setting each so that the middle of its base is the proper distance to the right, and so that they fit together at the corners. Thus, Figure 49. The result is, of course, not a smooth curve, but it is an approximation to one. If we had taken bits half as long and twice as numerous, like Figure 50, we should have a better approximation. But for a perfect curve, we ought to take each dx and its corresponding dy infinitesimally small and infinitely numerous. Then how much ought the value of any y to be? Clearly, at any point uppercase P of the curve, the value of y will be the sum of all the little dy's from 0 up to that level. That is to say, integral dy equals y. And as each dy is equal to 1/5 x times dx, it follows that the whole y will be equal to the sum of all such bits as 1/5 x times dx, or as we should write it, integral 1/5 x times dx. Now if x had been constant, integral 1/5 x times dx would have been the same as 1/5 x integral dx, or 1/5 x squared. But x began by being 0, and increases to the particular value of x at the point uppercase P, so that its average value from 0 to that point is 1/2 x. Hence, integral 1/5 x dx equals 1/10 x squared, or y equals 1/10 x squared. But, as in the previous case, this requires the addition of an undetermined constant C, because we have not been told at what height above the origin the curve will begin when x equals 0. So we write, as the equation of the curve drawn in figure 51, y equals 1/10 x squared plus C. End of section 40. Made Easy by Silvanus P. Thompson, section 41. Exercises 16. 1. Find the ultimate sum of 2/3 plus 1/3 plus 1/6 plus 1/12 plus 1/24 plus etc. Answer: 1 1/3. 3. If log to the base epsilon of the quantity 1 plus x equals x minus the quantity x squared over 2 plus the quantity x cubed over 3 minus the quantity x to the 4th over 4 plus etc., find log to the base epsilon of 1.3. Answer: 0.2624. 4. Following a reasoning similar to that explained in this chapter, find y. A. If dy over dx equals 1/4 x. B. If dy over dx equals cosine x. Answers: A. Y equals 1/8 x squared plus C. B. Y equals sine x plus C. 5. If dy over dx equals 2x plus 3, find y. Answer: y equals x squared plus 3x plus C. End of section 41. Differentiating is the process by which, when y is given us as a function of x, we can find dy over dx. Like every other mathematical operation, the process of differentiation may be reversed. Thus, if differentiating y equals x to the 4th gives us dy over dx equals 4x cubed, if one begins with dy over dx equals 4x cubed, one would say that reversing the process would yield y equals x to the 4th. But here comes in a curious point. We should get dy over dx equals 4x cubed if we had begun with any of the following: x to the 4th, or x to the 4th plus a, or x to the 4th plus c, or x to the 4th with any added constant. So it is clear that in working backwards from dy over dx to y, one must make provision for the possibility of there being an added constant, the value of which will be undetermined until ascertained in some other way. So, if differentiating x to the n power yields nx to the n minus 1 power, going backwards from dy over dx equals nx to the n minus 1 power will give us y equals x to the n power plus C, where C stands for the yet undetermined possible constant. Clearly, in dealing with powers of x, the rule for working backwards will be increase the power by 1, then divide by that increased power and add the undetermined constant. So, in the case where dy over dx equals x to the n power, working backwards, we get y equals the quantity 1 over n plus 1, n quantity, times x to the n plus 1 power plus C. If differentiating the equation y equals ax to the n power gives us dy over dx equals anx to the n minus 1 power, it is a matter of common sense that beginning with dy over dx equals anx to the n minus 1 power and reversing the process will give us y equals ax to the n power. So when we are dealing with the multiplying constant, we must simply put the constant as a multiplier of the result of the integration. Thus, if dy over dx equals 4x squared, The reverse process gives us y equals 4/3 x cubed. But this is incomplete, for we must remember that if we had started with y equals ax to the n power plus uppercase C, where uppercase C is any constant quantity whatever, we should equally have found dy over dx equals anx to the n minus 1 power. So therefore, when we reverse the process, we must always remember to add on this undetermined constant, even if we do not yet know what its value will be. This process, the reverse of differentiating, is called integrating, for it consists in finding the value of the whole quantity y when you are given only an expression for dy, or for dy over dx. Hitherto, we have as much as possible kept dy and dx together as a differential coefficient. Henceforth, we shall more often have to separate them. If we begin with a simple case, dy over dx equals x squared, we may write this, if we like, as dy equals x squared dx. Now this is a differential equation, which informs us that an element of y is equal to the corresponding element of x multiplied by x squared. Now what we want is the integral. Therefore, write down with the proper symbol the instructions to integrate both sides. Thus, integral dy equals integral x squared dx. We haven't yet integrated, we have only written down instructions to integrate. If we can, let us try. Plenty of other fools can do it, why not we also? The left-hand side is simplicity itself. The sum of all the bits of y is the same thing as y itself. So we may at once put y equals integral x squared dx. But when we come to the right-hand side of the equation, we must remember that what we have got to sum up together is not all the dx's, but all such terms as x squared dx. And this will not be the same as x squared integral dx, because x squared is not a constant. For some of the dx's will be multiplied by big values of x squared, and some will be multiplied by small values of x squared, according to what x happens to be. So we must bethink ourselves as to what we know about this process of integration being the reverse of differentiation. Now, our rule for this reversed process, when dealing with x to the nth power, is increase the power by 1 and divide by the same number as this increased power. That is to say, x squared dx will be changed to 1/3 x cubed. Footnote, you may ask, what has become of the little dx at the end? Well, remember that it was really part of the differential coefficient, and when changed over to the right-hand side, as in the x squared dx, serves as a reminder that x is the independent variable with respect to which the operation is to be effected, and, as a result of the product being totaled up, the power of x has increased by 1. You will soon become familiar with all this. End of footnote. Put this into the equation, but don't forget to add the constant of integration, uppercase C, at the end. So we get y equals 1/3 x cubed plus uppercase C. You have actually performed the integration. How easy! Let us try another simple case. Let dy over dx equal ax to the 12th, where a is any constant multiplier. Well, we found when differentiating that any constant factor in the value of y reappeared unchanged in the value of dy over dx. In the reversed process of integrating, it will therefore also reappear in the value of y. So we may go to work as before. Thus, dy equals ax to the 12th times dx. Integral dy equals integral ax to the 12th times dx. Integral dy equals a integral x to the 12th dx. Y equals a times 1/13 x to the 13th plus uppercase C. So that is done. How easy! We begin to realize now that integrating is a process of finding our way back as compared with differentiating. If ever, during differentiating, we have found any particular expression, in this example, ax to the 12th, we can find our way back to the y from which it was derived. The contrast between the two processes may be illustrated by the following remark due to a well-known teacher. If a stranger were set down in Trafalgar Square and told to find his way to Euston Station, he might find the task hopeless. But if he had previously been personally conducted from Euston Station to Trafalgar Square, it would be comparatively easy to him to find his way back to Euston Station. End of section 42. Integration of the sum or difference of two functions. Let dy over dx equal x squared plus x cubed. Then dy equals x squared dx plus x cubed dx. There is no reason why we should not integrate each term separately, for we found that when we differentiated the sum of two separate functions, the differential coefficient was simply the sum of the two separate differentiations. So when we work backwards, integrating, the integration will be simply the sum of the two separate integrations. Our instructions will then be integral dy equals integral of the quantity x squared plus x cubed dx equals integral x squared dx plus integral x cubed dx. Y equals 1/3 x cubed plus 1/4 x to the 4th plus uppercase C. If either of the terms had been a negative quantity, the corresponding term in the integral would have also been negative, so that differences are as readily dealt with as sums. End of section 43. Calculus Made Easy by Silvanus P. Thompson, Chapter 18, Integrating as a Reverse of Differentiating, Part 3, How to Deal with Constant Terms. Suppose there is, in the expression to be integrated, a constant term, such as this. dy over dx equals x to the nth plus b. This is laughably easy, for you have only to remember that when you differentiated the expression y equals ax, the result was dy over dx equals a. Hence, when you work the other way and integrate, the constant reappears, multiplied by x. So we get dy equals x to the nth dx plus b times dx. Integral dy equals integral x to the nth dx plus integral b dx. Y equals 1 over n plus 1 all times x to the n plus 1 power plus bx plus uppercase C. Here are a lot of examples on which to try your newly acquired powers. Examples. 1. Given dy over dx equals 24 x to the 11th, find y. Answer: y equals 2x to the 12th plus uppercase C. 2. Find the integral of the quantity a plus b times the quantity x plus 1 dx. It is the quantity a plus b integral the quantity x plus 1 dx. Or, open parenthesis, a plus b, close parenthesis, open bracket, integral x dx plus integral dx, close bracket, or, open parenthesis, a plus b, close parenthesis, open parenthesis, the quantity x squared over 2, end quantity, plus x, close parenthesis, plus uppercase C. 3. Given du over dt equals gt to the 1/2 power, find u. Answer: u equals 2/3 gt to the 3 over 2 power plus uppercase C. 4. dy over dx equals x cubed minus x squared plus x. Find y. dy equals open parenthesis, x cubed minus x squared plus x, close parenthesis, dx. Or dy equals x cubed dx minus x squared dx plus x dx. Y equals integral x cubed dx minus integral x squared dx plus integral x dx. And y equals 1/4 x to the fourth minus 1/3 x cubed plus 1/2 x squared plus uppercase C. 5. Integrate 9.75x to the 2.25 power dx. Answer: y equals 3x to the 3.25 power plus uppercase C. All these are easy enough. Let us try another case. Let dy over dx equal ax to the minus 1 power. Proceeding as before, we will write dy equals ax to the minus 1 power times dx. Integral dy equals a integral x to the minus 1 power dx. Well, but what is the integral of x to the minus 1 power dx? If you look back amongst the results of differentiating x squared and x cubed and x to the nth, etc., you will find we never got x to the minus 1 power from any one of them as the value of dy over dx. We got 3x squared from x cubed, we got 2x from x squared, we got 1 from x to the 1 power, that is, from x itself. But we did not get x to the minus 1 power from x to the 0 power for two very good reasons. First, x to the 0 power is simply equal to 1 and is a constant and could not have a differential coefficient. Secondly, even if it could be differentiated, its differential coefficient, got by slavishly following the usual rule, would be 0 times x to the minus 1 power, and that multiplication by 0 gives it 0 value. Therefore, when we now come to try to integrate x to the minus 1 power dx, we see that it does not come in anywhere in the powers of x that are given by the rule. Integral x to the nth dx equals the quantity 1 over n plus 1, end quantity, times x to the n plus 1 power. It is an exceptional case. Well, but try again. Look through all the various differentials obtained from various functions of x, and try to find amongst them x to the minus 1 power. A sufficient search will show that we actually did get dy over dx equals x to the minus 1 power as a result of differentiating the function y equals log base epsilon of x. Then, of course, since we know that differentiating log base epsilon of x gives us x to the minus 1 power, we know that by reversing the process, integrating dy equals x to the minus 1 power dx will give us y equals log base epsilon of x. But we must not forget the constant factor a that was given, nor must we omit to add the undetermined constant of integration. This then gives us as a solution to the present problem y equals a log base epsilon of x plus uppercase C. NB. Here note this very remarkable fact, that we could not have integrated in the above case if we had not happened to know the corresponding differentiation. If no one had found out that differentiating log base epsilon of x gave x to the minus 1 power, we should have been utterly stuck by the problem how to integrate x to the minus 1 power dx. Indeed, it should be frankly admitted that this is one of the curious features of the integral calculus, that you can't integrate anything before the reverse process of differentiating something else has yielded that expression which you want to integrate. No one, even today, is able to find the general integral of the expression dy over dx equals a to the minus x squared power, because a to the minus x squared power has never yet been found to result from differentiating anything else. Another simple case. Find integral of the quantity x plus 1 times quantity x plus 2 dx. On looking at the function to be integrated, you remark that it is the product of two different functions of x. You could, you think, integrate the quantity x plus 1 dx by itself, or the quantity x plus 2 dx by itself. Of course you could, but what to do with the product? None of the differentiations you have learned have yielded you for the differential coefficient a product like this. Failing such, the simplest thing is to multiply up the two functions and then integrate. This gives us integral of the quantity x squared plus 3x plus 2 dx. And this is the same as integral x squared dx plus integral 3x dx plus integral 2 dx. And performing the integrations, we get 1/3 x cubed plus 3 over 2 x squared plus 2x plus uppercase C. End of section 44. Now that we know that integration is the reverse of differentiation, we may at once look up the differential coefficients we already know and see from what functions they were derived. This gives us the following integrals ready-made. X to the minus 1 power integral x to the minus 1 power dx equals log base epsilon of x plus uppercase C. 1 over the quantity x plus a integral 1 over the quantity x plus a and quantity dx equals log base epsilon of the quantity x plus a and quantity plus uppercase C. Epsilon to the x power integral epsilon to the x power dx equals epsilon to the x power plus uppercase C. Epsilon to the minus x power integral epsilon to the minus x power dx equals minus epsilon to the minus x power plus uppercase C. For if y equals minus 1 over epsilon to the x power, dy over dx equals minus numerator epsilon to the x power times 0 minus 1 times epsilon to the x power, and numerator all over denominator epsilon to the 2x power, and denominator equals epsilon to the minus x power. Sine x integral sine x dx equals minus cosine x plus uppercase C. Cosine x integral cosine x dx equals sine x plus uppercase C. Also, we may deduce the following. Log base epsilon of x integral log base epsilon of x dx equals x of the quantity log base epsilon of x minus 1 and quantity plus uppercase C. For if y equals x log base epsilon of x minus x, dy over dx equals x over x plus log base epsilon of x minus 1 equals log base epsilon of x. Log base 10 of x integral log base 10 of x dx equals 0.4343x of the quantity log base epsilon of x minus 1 and quantity plus uppercase C. A to the x power integral a to the x power dx equals the quantity a to the x power over log base epsilon of a and quantity plus uppercase C. Cosine ax integral cosine ax dx equals the quantity 1 over a and quantity sine ax plus uppercase C. For if y equals sine ax, dy over dx equals a cosine ax. Hence, to get cosine ax, one must differentiate y equals the quantity 1 over a and quantity sine ax. Sine ax integral sine ax dx equals minus the quantity 1 over a and quantity cosine ax plus uppercase C. Try also cosine squared theta. A little dodge will simplify matters. Cosine 2 theta equals cosine squared theta minus sine squared theta equals 2 cosine squared theta minus 1. Hence, cosine squared theta equals 1/2 times the quantity cosine 2 theta plus 1, and integral cosine squared theta d theta equals 1/2 integral the quantity cosine 2 theta plus 1 and quantity d theta equals 1/2 integral cosine 2 theta d theta plus 1/2 integral d theta equals the quantity sine 2 theta over 4 and quantity plus the quantity theta over 2 end quantity plus uppercase C. See also the table of standard forms on pages 249 to 251. You should make such a table for yourself, putting in it only the general functions which you have successfully differentiated and integrated. See to it that it grows steadily. End of section 45. In many cases, it is necessary to integrate some expression for two or more variables contained in it, and in that case the sign of integration appears more than once. Thus, integral of function f of x, y, end function dx dy means that some function of the variables x and y has to be integrated for each. It does not matter in which order they are done. Thus, take the function x squared plus y squared. Integrating it with respect to x gives us integral x squared plus y squared dx equals 1/3 x cubed plus xy squared. Now integrate this with respect to y. Integral 1/3 x cubed plus xy squared dy equals 1/3 x cubed y plus 1/3 xy cubed, to which of course a constant is to be added. If we had reversed the order of the operations, the result would have been the same. In dealing with areas of surfaces and of solids, we have often to integrate both for length and breadth, and thus have integrals of the form integral u times dx dy, where u is some property that depends, at each point, on x and on y. This would then be called a surface integral. It indicates that the value of all such elements as u times dx times dy, that is to say, of the value of u over a little rectangle dx long and dy broad, has to be summed up over the whole length and whole breadth. Similarly, in the case of solids, where we deal with 3 dimensions. Consider any element of volume, the small cube whose dimensions are dx, dy, dz. If the figure of the solid be expressed by the function f of x, y, z, then the whole solid will have the volume integral. Volume equals integral of function f of x, y, z, end function, times dx times dy times dz. Naturally, such integrations have to be taken between appropriate limits in each dimension, and the integration cannot be performed unless one knows in what way the boundaries of the surface depend on x, y, and z. If the limits for x are from x sub 1 to x sub 2, those for y from y sub 1 to y sub 2, and those for z from z sub 1 to z sub 2, then clearly we have volume equals integral from z sub 1 to z sub 2, integral from y sub 1 to y sub 2, integral from x sub 1 to x sub 2 of function f of x, y, z, end function, times dx times dy times dz. There are, of course, plenty of complicated and difficult cases, but in general it is quite easy to see the significance of the symbols where they are intended to indicate that a certain integration has to be performed over a given surface, or throughout a given solid space. End of section 46. (1) Find integral y dx when y squared equals 4ax. Answer: numerator 4 times the square root of a times x to the 3/2 power, and numerator all over denominator 3, and denominator plus uppercase C. 2. Find integral 3/x to the 4th power dx. Answer: minus the quantity 1/x cubed and quantity plus uppercase C. 3. Find integral the quantity 1/a and quantity x cubed dx. Answer: the quantity x to the 4th power over 4a and quantity plus uppercase C. 4. Find integral of the quantity x squared plus a and quantity dx. Answer: 1/3 x cubed plus ax plus uppercase C. 5. Integrate 5x to the minus 7/2 power. Answer: minus 2x to the minus 5/2 power plus uppercase C. 6. Find integral of the quantity 4x cubed plus 3x squared plus 2x plus 1 and quantity dx. Answer: x to the 4th power plus x cubed plus x squared plus x plus uppercase C. 7. If dy over dx equals the quantity ax over 2 plus the quantity bx squared over 3 plus the quantity cx cubed over 4, find y. Answer: the quantity ax squared over 4 plus the quantity bx cubed over 9 plus the quantity cx to the 4th power over 16 plus uppercase C. 8. Find integral of the quantity x squared plus a all over x plus a and quantity dx. Answer: x squared plus a all over x plus a equals x minus a plus the quantity a squared plus a all over x plus a and quantity by division. Therefore the answer is the quantity x squared over 2 and quantity minus ax plus the quantity a squared plus a and quantity log base epsilon of the quantity x plus a and quantity plus uppercase C. 9. Find integral of the quantity x plus 3 and quantity cubed dx. Answer: the quantity x to the 4th power over 4 and quantity plus 3x cubed plus the quantity 27 over 2 and quantity x squared plus 27x plus uppercase C. 10. Find integral of the quantity x plus 2 times the quantity x minus a dx. Answer: the quantity x cubed over 3 plus the quantity 2 minus a over 2 and quantity times x squared minus 2ax plus uppercase C. 11. Find integral of the quantity the square root of x plus the cube root of x and quantity times 3a squared dx. Answer: a squared times the quantity 2x to the 3/2 power plus 9 over 4 x to the 4/3 power and quantity plus uppercase C. 12. Find integral of the quantity sine theta minus 1/2 and quantity d theta over 3. Answer: minus 1/3 cosine theta minus 1/6 theta plus uppercase C. 13. Find integral cosine squared a theta d theta. Answer: theta over 2 plus the quantity sine 2a theta over 4a, end quantity, plus uppercase C. 14. Find integral sine squared theta d theta. Answer: theta over 2 minus the quantity sine 2 theta over 4, end quantity, plus uppercase C. 15. Find integral sine squared a theta d theta. Answer: theta over 2 minus the quantity sine 2a theta over 4a, end quantity, plus uppercase C. 16. Find integral epsilon to the 3x power dx. Answer: 1/3 epsilon to the 3x power, plus uppercase C. 17. Find integral dx over 1 plus x. Answer: log base epsilon of the quantity 1 plus x, end quantity, plus uppercase C. 18. Find integral dx over 1 minus x. Answer: minus log base epsilon of the quantity 1 minus x, end quantity, plus uppercase C. End of section 47. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating, Part 1. One use of the integral calculus is to enable us to ascertain the values of areas bounded by curves. Let us try to get at the subject bit by bit. Let uppercase AB, figure 52, be a curve, the equation to which is known. That is, y in this curve is some known function of x. Think of a piece of the curve from the point uppercase P to the point uppercase Q. Let a perpendicular uppercase PM be dropped from uppercase P, and another uppercase QN from the point uppercase Q. Then call uppercase OM equals x sub 1 and uppercase ON equals x sub 2, and the ordinates uppercase PM equals y sub 1 and uppercase QN equals y sub 2. We have thus marked out the area uppercase PQNM that lies beneath the piece uppercase PQ. The problem is, how can we calculate the value of this area? The secret of solving this problem is to conceive the area as being divided up into a lot of narrow strips, each of them being of the width dx. The smaller we take dx, the more of them there will be between x sub 1 and x sub 2. Now the whole area is clearly equal to the sum of the areas of all such strips. Our business will then be to discover an expression for the area of any one narrow strip, and to integrate it so as to add together all the strips. Now think of any one of the strips. It will be like this, being bounded between two vertical sides, with a flat bottom dx and with a slightly curved, sloping top. Suppose we take its average height as being y. Then, as its width is dx, its area will be y dx. And seeing that we may take the width as narrow as we please, if we only take it narrow enough, its average height will be the same as the height at the middle of it. Now let us call the unknown value of the whole area uppercase S, meaning surface. The area of one strip will be simply a bit of the whole area, and may therefore be called d uppercase S. So we may write area of one strip equals d uppercase S equals y times dx. If then we add up all the strips, we get total area uppercase S equals integral d uppercase S equals integral y dx. So then our finding uppercase S depends on whether we can integrate y times dx for the particular case, when we know what the value of y is as a function of x. For instance, if you were told that for the particular curve in question, y equals b plus ax squared, no doubt you could put that value into the expression and say, then I must find integral of the quantity b plus ax squared and quantity dx. That is all very well, but a little thought will show you that something more must be done. Because the area we are trying to find is not the area under the whole length of the curve, but only the area limited on the left by uppercase PM and on the right by uppercase QN. It follows that we must do something to define our area between those limits. This introduces us to a new notion, namely that of integrating between limits. We suppose x to vary, and for the present purpose we do not require any value of x below x sub 1, that is, uppercase OM, nor any value of x above x sub 2, that is, uppercase ON. When an integral is to be thus defined between two limits, we call the lower of the two values the inferior limit, and the upper value the superior limit. Any integral so limited we designate as a definite integral, by way of distinguishing it from a general integral, to which no limits are assigned. In the symbols which give instructions to integrate, the limits are marked by putting them at the top and bottom, respectively, of the sign of integration. Thus the instruction integral from x equals x sub 1 to x equals x sub 2 of y times dx will be read, find the integral of y times dx between the inferior limit x sub 1 and the superior limit x sub 2. Sometimes the thing is written more simply, integral from x sub 1 to x sub 2 of y times dx. Well, but how do you find an integral between limits when you have got these instructions? Look again at figure 52. Suppose we could find the area under the larger piece of curve from uppercase A to uppercase Q. That is from x equals 0 to x equals x sub 2, naming the area uppercase AQNO. Then suppose we could find the area under the smaller piece from uppercase A to uppercase P. That is from x equals 0 to x equals x sub 1, namely the area uppercase APMO. If then we were to subtract the smaller area from the larger, we should have left as a remainder the area uppercase PQNM, which is what we want. Here we have the clue as to what to do. The definite integral between the two limits is the difference between the integral worked out for the superior limit and the integral worked out for the lower limit. Let us then go ahead. First, find the general integral thus, integral y dx. And, as y equals b plus ax squared is the equation to the curve in figure 52, integral of the quantity b plus ax squared and quantity dx is the general integral which we must find. Doing the integration in question by the rule, we get bx plus the quantity a over 3 and quantity times x cubed plus uppercase C. And this will be the whole area from 0 up to any value of x that we may assign. Therefore, the larger area up to the superior limit x sub 2 will be bx sub 2 plus the quantity a over 3 and quantity times x sub 2 cubed plus uppercase C. And the smaller area up to the inferior limit x sub 1 will be bx sub 1 plus the quantity a over 3 and quantity times x sub 1 cubed plus uppercase C. Now subtract the smaller from the larger, and we get for the area uppercase S the value area uppercase S equals b times the quantity x sub 2 minus x sub 1 and quantity plus a over 3 times the quantity x sub 2 cubed minus x sub 1 cubed. This is the answer we wanted. Let us give some numerical values. Suppose b equals 10, a equals 0.06, and x sub 2 equals 8, and x sub 1 equals 6, then the area S is equal to 10 times the quantity 8 minus 6 plus 0.06 over 3 times the quantity 8 cubed minus 6 cubed equals 20 plus 0.02 times the quantity 512 minus 216 equals 20 plus 0.02 times 296 equals 20 plus 5.92 equals 25.92. Let us here put down a symbolic way of stating what we have ascertained about limits. Integral from x equals x sub 1 to x equals x sub 2 of y dx equals y sub 2 minus y sub 1, where y sub 2 is the integrated value of y dx corresponding to x sub 2 and y sub 1 that corresponding to x sub 1. All integration between limits requires the difference between two values to be thus found. Also note that, in making the subtraction, the added constant C has disappeared. Examples. 1. To familiarize ourselves with the process, let us take a case of which we know the answer beforehand. Let us find the area of the triangle which has base x equals 12 and height y equals 4. We know beforehand, from obvious mensuration, that the answer will come 24. Now here we have as the curve a sloping line for which the equation is y equals x over 3. The area in question will be integral from x equals 0 to x equals 12 of y times dx equals integral from x equals 0 to x equals 12 of x over 3 times dx. Integrating x over 3 times dx and putting down the value of the general integral in square brackets with the limits marked above and below, we get area equals open bracket 1/3 times 1/2 x squared close bracket from x equals 0 to x equals 12 plus C equals open bracket x squared over 6 close bracket from x equals 0 to x equals 12 plus C equals open bracket 12 squared over 6 close bracket minus open bracket 0 squared over 6 close bracket equals 144 over 6 equals 24, which is the answer. Let us satisfy ourselves about this rather surprising dodge of calculation by testing it on a simple example. Get some squared paper, preferably some that is ruled in little squares of 1/8 inch or 1/10 inch each way. On this squared paper, plot out the graph of the equation y equals x over 3. The values to be plotted will be x equals 0, y equals 0, x equals 3, y equals 1, x equals 6, y equals 2, x equals 9, y equals 3, x equals 12, y equals 4. Now reckon out the area beneath the curve by counting the little squares below the line, from x equals 0 as far as x equals 12 on the right. There are 18 whole squares and 4 triangles, each of which has an area equal to 1 1/2 squares, or in total 24 squares. Hence 24 is the numerical value of the integral of x over 3 dx between the lower limit of x equals 0 and the higher limit of x equals 12. As a further exercise, show that the value of the same integral between the limits of x equals 3 and x equals 15 is 36. 2. Find the area between limits x equals x sub 1 and x equals 0 of the curve y equals b over x plus a. Area equals integral from x equals 0 to x equals x sub 1 of y times dx equals integral from x equals 0 to x equals x sub 1 of b over x plus a dx. equals b, open bracket, log base epsilon of the quantity x plus a, close bracket, from 0 to x sub 1, plus uppercase C, equals b, open bracket, log base epsilon of the quantity x sub 1 plus a, minus log base epsilon of the quantity 0 plus a, close bracket, equals b, log base epsilon of the quantity numerator x sub 1 plus a over denominator a, which is the answer. NB. Notice that in dealing with definite integrals, the constant uppercase C always disappears by subtraction. Let it be noted that this process of subtracting one part from a larger to find the difference is really a common practice. How do you find the area of a plane ring, the outer radius of which is r sub 2 and the inner radius is r sub 1? You know from mensuration that the area of the outer circle is pi r sub 2 squared. Then you find the area of the inner circle, pi r sub 1 squared. Then you subtract the latter from the former and find area of ring equals pi times the quantity r sub 2 squared minus r sub 1 squared, which may be written pi times the quantity r sub 2 plus r sub 1 times the quantity r sub 2 minus r sub 1 equals mean circumference of ring times width of ring. 3. Here's another case, that of the die-away curve. Find the area between x equals 0 and x equals a of the curve whose equation is y equals b epsilon to the minus x power. Area equals b integral from x equals 0 to x equals a of epsilon to the minus x power times dx. The integration gives equals b, open bracket, minus epsilon to the minus x power, close bracket, from 0 to a, equals b, open bracket, the quantity minus epsilon to the minus a power, minus the quantity minus epsilon to the minus 0 power, close bracket, equals b times the quantity 1 minus epsilon to the minus a power. 4. Another example is afforded by the adiabatic curve of a perfect gas, the equation to which is PV to the n power equals C, where P stands for pressure, V for volume, and n is of the value 1.42. Find the area under the curve, which is proportional to the work done in suddenly compressing the gas from volume V sub 2 to volume V sub 1. Here we have area equals integral from V equals V sub 1 to V equals V sub 2 of CV to the minus n power times dV equals C, open bracket, the quantity 1 over 1 minus n, end quantity, times V to the 1 minus n power, close bracket, from V sub 1 to V sub 2, equals C times the quantity 1 over 1 minus n, end quantity, times the quantity V sub 2 to the 1 minus n power minus V sub 1 to the 1 minus n power, equals the quantity minus C over 0.42, end quantity, times the quantity 1 over V sub 2 to the 0.42 power minus 1 over V sub 1 to the 0.42 power. An exercise. Prove the ordinary mensuration formula that the area uppercase A of a circle whose radius is uppercase R is equal to pi uppercase R squared. Consider an elementary zone or annulus of the surface of breadth dr situated at a distance r from the center. We may consider the entire surface as consisting of such narrow zones, and the whole area uppercase A will simply be the integral of all such elementary zones from center to margin, that is, integrated from r equals 0 to r equals uppercase R. We have therefore to find an expression for the elementary area d_A of the narrow zone. Think of it as a strip of breadth dr and of a length that is the periphery of the circle of radius r, that is, a length of 2πr. Then we have as the area of the narrow zone d_A equals 2πr dr. Hence the area of the whole circle will be A equals integral d_A equals integral from r equals 0 to r equals R of 2πr times dr equals 2π integral from r equals 0 to r equals R of r times dr. Now the general integral of r times dr is 1/2 r squared. Therefore A equals 2π open bracket 1/2 r squared close bracket from r equals 0 to r equals R. Or A equals 2π open bracket 1/2 R squared minus 1/2 times 0 squared close bracket, whence A equals pi R squared. Another exercise. Let us find the mean ordinate of the positive part of the curve y equals x minus x squared. To find the mean ordinate, we shall have to find the area of the piece OMN, and then divide it by the length of the base On. But before we can find the area, we must ascertain the length of the base, so as to know up to what limit we are to integrate. At N, the ordinate y has 0 value. Therefore we must look at the equation and see what value of x will make y equal 0. Now clearly, if x is 0, y will also be 0, the curve passing through the origin O. But also, if x equals 1, y equals 0, so that x equals 1 gives us the position of the point N. Then the area wanted is equals integral from x equals 0 to x equals 1 of the quantity x minus x squared dx equals open bracket 1/2 x squared minus 1/3 x cubed close bracket from 0 to 1 equals open bracket 1/2 minus 1/3 close bracket minus open bracket 0 minus 0 close bracket equals 1/6. But the base length is 1. Therefore the average ordinate of the curve equals 1/6. NB. It will be a pretty and simple exercise in maxima and minima to find by differentiation what is the height of the maximum ordinate. It must be greater than the average. The mean ordinate of any curve over a range from x equals 0 to x equals x sub 1 is given by the expression mean y equals 1 over x sub 1 integral from x equals 0 to x equals x sub 1 of y times dx. One can also find in the same way the surface area of a solid of revolution. Example: the curve y equals x squared minus 5 is revolving about the axis of x. Find the area of the surface generated by the curve between x equals 0 and x equals 6. A point on the curve, the ordinate of which is y, describes a circumference of length 2πy, and a narrow belt of the surface of width dx corresponding to this point has for area 2πy dx. The total area is 2π integral from x equals 0 to x equals 6 of y dx equals 2π integral from x equals 0 to x equals 6 of the quantity x squared minus 5 dx equals 2π open bracket x cubed over 3 minus 5x close bracket from 0 to 6 equals 6.28 times 42 equals 263.76. End of section 48. Areas in polar coordinates. When the equation of the boundary of an area is given as a function of the distance r of a point of it from a fixed point O, called the pole, and of the angle which r makes with the positive horizontal direction OX, the process just explained can be applied just as easily, with a small modification. Instead of a strip of area, we consider a small triangle OAB, the angle at O being d theta, and we find the sum of all the little triangles making up the required area. The area of such a small triangle is approximately the quantity A_B over 2 n quantity times r, or the quantity r d theta over 2 n quantity times r. Hence the portion of the area included between the curve and two positions of r, corresponding to the angles theta sub 1 and theta sub 2, is given by 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of r squared d theta. Examples. 1. Find the area of the sector of 1 radian in a circumference of radius a inches. The polar equation of the circumference is evidently r equals a. The area is 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of a squared d theta equals a squared over 2 integral from theta equals 0 to theta equals 1 of d theta equals a squared over 2. 2. Find the area of the first quadrant of the curve, known as Pascal's snail, the polar equation of which is r equals a times the quantity 1 plus cosine theta. Area equals 1/2 integral from theta equals 0 to theta equals pi over 2 of a squared times the quantity 1 plus cosine theta end quantity squared d theta equals a squared over 2 integral from theta equals 0 to theta equals pi over 2 of the quantity 1 plus 2 cosine theta plus cosine squared theta end quantity d theta equals a squared over 2 open bracket theta plus 2 sine theta plus theta over 2 plus sine 2 theta over 4 close bracket from 0 to pi over 2 equals numerator a squared times the quantity 3 pi plus 8 and numerator over denominator 8. End of section 49. We have done with the area of a little strip of a surface, we can, of course, just as easily do with the volume of a little strip of a solid. We can add up all the little strips that make up the total solid and find its volume, just as we have added up all the small little bits that made up an area to find the final area of the figure operated upon. Examples. 1. Find the volume of a sphere of radius r. A thin spherical shell has for volume 4 pi x squared dx. Summing up all the concentric shells which make up the sphere, we have volume sphere equals integral from x equals 0 to x equals r of 4 pi x squared dx equals 4 pi open bracket x cubed over 3 close bracket from 0 to r equals 4 over 3 pi r cubed. We can also proceed as follows. A slice of the sphere of thickness dx has for volume pi y squared dx. Also, x and y are related by the expression y squared equals r squared minus x squared. Hence, volume sphere equals 2 integral from x equals 0 to x equals r of pi times the quantity r squared minus x squared end quantity dx equals 2 pi, open bracket, integral from x equals 0 to x equals r of r squared dx minus integral from x equals 0 to x equals r of x squared dx, close bracket, equals 2 pi, open bracket, r squared x minus the quantity x cubed over 3, close bracket, from 0 to r, equals the quantity 4 pi over 3, end quantity r cubed. 2. Find the volume of the solid generated by the revolution of the curve y squared equals 6x about the axis of x between x equals 0 and x equals 4. The volume of a strip of the solid is pi y squared dx. Hence, volume equals integral from x equals 0 to x equals 4 of pi y squared dx equals 6 pi integral from x equals 0 to x equals 4 of x dx equals 6 pi, open bracket, x squared over 2, close bracket, from 0 to 4, equals 48 pi, equals 150.8. End of section 50. Finding areas by integrating. Part 4. On quadratic means. In certain branches of physics, particularly in the study of alternating electric currents, it is necessary to be able to calculate the quadratic mean of a variable quantity. By quadratic mean is denoted the square root of the mean of the squares of all the values between the limits considered. Other names for the quadratic mean of any quantity are its virtual value or its RMS, meaning root mean square value. The French term is valeur efficace. If y is the function under consideration and the quadratic mean is to be taken between the limits of x equals 0 and x equals L, then the quadratic mean is expressed as the square root of the quantity 1 over L integral from 0 to L of y squared dx. Examples. 1. To find the quadratic mean of the function y equals ax. Here the integral is integral from 0 to L of a squared x squared dx, which is 1/3 a squared L cubed. Dividing by L and taking the square root, we have quadratic mean equals the quantity 1 over the square root of 3, end quantity AL. Here the arithmetical mean is 1/2 AL, and the ratio of quadratic to arithmetical mean, this ratio is called the form factor, is 2 over the square root of 3, equals 1.155. 2. To find the quadratic mean of the function y equals x to the a power, the integral is integral from x equals 0 to x equals L of x to the 2a power dx. That is, numerator L to the 2a plus 1 power over denominator 2a plus 1. Hence, quadratic mean equals the square root of the quantity, numerator L to the 2a power over denominator 2a plus 1. 3. To find the quadratic mean of the function y equals a to the x over 2 power, the integral is integral from x equals 0 to x equals L of, open parenthesis, a to the x over 2 power, close parenthesis, squared dx. That is, integral from x equals 0 to x equals L of a to the x power dx. Or, open bracket, a to the x power over log base epsilon of a, close bracket, from x equals 0 to x equals L, which is, numerator, the quantity a to the L power, end quantity, minus 1, over denominator, log base epsilon of a. Hence the quadratic mean is the square root of the quantity, numerator a to the L power minus 1 over denominator L log base epsilon of A. End of section 51.
Calculus Made Easy by Silvanus P. Thompson, Section 52. Exercises 18. 1. Find the area of the curve y equals x squared add x minus 5 between x equals 0 and x equals 6, and the mean ordinates between these limits. Answer. Area equals 60, mean ordinate equals 10. 2. Find the area of the parabola y equals 2a root x between x equals 0 and x equals a. Show that it is 2/3 of the rectangle of the limiting ordinate and of its abscissa. Answer. Area equals 2/3 of a times 2a root a. 3. Find the area of the positive portion of a sine curve and the mean ordinate. Answer. Area equals 2, mean ordinate equals 2 over pi equals 0.637. 4. Find the area of the positive portion of the curve y equals sin squared x and find the mean ordinate. Answer. Area equals 1.57, mean ordinate equals 0.5. 5. Find the area included between the two branches of the curve y equals x squared plus minus x to the power of 5 over 2, from x equals 0 to x equals 1. Also the area of the positive portion of the lower branch of the curve. Answer. 0.572, 0.0476. 6. Find the volume of a cone of radius of base r and of height h. Answer. Volume equals pi r squared h over 3. 7. Find the area of the curve y equals x cubed minus log base ex between x equals 0 and x equals 1. Answer. 1.25. 8. Find the volume generated by the curve y equals the square root of 1 add x squared, as it revolves around the axis of x between x equals 0 and x equals 4. Answer. 79.4. 9. Find the volume generated by a sine curve revolving around the axis of x. Find also the area of its surface. Answer. Volume equals 4.9348. Area of surface equals 12.57 from 0 to pi. 10. Find the area of the portion of the curve xy equals a, included between x equals 1 and x equals a. Find the mean ordinate between these limits. Answer. A log base a over a minus 1 log base ea. 11. Show that the quadratic mean of the function y equals sin x between the limits of 0 and pi radians is root 2 over 2. Find also the arithmetical mean of the same function between the same limits, and show that the form factor is 1.11. 12. Find the arithmetical and quadratic means of the function x squared add 3x add 2 from x equals 0 to x equals 3. Answer. Arithmetical mean 9.5. Quadratic mean 10.85. 13. Find the quadratic mean and the arithmetical mean of the function a1 sin x add a3 sin 3x. Answer. Quadratic mean equals 1 over root 2 times the square root of a1 squared add a3 squared. Arithmetical mean equals 0. The first involves a somewhat difficult integral, and may be stated thus. By definition the quadratic mean will be the square root of 1 over 2 pi integral between 0 and 2 pi, open brackets, a1 sin x add a3 sin 3x, close brackets, squared dx. Now the integration indicated by integral open brackets a1 squared sin squared x add 2a1 a3 sin x sin 3x add a3 squared sin squared 3x, close brackets, dx, is more readily obtained if for sin squared x we write 1 minus cos 2x all over 2. For 2 sin x sin 3x we write cos 2x minus cos 4x, and for sin squared 3x 1 minus cos 6x all over 2. Making these substitutions and integrating we get a1 squared over 2, open brackets, x minus sin 2x all over 2, close brackets, add a1, a3, open brackets, sin 2x all over 2 minus sin 4x all over 4, close brackets, add a3 squared over 2, open brackets, x minus sin 6x all over 6, close brackets. At the lower limit the substitution of 0 for x causes all this to vanish, while at the upper limit the substitution of 2 pi for x gives a1 squared pi add a3 squared pi, and hence the answer follows. 14. A certain curve has the equation y equals 3.42 times e to the power of 0.21x. Find the area included between the curve and the axis of x from the ordinate at x equals 2 to the ordinate at x equals 8. Find also the height of the mean ordinate of the curve between these points. Answer. Area equals 62.6 square units. Mean ordinate is 10.42. 15. Show that the radius of a circle, the area of which is twice the area of a polar diagram, is equal to the quadratic mean of all the values of r for that polar diagram. 16. Find the volume generated by the curve y equals plus or minus x over 6 times the square root of x open brackets 10 minus x close brackets, rotating about the axis of x. Answer. 436.3. This solid is pear-shaped. End of section 52. Things consists in licking them into some shape that can be integrated. The books, and by this is meant the serious books, on the integral calculus are full of plans and methods and dodges and artifices for this kind of work. The following are a few of them. Integration by parts. This name is given to a dodge, the formula for which is integral u dx equals ux minus integral x du add c. It is useful in some cases that you can't tackle directly, for it shows that if in any case integral x du can be found, then integral u dx can also be found. The formula can be deduced as follows. From page 37 we have d open brackets ux close brackets equals u dx add x du, which may be written u dx equals open brackets d ux close brackets minus x du, which by direct integration gives the above expression. Examples. 1. Find integral w sin w dw. Write u equals w, and for sin w dw write dx. We shall then have du equals dw, while integral sin w dw equals minus cos w equals x. Putting these into the formula, we get integral w sin w dw equals w open brackets minus cos w close brackets minus integral minus cos w dw equals minus w cos w add sin w add c. 2. Find integral x e to the power of x dx. Write u equals x, e to the power of x dx equals dv, then du equals dx, v equals e to the power of x, and integral x e to the power of x dx equals x e to the power of x minus integral e to the power of x dx by the formula equals x e to the power of x minus e to the power of x equals e to the power of x, open brackets, x minus 1, close brackets, add c. 3. Try integral cos squared theta d theta. U equals cos theta d theta equals dv. Hence, du equals minus sin theta d theta, v equals sin theta. Integral cos squared theta d theta equals cos theta sin theta add integral sin squared theta d theta equals 2 cos theta sin theta all over 2 add integral open brackets 1 minus cos squared theta close brackets d theta equals sin 2 theta all over 2 add integral d theta minus integral cos squared theta d theta. Hence 2 integral cos squared theta d theta equals sin 2 theta all over 2 add theta, and integral cos squared theta d theta equals 2 sin theta all over 4 add theta over 2 add c. 4. Find integral x squared sin x dx. Write x squared equals u, sin x dx equals dv. Then du equals 2x dx, v equals minus cos x. Integral x squared sin x dx equals minus x squared cos x add to integral x cos x dx. Now find integral x cos x dx integrating by parts, as in example 1 above. Integral x cos x dx equals x sin x add cos x add c. Hence, x squared sin x dx equals minus x squared cos x add 2x sin x add 2 cos x add c dash equals 2 open brackets x sin x add cos x open brackets 1 minus x squared over 2 close brackets add c dash. 5. Find integral square root of 1 minus x squared dx. Write u equals square root of 1 minus x squared dx equals dv. Then du equals minus x dx over square root of 1 minus x squared and x equals v, so that integral square root of 1 minus x squared dx equals x square root 1 minus x squared add integral x squared dx over square root of 1 minus x squared. Here we may use a little dodge, for we can write integral the square root of 1 minus x squared dx equals integral open brackets 1 minus x squared close brackets dx all over the square root of 1 minus x squared equals dx over the square root of 1 minus x squared minus integral x squared dx over the square root of 1 minus x squared. Adding these two last equations we get rid of integral x squared dx over the square root of 1 minus x squared, and we have 2 integral square root of 1 minus x squared dx equals x times the square root of 1 minus x squared add integral dx over the square root of 1 minus x squared. Do you remember meeting dx over the square root of 1 minus x squared? It is got by differentiating y equals arc sin x. Hence its integral is arc sin x, and so integral square root of 1 minus x squared dx equals x square root of 1 minus x squared all over 2 add a half arc sin x add c. You can try now some exercises by yourself. You will find some at the end of this chapter. Substitution. This is the same dodge as explained in chapter 9, page 66. Let us illustrate its application to integration by a few examples. 1. Integral square root of 3 add x dx. Let 3 add x equals u, dx equals du. Replace integral u to the power of a half du equals 2 over 3 u to the power of 3 over 2 equals 2 over 3 open brackets 3 add x close brackets to the power of 3 over 2. 2. integral dx over e to the power of x add e to the power of minus x. Let e to the power of x equals u, du over dx equals e to the power of x, and dx equals du over e to the power of x. So that dx over e to the power of x add e to the power of minus x equals integral du over e to the power of x, open brackets, e to the power of x add e to the power of minus x, close brackets, equals integral du over u, open brackets, u add 1 over u, close brackets, equals integral du over u squared add 1. Du over u squared add 1 is the result of differentiating arctan x, hence the integral is arctan e to the power of x. 3. Integral dx over x squared add 2x add 3 equals integral dx over x squared add 2x add 1 add 2 equals integral dx over, open brackets, x add 1 close brackets squared add, open brackets, square root of 2 close brackets squared. Let x add 1 equals u, dx equals du. Then the integral becomes integral du over u squared add, open brackets, square root of 2 close brackets squared. But du over u squared add a squared is the result of differentiating u equals 1 over a arctan u over a. Hence one has finally 1 over the square root of 2 arctan x add 1 all over the square root of 2 for the value of the given integral. Formulae of reduction are special forms applicable chiefly to binomial and trigonometrical expressions that have to be integrated and have to be reduced into some form of which the integral is known. Rationalisation and factorisation of denominator are dodges applicable in special cases, but they do not admit any short or general explanation. Much practice is needed to become familiar with these preparatory processes. The following example shows how the process of splitting into partial fractions, which we learned in chapter 13, page 118, can be made use of in integration. Take again integral dx over x squared add 2x add 3. If we split 1 over x squared add 2x add 3 into partial fractions, this becomes 1 over 2 square root of minus 2, open brackets, integral dx over x add 1 minus square root of minus 2 minus integral dx over x add 1 add square root of minus 2, close brackets, equals 1 over 2 square root of minus 2 log base e x add 1 minus square root of minus 2 over x add 1 add square root of minus 2. Notice that the same integral can be expressed sometimes in more than one way, which are equivalent to one another. Pitfalls. A beginner is liable to overlook certain points that a practised hand would avoid, such as the use of factors that are equivalent to either 0 or infinity, and the occurrence of indeterminate quantities such as 0 over 0. There is no golden rule that will meet every possible case. Nothing but practice and intelligent care will avail. An example of a pitfall which had to be circumvented arose in chapter 18, page 189, when we came to the problem of integrating x to the minus 1 dx. Triumphs. By triumphs must be understood the successes with which the calculus has been applied to the solution of problems otherwise intractable. Often in the consideration of physical relations one is able to build up an expression for the law governing the interaction of the parts or the forces that govern them, such expression being naturally in the form of a differential equation, that is, an equation containing differential coefficients with or without other algebraic quantities. And when such a differential equation has been found, one can get no further until it has been integrated. Generally it is much easier to state the appropriate differential equation than to solve it. The real trouble begins then only when one wants to integrate, unless indeed the equation is seen to possess some standard form of which the integral is known, and then the triumph is easy. The equation which results from integrating a differential equation is called its solution, and it is quite astonishing how in many cases the solution looks as if it had no relation to the differential equation of which it is the integrated form. The This means that the actual result of solving it is called its solution, but many mathematicians would say, with Professor Forsyth, every differential equation is considered as solved when the value of the dependent variable is expressed as a function of the independent variable by means either of known functions or of integrals, whether the integration in the latter can or cannot be expressed in terms of functions already known. End footnote. The solution often seems as different from the original expression as a butterfly does from the caterpillar that it was. Who would have supposed that such an innocent thing as dy over dx equals 1 over a squared minus x squared could blossom into y equals 1 over 2a log base e a add x over a minus x add c, yet the latter is the solution of the former. As a last example, let us work out the above together. By partial fractions, 1 over a squared minus x squared equals 1 over 2a open bracket a add x close bracket add 1 over 2a open bracket a minus x close bracket. dy equals dx over 2a open brackets a add x close bracket add dx over 2a open brackets a minus x close bracket. Y equals 1 over 2a open bracket integral dx over a add x add integral dx over a minus x close bracket equals 1 over 2a open brackets log base e open brackets a add x close brackets minus log base e open brackets a minus x close bracket equals 1 over 2a log base e a add x over a minus x add c. Not a very difficult metamorphosis. There are whole treatises, such as Boole's differential equations, devoted to the subject of thus finding the solutions for different original forms. End of section 53. Made easy by Silvanus P. Thompson. Section 54. Exercises 19. 1. Find integral square root of a squared minus x squared dx. Answer. X square root of a squared minus x squared all over 2 add a squared over 2 sin to the power of minus 1 x over a add c. 2. Find integral x log base e x dx. Answer. X squared over 2 open brackets log base e x minus a half close brackets add c. 3. Find integral x to the power of a log base e x dx. Answer. X to the power of a add 1 all over a add 1 open brackets log base e x minus 1 over a add 1 close brackets add c. 4. Find integral e to the power of x cos e to the power of x dx. Answer. Sin e to the power of x add c. 5. Find integral 1 over x cos open brackets log base e x close brackets dx. Answer. Sin open brackets log base e x close brackets add c. 6. Find integral x squared e to the power of x dx. Answer. E to the power of x open brackets x squared minus 2x add 2 close brackets add c. 7. Find integral open brackets log base e x close brackets to the power of a all over x dx. Answer. 1 over a add 1 open brackets log base e x close brackets to the power of a add 1 add c. 8. Find integral dx over x log base e x. Answer. Log base e open brackets log base e x close brackets add c. 9. Find integral 5x add 1 all over x squared add x minus 2 dx. Answer. 2 log base e open brackets x minus 1 close brackets add 3 log base c, open brackets, x add 2, close brackets, add c. 10. Find integral, open brackets, x squared minus 3, close brackets, dx, all over x cubed minus 7x add 6. Answer. Half log base e, open brackets, x minus 1, close brackets, add 1/5 log base e, open brackets, x minus 2, close brackets, add 3/10 log base e, open brackets, x add 3, close brackets, add c. 11. Find integral b dx all over x squared minus a squared. Answer. b over 2a log base e x minus a over x add a, add c. 12. Find integral 4x dx all over x to the power of 4 minus 1. Answer. Log base e x squared minus 1 over x squared add 1, add c. 13. Find integral dx over 1 minus x to the power of 4. Answer. 1/4 log base e 1 add x over 1 minus x, add a half arc tan x, add c. 14. Find integral dx over x times the square root of a minus bx squared. Answer. 1 over root a log base e root a minus root a minus bx squared all over x root a. Let 1 over x equals v, then in the result let square root of v squared minus b over a equal v minus u. You had better differentiate now the answer and work back to the given expression as a check. End of section 54. Calculus Made Easy by Silvanus P. Thompson. Chapter 21. Finding some Solutions, Part 1. In this chapter we go to work finding solutions to some important differential equations, using for this purpose the processes shown in the preceding chapters. The beginner, who now knows how easy most of these processes are in themselves, will here begin to realise that integration is an art. As in all arts, so in this, facility can be acquired only by diligent and regular practice. He who would attain that facility must work out examples and yet more examples, such as are found abundantly in all the regular treatises on the calculus. Our purpose here must be to afford the briefest introduction to serious work. Example 1. Find the solution of the differential equation ay add b dy over dx equals 0. Transposing, we have b dy over dx equals minus ay. Now the mere inspection of this relation tells us that we have got to do with a case in which dy over dx is proportional to y. If we think of the curve which will represent y as a function of x, it will be such that its slope at any point will be proportional to the ordinate at that point, and will be a negative slope if y is positive. So obviously the curve will be a die-away curve, and the solution will contain e to the power of minus x as a factor. But, without presuming on this bit of sagacity, let us go to work. As both y and dy occur in the equation and on opposite sides, we can do nothing until we get both y and dy to one side, and dx to the other. To do this, we must split our usually inseparable companions dy and dx from one another. dy over y equals minus a over b dx. Having done the deed, we now see that both sides have got into a shape that is integratable, because we recognise dy over y, or 1 over y times dy, as a differential that we have met with when differentiating logarithms, so we may at once write down the instructions to integrate. Integral dy over y equals integral minus a over b dx, and doing the two integrations we have log base ey equals minus a over bx add log base ec, where log base ec is the yet undetermined constant of integration. Footnote We may write down any form of constant as the constant of integration, and the form log base EC is adopted here by preference, because the other terms in this line of equation are or are treated as logarithms, and it saves complications afterward if the added constant be of the same kind.
End footnote.
Then, delogarising, we get y equals c e to the power of minus a over b x, which is the solution required. Now this solution looks quite unlike the original differential equation from which it was constructed, yet to an expert mathematician they both convey the same information as to the way in which y depends on x. Now, as to the c, its meaning depends on the initial value of y. For if we put x equals 0 in order to see what value y then has, we find that this makes y equals c e to the power of minus 0, and as e to the power of minus 0 equals 1, we see that c is nothing else than the particular value of y at starting.
Footnote.
Compare what was said about the constant of integration with reference to figure 48 on page 184 and figure 51 on page 187.
End footnote.
This we may call y0, and so write the solution as y equals y0 e to the power of minus a over b x. Example 2. Let us take as an example to solve ay add b dy over dx equals g, where g is a constant. Again, inspecting the equation will suggest 1. That somehow or other e to the power of x will come into the solution, and 2. That if at any point of the curve y becomes either a maximum or a minimum, so that dy over dx equals 0, then y will have the value of g over a. But let us go to work as before, separating the differentials and trying to transform the thing into some integrable shape. b dy over dx equals g minus ay. dy over dx equals a over b, open brackets, g over a minus y, close brackets. dy all over y minus g over a equals minus a over b dx. Now we have done our best to get nothing but y and dy on one side and nothing but dx on the other, but is the result on the left side integrable? It is of the same form as the result on page 145, so writing the instructions to integrate we have integral dy all over y minus g over a equals minus integral a over b dx, and doing the integration and adding the appropriate constant, log base e open brackets y minus g over a close brackets equals minus a over bx add log base ec, whence y minus g over a equals c e to the power of minus a over bx, and finally y equals g over a add c e to the power of minus a over bx, which is the solution. If the condition is laid down that y equals 0 when x equals 0, we can find c, for then the exponential becomes equals 1, and we have 0 equals g over a add c, c equals minus g over a. Putting in this value, the solution becomes y equals g over a open brackets 1 minus e to the power of minus a over b x close brackets. But further, if f grows indefinitely, y will grow to a maximum, for when x equals infinity, the exponential equals 0, giving y max equals g over a. Substituting this, we get finally y equals y max open brackets 1 minus e to the power of minus a over bx close brackets. This result is also of importance in physical science. Example 3. Let ay add b dy over dt equals g times sin 2 pi nt. We shall find this much less tractable than the preceding. First divide through by b. dy over dt add a over by equals g over b times sin 2 pi nt. Now as it stands, the left side is not integratable. but it can be made so by the artifice, and this is where skill and practice suggest a plan, of multiplying all the terms by e to the power of a over bt, giving us dy over dt e to the power of a over bt, add a over by e to the power of a over bt equals g over b e to the power of a over bt times sin 2 pi nt, which is the same as dy over dt e to the power of a over bt add y d open brackets e to the power of a over bt close brackets over dt equals g over b e to the power of a over bt times sin 2 pi nt, and this being a perfect differential may be integrated thus, since if u equals y e to the power of a over bt, du over dt equals dy over dt e to the power of a over bt add y d open brackets e to the power of a over bt close brackets over dt. Y equals e to the power of a over bt equals g over b integral e to the power of a over bt times sin 2 pi nt dt add c, or y equals g over b e to the power of minus a over bt integral e to the power of a over bt times sin 2 pi nt dt add c e to the power of minus a over bt. Equation A. The last term is obviously a term which will die out as t increases, and may be omitted. The trouble now comes in to find the integral that appears as a factor. To tackle this we resort to the device of integration by parts, the general formula for which is integral u dv equals uv minus integral v du. For this purpose we write u equals e to the power of a over bt and dv equals sin 2 pi nt dt. We shall then have du equals e to the power of a over bt times a over b dt, and v equals minus 1 over 2 pi n cos 2 pi nt. Inserting these, the integral in question becomes integral e to the power of a over bt sin 2 pi nt dt equals minus 1 over 2 pi n times e to the power of a over bt times cos 2 pi nt minus integral minus 1 over 2 pi n cos 2 pi nt times e to the power of a over bt times a over b dt equals minus 1 over 2 pi n times e to the a over bt cos 2 pi nt add a over 2 pi nb integral e to the power of a over b t times cos 2 pi nt dt. Equation B. The last integral is still irreducible. To evade the difficulty, repeat the integration by parts of the left side, but treating it in the reverse way by writing u equals sin 2 pi nt and dv equals e to the power of a over bt dt, whence du equals 2 pi n times cos 2 pi nt times dt, and v equals b over a e to the power of a over bt. Inserting these, we get integral e to the power of a over bt times sin 2 pi nt dt equals b over a times e to the power of a over bt times sin 2 pi nt minus 2 pi nb all over a integral e to the power of a over bt times cos 2 pi nt dt. Equation C. Noting that the final intractable integral in C is the same as that in B, we may eliminate it by multiplying b by 2 pi nb all over a, and multiplying c by a over 2 pi nb, and adding them. The result, when cleared down, is integral e to the power of a over bt times sin 2 pi nt dt equals e to the power of a over bt open brackets AB sin 2 pi nt minus 2 pi nb squared cos 2 pi nt all over a squared add 4 pi squared n squared b squared, close brackets. Inserting this value in a, we get y equals g, open brackets, a sin 2 pi nt minus 2 pi nb cos 2 pi nt all over a squared add 4 pi squared n squared b squared, close brackets. To simplify still further, let us imagine an angle phi such that tan phi equals 2 pi nb over a. Then sin phi equals 2 pi nb all over the square root of a squared add 4 pi squared n squared b squared, and cos phi equals a over the square root of a squared add 4 pi squared n squared b squared. Substituting these, we get y equals g cos phi sin 2 pi nt minus sin phi cos 2 pi nt all over the square root of a squared add 4 pi squared n squared b squared, which may be written y equals g sin open brackets 2 pi nt minus phi close brackets all over the square root of a squared add 4 pi squared n squared b squared, which is the solution desired. This is indeed none other than the equation of an alternating electric current, where G represents the amplitude of the electromotive force, N the frequency, A the resistance, B the coefficient of self-induction of the circuit, and phi is an angle of lag. End of section 55. This made easy by Silvanus P. Thompson. Chapter 21. Finding some solutions. Part 2. Example 4. Suppose that m dx add n dy equals 0. We could integrate this expression directly if m were a function of x only and n a function of y only, but if both m and n are functions that depend on both x and y, how are we to integrate it? Is it itself an exact differential? That is, have m and n each been formed by partial differentiation from some common function u or not? If they have, then delta u over delta x equals m and delta u over delta y equals n. And if such a common function exists, then delta u over delta x dx add delta u over delta y dy is an exact differential. Now the test of the matter is this. If the expression is an exact differential, it must be true that dm over dy equals dn over dx, for then d open brackets du close brackets all over dx dy equals d open brackets du close brackets over dy dx, which is necessarily true. Take as an illustration the equation open brackets 1 add 3xy close brackets dx add x squared dy equals 0. Is this an exact differential or not? Apply the test. D open brackets 1 add 3xy close brackets over dy equals 3x, and d open brackets x squared close brackets over dx equals 2x, which do not agree. Therefore it is not an exact differential, and the two functions 1 add 3xy and x squared have not come from a common original function. Is it possible in such cases to discover, however, an integrating factor, that is to say, a factor such that if both are multiplied by this factor, the expression will become an exact differential? There is no one rule for discovering such an integrating factor, but experience will usually suggest one. In the present instance 2x will act as such. Multiplying by 2x we get open brackets 2x add 6x squared y close brackets dx add 2x cubed dy equals 0. Now apply the test to this. D open brackets 2x add 6x squared y close brackets over dy equals 6x squared. d open brackets 2x cubed close brackets over dx equals 6x squared, which agrees. Hence this is an exact differential and may be integrated. Now, if w equals 2x cubed y, dw equals 6x squared y dx, add 2x cubed dy, hence integral 6x squared y dx add integral 2x cubed dy equals w equals 2x cubed y, so that we get u equals x squared add 2x cubed y add c. Example 5. Let d2y over dt squared add n squared y equals 0. In this case we have a differential equation of the second degree in which y appears in the form of a second differential coefficient as well as in person. Transposing, we have d2y over dt squared equals minus n squared y. It appears from this that we have to do with a function such that its second differential coefficient is proportional to itself, but with reversed sign. In chapter 15 we found that there was such a function, namely the sine, or the cosine also, which possessed this property. So, without further ado, we may infer that the solution will be of the form y equals a sin open brackets pt add q close brackets. However, let us go to work. Multiply both sides of the original equation by 2 dy over dt and integrate, giving us 2 d2y over dt squared dy over dt add 2x squared y dy over dt equals 0, and us 2 d2y over dt squared dy over dt equals d open brackets dy over dt close brackets squared over dt open brackets dy over dt close brackets squared add n squared open brackets y squared minus c squared close brackets equals 0, c being a constant. Then, taking the square roots, dy over dt equals minus n square root of y squared minus c squared, and dy over the square root of c squared minus y squared equals n dt. But it can be shown that 1 over the square root of c squared minus y squared equals d open brackets arc sin y over c close brackets over dy, whence, passing from angles to sines, arc sin y over c equals nt add c1, and y equals c sin open brackets nt add c1 close brackets, where c1 is a constant angle that comes in by integration, or preferably this may be written y equals a sin nt add b cos nt, which is the solution. Example 6. d2y over dt squared minus n squared y equals 0. Here we obviously have to deal with a function y which is such that its second differential coefficient is proportional to itself. The only function we know that has this property is the exponential function, and we may be certain therefore that the solution of the equation will be of that form. Proceeding as before, by multiplying through by 2 dy over dx and integrating, we get 2 d2y over dx squared dy over dx minus 2x squared y dy over dx equals 0, and as 2 d2y over dx squared dy over dx equals d open brackets dy over dx close brackets squared over dx open brackets dy over dx close brackets squared minus n squared open brackets y squared add c squared close brackets equals 0, dy over dx minus n square root of y squared add c squared equals 0, where c is a constant, and dy over the square root of y squared add c squared equals n dx. Now, if w equals log base e open brackets y add the square root of y squared add c squared close brackets equals log base e u, dw over du equals 1 over u. Du over dy equals 1 add y over the square root of y squared add c squared equals y add square root of y squared add c squared all over the square root of y squared add c squared, and dw over dy equals 1 over the square root of y squared add c squared. Hence, integrating, this gives us log base e open brackets y add square root of y squared add c squared close brackets equals nx add log base e Big C. Y add square root of y squared add c squared equals big C e to the power of nx, equation 1. Now, open brackets, y add square root of y squared add c squared, close brackets, times, open brackets, minus y add square root of y squared add c squared, close brackets, equals c squared. Whence, minus y add square root of y squared add c squared equals c squared over big C e to the power of minus nx, equation 2. Subtracting equation 2 from equation 1 and dividing by 2, we then have y equals half big C e to the power of nx minus a half c squared over big C e to the power of minus nx, which is more conveniently written y equals a e to the power of nx add b e to the power of minus nx. Or the solution, which at first sight does not look as if it had anything to do with the original equation, shows that y consists of two terms, one of which grows logarithmically as x increases, and of a second term which dies away as x increases. Example 7. Let b d2y over dt squared add a dy over dt add gy equals 0. Examination of this expression will show that, if b equals 0, it has the form of example 1, the solution of which was a negative exponential. On the other hand, if a equals 0, its form becomes the same as that of example 6, the solution of which is the sum of a positive and a negative exponential. It is therefore not very surprising to find that the solution of the present example is y equals open brackets e to the power of minus mt close brackets open brackets a e to the power of nt add b e to the power of minus nt close brackets, where m equals a over 2b and n equals the square root of a squared over 4b squared minus g over b. The steps by which this solution is reached are not given here. They may be found in advanced treatises. Example 8. d2y over dt squared equals a squared d2y over dx squared. It was seen that this equation was derived from the original y equals big F as a function of x add at little f as a function of x minus at, where big F and little f were any arbitrary functions of t. Another way of dealing with it is to transform it by a change of variables into d2y over du dv equals 0, where u equals x add at and v equals x minus at, leading to the same general solution. If we consider a case in which big F vanishes, then we have simply y equals little f as a function of x minus at, and this merely states that at the time t equals 0, y is a particular function of x, and may be looked upon as denoting that the curve of the relation of y to x has a particular shape. Then any change in the value of t is equivalent simply to an alteration in the origin from which x is reckoned. That is to say, it indicates that, the form of the function being conserved, it is propagated along the x direction with a uniform velocity a, so that whatever the value of the ordinate y at any particular time t0, at any particular point x0, the same value of y will appear at the subsequent time t1 at a point further along, the abscissa of which is x0 add a open brackets t1 minus t0 close brackets. In this case, the simplified equation represents the propagation of a wave, of any form, at a uniform speed along the x direction. If the differential equation had been written m d2y over dt squared equals k d2y over dx squared, the solution would have been the same, but with the velocity of propagation would have the value a equals the square root of k over m. You have now been personally conducted over the frontiers into the enchanted land, and in order that you may have a handy reference to the principal results, the author, in bidding you farewell, begs to present you with a passport in the shape of a convenient collection of standard forms. In the middle column are set down a number of the functions which most commonly occur. The results of differentiating them are set down on the left, the results of integrating them are set down on the right. May you find them useful. End of section 56.
Calculus Made Easy by Silvanus P. Thompson. Epilogue and Apologue. It may be confidently assumed that when this tractate book, of that there can be, from their point of view, no possible manner of doubt whatever. It commits several most grievous and deplorable errors. First, it shows how ridiculously easy most of the operations of the calculus really are. Secondly, it gives away so many trade secrets. By showing you that what one fool can do other fools can do also, it lets you see that these mathematical swells, who pride themselves on having mastered such an awfully difficult subject as the calculus, have no such great reason to be puffed up. They like you to think how terribly difficult it is, and don't want that superstition to be rudely dissipated. Thirdly, among the dreadful things they will say about "so easy," is this, that there is an utter failure on the part of the author to demonstrate with rigid and satisfactory completeness the validity of sundry methods which he has presented in simple fashion, and has even dared to use in solving problems. But why should he not? You don't forbid the use of a watch to every person who does not know how to make one. You don't object to the musician playing on a violin that he has not himself constructed. You don't teach the rules of syntax to children until they have already become fluent in the use of speech. It would be equally absurd to require general rigid demonstrations to be expounded to beginners in the calculus. One other thing will the professed mathematicians say about this thoroughly bad and vicious book, that the reason why it is so easy is because the author has left out all the things that are really difficult. And the ghastly fact about this accusation is that it is true. That is indeed why the book has been written for the legion of innocents who have hitherto been deterred from acquiring the elements of the calculus by the stupid way in which its teaching is almost always presented. Any subject can be made repulsive by presenting it bristling with difficulties. The aim of this book is to enable beginners to learn its language, to acquire familiarity with its endearing simplicities, and to grasp its powerful methods of solving problems, without being compelled to toil through the intricate, out of the way, and mostly irrelevant, mathematical gymnastics so dear to the unpractical mathematician. There are amongst young engineers a number on whose ears the adage that "what one fool can do another can" may fall with a familiar sound. They are earnestly requested not to give the author away, nor to tell the mathematicians what a fool he really is. End of Section 57. End of Calculus Made Easy, by Silvanus P. Thompson.